Want to take a second to welcome all of you to the University of Houston. Want to extend a special welcome to my colleagues from the University of Utah for being a part of this conversation here, for helping us organize this and put this together. Sorry for the technical challenges. We'll try and get back on time as quickly as we can, understanding that both Milind and I have 4 minutes to introduce this topic and welcome all of you, and also to thank a whole bunch of people for making this happen. First of all, just in the interest of safety, there are no fire drills planned. If you hear a fire alarm, if you hear a notification, it is real. We'll get out from here through multiple exits. The one that you came through, that's one way to get out. And then there are a series of exits on the right-hand side as well as on the left-hand side where you can get out of the building, and the muster point is out in the front of the hotel. So get that out of the way and make sure everybody is sure that if there is an emergency, it is real, and please do make sure that you get out in time and out of the building. So this is our first effort to put together a conference with a powerhouse from the University of Utah. They've been doing some fantastic work in the area of energy, along with the University of Houston, which is in the world's capital for energy and is also a significant powerhouse in energy. I'm going to try and walk you through some of this very, very quickly from the University of Houston side. So welcome. This is me. What we do really as a focused effort to build our efforts in energy is to educate, innovate, and build partnerships. And for that reason, the University of Houston has actually trademarked itself to be the energy university, something that nobody else did. So we grabbed that opportunity and took it on and said, being in the capital of energy, let's be the energy university. And so that's been a big focal point. The fonts are messed up. Just I'll tell you very quickly, we are a tier 1 university. It's a flagship university of 4 university systems. We educate 48,000 students on an annual basis on this campus, and about 75,000 students across the system of universities here. More than half of our students end up staying back in the Houston area. One of the remarkable things is we are perhaps the most diverse, or the second most diverse research universities in the country. We trade spots 1 and 2 with Rutgers University. This year we are number 2. Previous years we were number 1. So we do have a lot of different programs and research centers, but just to highlight for you in terms of some metrics, we do $240 million in research, and we are ranked 70th amongst all public universities by US News and World Report. I was going to try and play this video. I hope it can play. If it does, this is all I need to say. You can't hear the audio, so it's perhaps going to be lost on you, but this is the story about superconductivity. It is a flagship at the university in terms of research efforts. High temperature superconductivity has been an idea that's been around for about 40 years. It was first discovered at the University of Houston and has since been developed, where it's gone from the realm of science fiction to actually transforming energy. So superconductors are going to be the critical material to actually make fusion happen. It's also being used for transportation, levitated mag rails, as well as transportation from automobiles. So I'm not going to belabor the point here. I'm going to skip over and just thank a very important group that has helped us direct the efforts that we do at the university. And that's the Energy Advisory Board that we have. These are all C-level folks from the Energy Advisory Board. A couple of the members of that advisory board are in the audience here today. And a big thanks to them to really help shape the conversations that we have at the university to drive the research efforts. Our efforts are focused on traditional oil and gas, on the energy transition area, on areas of downstream chemicals, as well as an energy education. I'm going to very quickly jump over all of this just because in the interest of time, and just tell you that I'm Ramanan Krishnamorti. I'll be in the audience, happy to answer any questions that you might have, and it's a true delight to have the University of Utah here come and partner with us in this effort. And my co-conspirator is Milind Deo. Milind is an alumnus of the University of Houston. He got his PhD from the University of Houston as a chemical engineer, but he's gone on to achieve really great things at the University of Utah. I'm going to let him come and tell you a little bit about what he oversees there. So, Milind?
Thank you very much, Ramanan. We appreciate the warm welcome and are delighted to organize this joint meeting with the University of Houston. Okay, that's me. So I'm going to give you a quick overview of Energy and Geoscience Institute, which is basically an institute within the University of Utah. It has about a 50-year history, and we are part of a university that does about around $700 million in research. So we are also an R1 university with a large medical school and a fairly large business school, law school and all that. So the entire professional program. So EGI was formed in 1972 as basically two institutes. One was the frontier oil and gas exploration, and the other was geothermal, and these two merged in 1990 timeframe to create basically what is EGI. And currently we are organized into several of those sectors, and you will hear from researchers in each of those sectors: the conventional oil and gas, renewables and geothermal, grid resiliency, and decarbonization aspects. So I just wanted to show this one slide to highlight what's happening in the energy space right now. You basically see the energy mix in 2013 and energy mix now in 2023. Actually, when I made this chart, even as an energy professional, I was quite surprised to see that the proportion of oil and gas that the energy mix, that was part of the energy mix in 2013 actually increased from 62% to 68%. Coal, of course, went down, but natural gas made up for that and more. And it basically shows the challenge that we have in getting to what people are considering net zero by whatever metric you use and by whatever time period you look at, 2030 or 2050. Anyway, so the EIA chart there shows how the projections on carbon emissions over the next 30 years or so. So we need to really be, I think, on our game as we look at the different aspects of energy and how we can move the low carbon technologies forward, while of course providing sufficient energy for the world. And as part of that, we of course do conventional oil and gas. We do have some large databases that both onshore and offshore, and are looking at worldwide exploration and some shale research. We manage the Frontier Observatory for research in geothermal energy, and researchers from that are here forged. And as you probably have seen in the news, it has had some significant breakthroughs that are actually being used by commercial companies. There have been big advances in drilling, induced seismicity monitoring, as well as stimulation in dry hot rock, that those advances that are being created in Forge. We also manage several large carbon safe type demonstration projects, from what we call cradle to grave. It is capturing CO2, transporting it, and then storing it. We have decarbonization efforts and some efforts in hydrogen, and you will hear about that later in the program. And then we also have some projects going on the critical mineral space. So just like most energy groups around the world, we are looking at all aspects of energy transition while providing what we consider sufficient energy for the world. So at least from our perspective, what we want to do is to bring these two significant energy groups together to see what type of synergies we can realize. And so, of course, network, explore, discover, and I think as we meet, new ideas will come up and new initiatives, I think, new partnerships will be forged. So we basically are a landlocked state, whereas you have a state that is right next to a big ocean. We also have a big kind of a ocean in our midst, which currently is endangered, the Big Salt Lake. But anyway, so I think, and one of the motivations for bringing us together also was the football game on Friday or Saturday, when University of Utah, which is not doing that great this year, is meeting University of Houston. So very happy to see you all here, and we would like to continue this conversation. Thank you.
Thank you, Milind. So we'll get started with the program. So if anybody does want to go to the football game, let me know. We'll find you tickets to go there. Certainly something that, just as a side note, we were at ExxonMobil the other day. We had an alumni get-together, and 75 of our alumni who never came to football games decided to sign up when we made that offer. So that's the challenge here. If 76 people sign up here, we'll do one better. Let's have our first talk here today. We're going to start off with a legend. A legend in the area of CO2. He was the person who started and worked with SACROC. He's somebody who's worked at Chevron for a long time. Came to the University of Houston about 8 years ago, and we are truly blessed to have him as a faculty leader here. And that's Dr. Ganesh Thakur, and he is going to tell us a little bit about CO2 EOR and the energy transition. With that, Dr. Thakur.
Thank you, Dr. Ramanan. Thank you, Dr. Milind. It's a great pleasure for me to be here. And this morning, we are going to talk about CCUS and EOR. And I'm going to very briefly touch the subject because we cannot talk about a lot of things in 20 minutes. But we'll make sure this is a little bit about my background. And I'm not going to spend too much time regarding my background, but we have a website, and that information is available. But right from 1973, after my graduation from Penn State, I had been working on fluid injection projects all around the world. And as Dr. Milind showed here, the importance of the fossil fuel energy is still very important. But we have to be sure that we do these things in a very responsible way. It is Dr. Scott Tinker is going to be giving a presentation during the lunch today. He has said that it is important for us to have sustainable, reliable, and cost-effective energy source, which also addresses the environmental concerns. So this is very important for us to be working together in these areas. Let's face the fact, the scientific consensus is that it will be almost impossible to reach net zero emissions by 2050 without a significant global scale-up of CCS. So CCS, CCUS, and I believe enhanced oil recovery using CCUS and carbon capture and storage is going to play a very important role. This is our team at University of Houston. I have just highlighted a few names here. We have a variety of expertise available here, and we are looking forward to working with the University of Utah, Bob McPherson and his team, very, very closely, and we are also going to have a special session with them tomorrow morning. So let's look at where did CO2 EOR all started. It started in 1972 in the Sac Rock unit in Snyder, Texas. That's where it started. Long, long time ago. So we have a history of over 50 years of CO2 injection. And I had the pleasure of working in Snyder, Texas for a year on this project. And it really has been a great project since then. Now we see over 140 projects in the US, all commercial scale. Right now, the big players include companies like Oxy, and then other companies are also involved, but a lot of CO2 EOR successful projects going on. And there's a lot of debate about CO2 projects, whether they work from enhanced oil recovery point of view or not. When I worked in Chevron, almost 40 years, there was a lot of debate early on. Is this really an EOR project? Does it really give you values? And finally, I was convinced, and most people in the company were completely convinced that CO2 EOR is really a viable way of increasing oil production. So this is an example. We took a portion of the field, and we made sure that that field was almost at the residual oil saturation. And then we came in with CO2 injection, and what we find here is a big bump in oil production. So this methodology works very, very well. And based upon these pilots, based upon these experiments, other companies came in the Permian Basin, Shell, BP, ExxonMobil, other companies came in, and they all started doing successful CO2 projects. As I mentioned earlier, today, Oxy plays a very, very important role. We really don't have to go over the theoretical aspects of the CO2 flood, but this slide just shows very clearly that CO2 is playing a very important role. But if you go to any CO2 project, it looks like upstream expertise are very important at subsurface scale. But at the surface, it looks like all chemical engineering operations. Pretty much, almost like a little bit of refinery, little bit of separation, little bit of compression. All of these things play a very important role. I worked on projects in Kazakhstan, the Tengiz field for Chevron, and same thing you see there. Underground is all subsurface expertise. At the surface is all chemical engineering and refinery type of expertise required. So really, we integrate these things very, very well in this area. As I pointed out earlier, there are over 140 CO2 EOR projects successfully running in the US. And all over the world, 80 million tons per annum of CO2 is getting injected at this point in time in these projects. However, over 80% of the CO2 injected is not anthropogenic. They are CO2 coming in from natural reservoirs. So one of the lowest hanging fruits that we have at this point in time is to make those CO2 injection anthropogenic. And I must tell you one thing, people may not know this, the first CO2 project in the world, Sac Rock, was actually an anthropogenic project. Because at that time, natural CO2 did not exist. So we were collecting CO2 from the gas plants. And that CO2 was getting injected in Sac Rock. So Sac Rock showed the anthropogenic CO2 was the way to go. We were very fortunate at the University of Houston. I had a $5 million research grant from Oil India Limited. So we screened 50 of their reservoirs containing 2.5 billion barrels of oil in place. And almost all of those reservoirs are amenable to CO2 injection. And Milind, the beauty of those reservoirs are they all have aquifers below them, 10 times larger than the reservoir volume or even larger. So there is a tremendous potential to store CO2 in those aquifers as long as we produce those water. And producing those waters is very valuable commodity because India needs a lot of water resources at the surface level. And we have established a process of simulation, lab work, field implementation that we applied on this project. So in the interest of time, I'm not going to go over some of the patents that we received and some of the papers that we published. We're going to go directly into some of the great projects that the industry has. This is Chevron's big project in the Gorgon field. They have done a superb job. And it's not only because of the enhanced oil recovery that these projects are successful. They are successful as CCS projects. And yes, there will be some challenges on projects like this. But what I understand from the public information, that they were able to solve those challenges and making the project very, very successful. One of the projects that, and this is information from the public domain that I was personally involved with, was the methane injection project in the Agbami field for Chevron offshore deep water. And what it shows here, that even with methane injection, you can make some of these projects very successful, and the company had to do it because the Nigerian government had restriction of not flaring the gas at the surface. So they had to inject the gas. But we were fortunate. The reservoir has a dip angle of 30 degrees. It's a very light oil, and the injection gas is completely miscible with oil. First contact miscibility. So really, you have a great opportunity to do projects like this. And a very successful project. And I'm very proud of showing this, although my information is from the public domain, because I was involved in the initial design of this project. And this project, $5 billion capital project, very successful, producing over 225,000 barrels of oil per day for the last 10, 12 years at a flat rate almost. This is, we were also very lucky at the University of Houston here to receive a $6 million grant from the governor of Texas and the chancellor of the University of Houston. That was really helpful for my research lab. So we have been able to establish a great Milind Bhai CCS. We'll be showing it to you tomorrow. UR projects, and we can, and not only myself, but my colleagues also have similar labs, and really together we can do great jobs for CCS and CCUS related to EOR. Okay, great opportunities for us. Next generation CO2 EOR and storage technologies. But I want to spend a little bit time on one slide that I prepared just a few days ago that I want to share with you, that what we can learn from CCS, from EOR projects that we can apply to CCS projects. Okay. And another big advantage we have is 45Q, tax incentives. So that's going to play a very, very important role for us. But even with CO2 EOR projects, when you go to field implementation, life is not going to be that easy at high pressure, high temperature. Most of the projects at this point in time on CCUS EOR is at cold temperatures in the Permian Basin, where depth is lower, reservoir temperature is lower. But when you go to very high depth and when you go to very high temperature, then the challenges are there. So I want to mention this also, that it's not an easy solution. It's a constantly challenging situation that we have to be very, very careful about. So there are things that we can do. Where is the current stage? And what are the kind of things we can do? But I feel what it will take for us to move the needle in the CCUS areas is when the operating companies take a leading role. When the operating companies adopt this thing by sincerely adopting and doing the projects in the field, like what they are doing in the Gorgon field, like what they are doing in Canada, that they have to adopt it, and with or without tax advantage or tax incentives, if they can make those projects work. And if anybody can make those projects work, it's going to be the operating companies, because they have the expertise, they have the capitals, they have the people. And universities like ourselves in Utah, we can play a very important role in supporting them. So I'm going to go to my final slide in the interest of time. And basically, what my final slide says, that what CO2 EOR has already taught us about permanently storing carbon. Number one, comparison between CCS and CO2 EOR based on analyzing field data. We can do numerical modeling, we can do lab work, we can work with knowledge that we have gained from the injection wells, the knowledge that we have gained from surveillance and monitoring. And keeping our fingers crossed, no detectable caprock breaches and practically no surface leaks related to CO2 EOR in the last 50 years. That speaks very highly of the operating companies working in this area. However, we must realize that the timelines between CCS and CO2 EOR is quite different. CO2 EOR projects are for 50 years or less. CCS, we have to look at order of magnitude larger in terms of time. External boundaries between CCS and CO2 EOR, there are some differences. And CCS, we have to consider water production. That's what we have learned from our Indian projects. Next, CO2 EOR is subject to a smaller volumetric sweep because of large mobility and formation heterogeneities. 40 years ago, we were always trying to minimize the amount of CO2 injection in the reservoir because we didn't have enough CO2 available. Today, we have plenty of CO2 available. So we don't have to minimize the amount of CO2 be injected in the reservoirs. We need to maximize the amount of CO2 injection and retain those in the reservoir, therefore increasing our volumetric sweep. The source of CO2 differs. And in my opinion, as I pointed out earlier, about 80 million tons of CO2 can be transferred to anthropogenic CO2 today with the right government incentives, with the right kind of political environment. Therefore, there is a great opportunities to improve these things. Of course, there is a difference in economics in CCS and CO2 EOR. Almost all the CO2 EOR projects today are economically very successful. CCS, question mark. And an obvious product of commerce and storage is CO2 EOR itself. CO2 stored versus oil produced. When we look at the net zero, Dr. Milind, from that point of view. However, we have an opportunity not only in the reservoirs, but also in the aquifers if we produce water. And last but not the least, lessons learned from the reservoir management aspects of fluid injection. We, in the petroleum industry, inject water and gas all over the world. We inject onshore, we inject offshore, and we are very successful. And you saw some of the examples here. And we can transfer those expertise to CCS. Thank you, ladies and gentlemen. That concludes my talk.
What would you say to the materials discussions happening around steel and cement, and particularly in the presence of carbonic acid formed in this?
You know, it's a really very, very interesting. If you go to the Permian Basin, and the carbonic acid, as you know, is corrosive, but mildly corrosive, especially at lower temperatures. So really, it's not a big problem. And when we operated these projects, our operating costs never went up, practically. However, if you go to Gulf of Mexico, where I have just completed an offshore CO2 storage project study, under high temperatures, high pressures, you have to be careful. You have to be extremely careful in those kind of situations. So you cannot take it for granted. We have to continuously work very hard on it and think about high pressure, high temperature applications for CO2 injection. Thank you for a great question.
So as I mentioned to you, he's a legend, and we all sort of respect what he does and brings to the table here. So it's my pleasure to start the next conversation, and this is with another legend, and this is Rasoul Sorkhabi from the University of Utah, and he's going to tell us a little bit about hydrocarbons and basin R&D, both in the nation as well as international. So, Rasoul? If you want to, you can use this mic, or I'm sure you can use one of the handheld mics.
Good morning. Well, thank you for your participation this morning, and a huge thanks to the University of Utah for hosting this joint meeting. So my name is Rasoul Sorkhabi. I am a research professor at the University of Utah's EGI. I have been with the university for the past 22 years. Now, those of you who do not know about EGI, as my EGI director, Dr. Milind Deo, mentioned, actually EGI started in 1972 during the first oil shock. So we have been around for 52 years, continuous research and service to science and industry, so, and we are very, very proud of that. Next, please. Now, yes. Now, the focus of my presentation is on oil and gas, and I will share with you some of the activities and the directions we are taking in this space. We don't think that oil and gas is going to go away. Actually, I was talking to Christine Economides this morning. Last time I saw her and her late husband, Michael, was at a SPE meeting, and then she was just remarking that were Michael were here today, he would say that, you know, no exploration, no workforce training in oil and gas, then oil and gas prices will really go high. And I think I would agree with that. Now, where we are located, those of you who are geologists or know something about the geology of Utah, know that even though we may not be producing 45% of oil production in the U.S. As Texas does, but we have some of the best geological setting in the world, I would say. Salt Lake itself is a tectonic valley. It's part of the Basin Range extensional province, but we also have access to other tectonic slides, including high plateaus, Colorado Plateau, and also the Rocky Mountains, foreland basins, you name it. I guess except for the ultra deep water, we have almost every analog of any petroleum system and reservoir scale analogs in Utah. That's the building of EGI. As Milind mentioned, we are a mid-sized, I would say, research institute with dozens of researchers from different backgrounds, engineers as well as geoscientists. So there's a good synergy between the two groups, especially under Milind's leadership. And depending on the project, we collaborate with one another. Now, one of the cornerstones of EGI is the Corporate Associate Program. It's an annual subscription, mainly oil and gas companies. So we have some benefits package for the CAs or corporate associates. EGI Connect is one of them. That's a global database online. That comes part of the membership. We also have other benefits for our members. And lastly, as Milind mentioned, the ICORDS, which is a global offshore database. It's also part of the membership. So EGI Connect has its own website. The companies can go and see our reports. We have almost 1,000 EGI reports plus thousands of other documents, well logs and seismic lines. And every 2 years or so, we add to this portfolio. For example, since the COVID, over the past 4 years or so, we have added 40 major reports to our EGI Connect portfolio. Now, ICORDS is a web-based global database, mostly on petroleum basins. I have a brief video clip, if we can play it, if possible. This will save me lots of time in terms of...
This is an introduction to ICORDS Offshore, the Integrated Continent Ocean Research Data System for Offshore Basins, produced at the University of Utah's Energy and Geoscience Institute. The ICORDS program began at EGI with the realization that big data is the lifeblood of modern petroleum geoscience and technology. ICORDS is a multidisciplinary initiative to digitize and integrate geoscience data in a user-friendly platform for the benefit of energy companies. It is a web-based databank offered at an annual subscription to our clients. ICORDS has adopted a rigorous workflow for its database construction that includes deep data mining, quality control, and integration with digital systems that enables the user easy access, custom queries, and data analytics. ICORDS data comes from EGI's more than 5 decades of legacy data, as well as many other sources, including International Ocean Discovery Program, formerly DSDP-ODP, NOAA's National Geophysical Data Center, U.S. Geological Survey, U.S. Bureau of Ocean Energy Management, as well as data services and survey institutions from Canada, Australia, UK, Norway, the Netherlands, and several other countries. ICORDS Offshore incorporates a large set of data types and services, including nearly 23 million geoscientific data from rock samples, cores, and cuttings from thousands of wells. The data can be queried and filtered under various categories, such as well header, sample information, stratigraphic age and rock type, total organic carbon, pyrolysis, thermal maturity, petrophysical properties, sonic velocity, and gas compositional analysis. The data can be accessed from the built-in interactive map, or by applying one or more filters to return a data table. There are also built-in analytic tools to view and interpret the geochemical data, which can also be exported as JPG or XLSX files. We continuously update our data bank and strive to incorporate new data from various sources for our clients. In addition to geologic and geochemical data, Eiichi Offshore also offers access to thousands of seismic lines from around the world. There are also supportive data maps, such as heat flow and ocean floor age, to place the geochemical data in a regional context. Eiichi is an easy-to-use databank and research tool at your fingertips for subsurface energy industries. Exploration geoscientists will find Eiichi Offshore useful and easy to use. You can query and extract the geological, geochemical, and petrophysical data on specific wells or basins. You can plot and create figures for presentations and discussions. You can also upload your own data to augment the Eiichi data and use our built-in graphics to plot and export data and figures. The databank and graphic tools in Eiichi help exploration geoscientists compare and correlate wells and gain valuable insights into petroleum source and reservoir rocks in a given basin. Eiichi's research work and database construction is conducted by a team of EGI scientists and IT experts who collectively have over 100 years of experience in geoscience and petroleum research or information technology. Eiichi Offshore is a web-based databank offered at an annual subscription to our clients. Your annual membership delivers analytics-ready geoscience data on a unified platform for data discovery, transformation, on-demand visualization, and integration. For more information, you can send us messages via the contact form on Eiichi's Offshore website, eiichordsgeo.org, or direct email to the principal investigator. You may also visit EGI's website, egi.utah.edu.
Thank you. Now we can switch back to the PowerPoint file if possible. Okay, even though I'm talking on behalf of Eiichi, but this has been really a team effort, and I have listed some of the contributors and researchers, as well as IT experts working on Eiichi. Okay, I can skip these slides. Now, one of the moving to switch into specific projects. One of the projects which we have recently completed is the Guyana-Sriram Basins project. As you know, this basin has been very prolific in the past 10 years or so. Actually, outside of shale, this is the most, I would say, in terms of reserve growth, the best basin in the world. So if you are interested in, this report is ready to go, basically. It's, so if any of the company is interested in evaluating this and purchasing it, please contact us. Most of the wells which we analyzed were pre-Lisa. As you know, Lisa discovery really was the game changer in the Guyana-Sriram Basin. So most of the wells which we analyzed, the data come from pre-Lisa wells, which are really hard to find. We are developing a new research consortium on ultra-deep water plays, especially in the southern Atlantic margin as well as the equatorial Atlantic margin. Really, the motivation for this, as some of you may know, is the discovery of major, giant fields sitting on transitional crusts, which in the past were conceived as unproductive and almost infertile to petroleum systems. So we are trying to work out the crustal architecture of this place and then relate the basin evolution to petroleum systems in terms of source, charge, and accumulation. Next month, in November, one of our member companies will be hosting a meeting related to this consortium. So if you are interested, please contact me, and then I will give you more information. In the interest of time, I will skip this slide. Basically, as I mentioned, we are trying to pinpoint the source to accumulation pathways in ultra deep water plays. Now, another space we have been working is, of course, shale. Milind and his students have done lots of work on shale in terms of reservoir characterization. We have a poster today. I don't know where the posters are, but wherever they are, my colleague, Dr. Palash Panja, will be there, and then he can answer all your questions. So what we have tried to do is to create an app called Shale Smart, EGI Shale Smart, and we have data, production data, and some geological data on almost 100,000 horizontal wells from almost a dozen shale tight plays in the US. And what we are trying to do is reverse engineering of production data to petroleum systems. And we have developed a key performance indicator called MPI, Normalized Production Index. The unit is, standard tank barrel per foot per month. Then you can analyze and screen the performance of each well. Also, we have calculated EUR based on declining curves and to some extent machine learning. Now, we are trying to use this database to study some of the re-stimulation projects that are going on. As you know, re-stimulation is really the name of the game now in shale. Already more than 300 wells have been re-stimulated in Eagle Ford play only. So we are trying to do some numerical simulation of some important problems based on real data, both production as well as geology. So this database is helpful for candidate selection of those wells which are supposed to be or are planned to be re-stimulated. We have published a large number of papers, and our work has been featured in the APG Explorer and other media. So if you are interested in bibliography of our publication, again, please contact Palash or myself or Dr. Dev, and we will send you our publications. Again, I will skip this. This is the workflow. We are trying to add machine learning component to shale characterization. And also we have, we are creating a geological database on almost more than 20,000 wells related to source rocks in the US only. So this is also going to be a huge component of Shale Smart. Now, coming back to our own backyard in Utah, Colorado Plateau, even though it's called Colorado Plateau, but most of the plateau actually is situated in Utah and not in Colorado. So that is where the old or the traditional energy corridor is. Almost all of our oil and gas fields and wells are located on the high plateaus. But the new energy corridor is really being developed in the Great Basin. So we published I would say, popular article about Utah's new energy corridor. It came out actually this month in First Break, publication of the EAGE in Europe. So within a distance of 160 miles or so, you have geothermal fields, solar, wind, hydrogen storage. I do not know of any other place that you would have all these energy transition technologies concentrated in such a small space. For the traditional energy corridor, we are trying to develop what's called the energy superbasin model, an integrated co-production of oil and gas together with other resources, as well as carbon capture. So that's something that EGI is also working on. I think this is my last slide. Thank you very much for your patience and attention. And you can also visit our website for more information. Thank you.
That was fantastic, including the video, but any questions from the audience? If not, Rasoul will be here the rest of the day, so please do reach out to him. They've got some incredible resources that they can share. So we're going to get to the frontier, I think, of the energy transition, the next talk. This is on natural hydrogen or white hydrogen. So we've a tag team presentation with Dr. Setoyama and Dr. Richards are going to tell us a little bit about how do we stay current and one step ahead of white hydrogen. So with that, please join us.
So we started a research on natural hydrogen last year, and we had a presentation in the technical conference. And I had a kind of slide showing the increase in public's interest in natural hydrogen. And that started really at the beginning of last year, 2023, after the publication of an article called Hidden Hydrogen. And I have another slide which shows kind of change in public's interest in natural hydrogen. It shows that our honeymoon period with natural hydrogen is over, but we are in kind of now a stable relationship with natural hydrogen. But the number of papers related to natural hydrogen published per year is increasing, and we can expect more papers coming out because of the new projects started in the last few years. So it's really kind of becoming a challenge to keep up with, with the development in natural hydrogen research. And so what we are doing right now is to gather information and data related to natural hydrogen to understand how natural hydrogen systems work, and so that we can really evaluate its potential and compare the reserves size of different prospects reported in different, by different companies. So I talked about the trend in public's interest in natural hydrogen, and this is where we are. So this data is as of about 2 weeks ago. And as I said, the number of papers related to natural hydrogen published per year is increasing. And we expect more papers coming out because of the new project started in the last few years. But let's start with the definition or defining what we are going to talk about. So natural hydrogen is hydrogen naturally occurring in various environments in different forms. And they are generated through either biotic or abiotic processes without human intervention. So then there are more and more reports of highly concentrated natural hydrogen. And the distribution or the occurrence of natural hydrogen, such natural hydrogen is ubiquitous and it's widely spread. And I believe it's one of the potential advantages of natural hydrogen. Now, this diagram is a little complicated, but what it shows is how to get manufactured hydrogen from primary energy sources and feedstocks, these, using production technologies and mitigation technologies. And what I want to point out is that in this diagram, at each step in the process, carbon footprint, water footprint, mineral requirement, land requirement, and energy loss increase. And the major difference between manufactured hydrogen and geological hydrogen is that natural hydrogen is primary energy source. You don't need to convert natural hydrogen into hydrogen. You can use it as is. Well, you still need to probably separate from other associated gases. But because it's a primary energy source, you can skip all these steps. So there's a chance or that the production of natural hydrogen has smaller environmental footprint, and also we can use it without energy loss. Okay, so because of these, we see many papers or articles on natural hydrogen, and people are excited about, about natural hydrogen because it might be a new, clean energy source with burst potential. And such articles start with the story of discovery of natural hydrogen in Mali because of its exceptionally high hydrogen concentration, but also because it is the only pilot study which did the production of natural hydrogen, electricity generation using natural hydrogen, and they provided electricity to local community. So it's a nice, success story with an explosion with cigarette at the beginning. And there are other interesting facts about this field, and one of them is that there's an indication that the hydrogen is generated dynamically now based on the stable reservoir pressure after several years of production, and also the young age of hydrogen in reservoir. So you've probably seen some articles or people claiming that natural hydrogen is a new renewable energy source. I am not sure if it's really renewable, but I leave it to you to decide. Then, okay, so natural hydrogen seems to be exciting, a new energy source with burst potential. But where was it hiding? Why you are not studying natural hydrogen, right? And you've probably seen such comments before or heard people saying, but even if we limit ourselves to papers or reports written in English, there are reports with natural high concentration of hydrogen in like 30s or 40s. And there's also this article which listed already highly concentrated hydrogen occurrence. And this is my favorite, geothermal hydrogen in 80s, 90s, and early 2000. We had papers basically telling us to wake up and start looking for natural hydrogen. And the original paper on Mali field was published 6 years ago. So I agree with such statements that there was a prejudice that hydrogen cannot be trapped, and we simply ignored natural hydrogen. Much like ultra-deep water systems, we were not looking for petroleum systems on transitional class and oceanic class, and now all the companies are looking for such field. So, and it seems that the Mali field is not a one-off. There are reports of prospects with size similar to that of Mali field. These are here. And there are also studies now showing that hydrogen can be trapped and stored in subsurface. And the example of seals would be like a dolerite seals in Mali, or shale or clay stones in Kansas, or the thick evaporite layers in the Amadeus Basin in Australia. And we, all of us know that there are large sort of structures in both in Texas and Utah, which can serve as a good seed for hydrogen storage. So now you might be wondering the size of these prospects. And if you compare them to oil and gas, they are not massive, they are not gigantic. However, this comparison is also not valid because probably you cannot see, but we do not have a standardized way to do an evaluation of reserve size for natural hydrogen system. So we are not comparing apple to apple. These are all different estimates. And to have such standardized way to evaluate natural hydrogen prospects or fields, we need to understand how natural hydrogen systems work. And that is what we are doing right now. So we are gathering information and data. We are we are collecting the information about the analogs that we could use. We are also collecting information about processes of natural hydrogen systems, and And the goal of this project is to really understand how natural hydrogen systems work, identify the knowledge gaps, and come up with new ideas for research project. So I think we all agree that the basic concepts of petroleum system can be applied to natural hydrogen system. There are source, there are reservoirs, there are cap rocks, and there are processes like generation, expulsion, migration, accumulation. There are also consumption too. But if you compare them closely, then there are many unknown, there are many known differences because hydrogen is more diffusive, it's more reactive, they behave differently, for example, in reservoir. And there are also, we expect more unknown differences that we are not aware of, and also knowledge gaps that we would like to identify as this project progress. So, as part of this project, we are also developing a new method for natural hydrogen exploration. And with this slide, I will.
Awesome, thank you. For those of you that didn't see me wipe out, do not try and climb up here. Please use the stairs, public announcement. Okay, hi, I'm Dr. Bryony Richards. I'm an advanced imaging expert and economic geologist from the University of Utah at EGI. Eiichi and I have been working on natural hydrogen exploration for about a year now. And we found some really exciting ways to not only look for natural hydrogen and assess whether depressions and fairy circles, whichever one you want to call them, I prefer fairy circles, whether they're productive or not, whether they have a life cycle, which we now know they do, and also to try and quantify how much hydrogen is coming out of the seeps using mineral proxy-based hyperspectral imaging. So this shows a little bit of the workflow. Obviously, you need to get the imaging first. You can do that using satellites, which is very nice because it's free public data for the majority of the time. You can use airborne planes, Avaris, the NASA plane is one of those examples, and you can also use drones, which we will be hopefully utilizing next year. After that, there's a fairly simple methodology, and this has been published before. I believe, what was the paper, Eiichi? Can you remember the paper that this comes out of? Or is this is your methodology? This is ours. We've seen some with the sort of reconnaissance characterization, but the idea of putting hyperspectral imaging into this is new. So you might be asking, what is hyperspectral imaging? It is imaging. I'm going to skip to this slide first. It was introduced in the 1990s. You might remember things like the Landsat and ASTER satellites. We're now on Landsat 8. ASTER, the satellite, is kind of defunct. It sort of went out of service in 2008 for some of its bandwidths. You can think of hyperspectral imaging as a continuous rainbow. So you have RGB, that's what we're used to on things like TVs and our cell phones. You can have multispectral imaging, and that goes up to 37 bands of wavelength light. Or in hyperspectral, you can have more than 37 bands, and this is based on the USGS. I often get asked, if it was introduced in the 90s, why are we using it so much now? And my answer to that is computing power. We've only just kind of reached this axis, where you have both the computing power and the data. Then the problem is you need the expertise to read the data. And so you kind of need to be a mineralogist on top of that. So it's a combination of mineralogy, imaging, and computing power. So it's a really difficult trifecta for people to learn. If we use it in terms of a landscape, you can imagine that the satellite is pushing a broom along. That's how we sort of measure the pixels. It's called a push broom sensor. With that, every single pixel Doesn't matter what's on the ground, whether it's a rock, a human, or a cow, it all reflects. And it gives us a very distinct reflection signal, and you can see that there. What we then do is pick out those parts of the spectra that are significant for minerals or snow studies or water studies or whatever you want to do. And if you have enough data, you can start to make incredibly detailed mineralogical maps. The map you see on this is actually Yellowstone. So that is the gram prismatic area. The diameter of the picture is about a mile. So this is, as far as I know, the most detailed geological map of gram prismatic. As I said, we use a variety of different methods, and the really good thing about this is that you need to cross-correlate. With hyperspectral imaging, you need to understand the satellites, you need to understand the spectral properties of the minerals, and you need to cross-correlate to check your work. You need to ground truth. Now, the best ground truthing is obviously going and getting rocks. But as you'll see, a lot of our fairy circles are not in places we can go get samples. So we use multiple methods to cross-check our spectral imaging. And geological maps and things like MINDAT, where rock hounders have picked up rocks. That's also useful. As I said, we can't go to most of places where there are the large fairy circles. And the reason we've chosen these is that there's published data to go with these. So there are hydrogen measurements. And that was obviously very key with looking at hyperspectral and hydrogen. We need to make sure that we can cross-correlate and ground truth. So you've all heard of the Mali depressions. The very large depression from Mali that we'll talk about in a minute was discovered after someone lit a cigarette near the well. Apparently he's still alive, which is good to know. Probably doesn't like natural hydrogen anymore. We're also going to discuss some Russian circles and some Brazilian circles. The reason I include the Russian and the Brazilian so much in presentations is because they're vegetated. Most people who know hyperspectral imaging are terrified of vegetation because obviously it masks any signals that your rocks are trying to show you. This is the Mali circle. And this is personally my favorite because I think the analog is so good. I would prefix this with the data that was taken from Prinshofer in 2008 is actually measurements from 2015. And our spectral data is from a decade later almost. So you're seeing a change in these fairy circles because they evolve. They kind of have a life cycle. And we see that, and we'll show you that in different slides. And they're very dynamic. If we're seeing a change over 10 years in the mineralogical surface changes, which is what we're looking at, then we know that below there is a very dynamic system. As you can see on this slide, our data from our spectral indices, and a spectral indice in this case is the visual representation of the mathematical equations of different spectra. So what we've done is not only use spectra to highlight certain minerals, we've then combined that to make sure that we look at different minerals that are affected by hydrogen. So we have multiple mineral signatures that we're looking at, in addition to a built-in vegetation reduction index. And that works very, very well. You'll see that the peaks correlate very nicely with the data. And the spectral index, where you get highs, you got highs in the Prinshofer paper. So this was the first one we did, and we got really excited. But we needed to try another one. So I like to call this the Barbie figure. It's nice and pink, very pretty. The useful thing scientifically is it shows kind of an active fairy circle and a dying fairy circle. You can see that they look very different spectrally. And that's really important. So the blue one above the active fairy circle is unlikely to have that much hydrogen, or so we think. There are no measurements from the upper circle, so it's quite hard to tell. This spectral index was ridiculously complex, but what it does really well is show extinct fairy circles, and those kind of appear as ghostly white. And so this is very useful for us when we're kind of scanning an area to see the potential, seeing immediately where those trending extinct fairy circles are. We again put our spectral hydrogen alteration index onto this. There's a reason I'm not telling you what it is, and that's because we're about to publish on it. Again, this is a different paper. This is Larin 2015. And you can see again, does the laser pointer? No. You can see again that it picks up the trends of the actual hydrogen measurements within the spectral data. We then went one stage further with this and mineralogically mapped the lower fairy circle. There's also a very good geological sort of story here, and that's another part of the paper. So we can show you the colors, but we can't show you the minerals. If we apply a heat map to that black and white picture, it becomes much easier to see. When I put on the 3 stars, you can see that they're on structural boundaries of the fairy circle. No one really knows what those spectral boundaries represent. We think we know. So that again will be in a publication. It's likely to be subsurface as well. So we think it's both a mineralogical surface change, but also represents something subsurface. The next one is the Brazilian fairy circles. Unfortunately, no transects, but again, we have those very consistent patterns. This also very nicely shows a mega structure, and it shows how our index deals with vegetation, which is that it ignores it, which is what we want. You can see in Brazil, not only does the hyperspectral imaging pick up the fairy circles, but it picks up the larger basinal strike structure. And so this has already helped us to identify tens more of fairy circles in this basin, which is the São Francisco Basin. And I'm going to hand over to Eiichi.
Thank you. So just the final remark, I would say. So the research on natural hydrogen requires people from petroleum science, but also people who knows how to work with hot and hard rocks and how mineral and water reaction works. So I think in this room we have the right mixture of people, so I'm looking forward to have more discussion on natural hydrogen, and hopefully we can come up with nice research ideas. So thank you.
Absolutely fascinating talk. So thank you so much. Really appreciate this sort of exposition on natural hydrogen. We might have time for one very, very quick question. Christine.
Yeah, I hope this is an okay question, but the list that you showed and what you're telling us here, are any of these incidences of actually seeing the subsurface hydrogen on purpose, or are they all, you were looking at something else and wow, it's hydrogen?
So Mari's case is accidental. But there are like 30 or 40 exploration companies now doing active exploration. And yes, many of them found actually reviewing the old well reports. But they are kind of intentional. The activity was intentional. So yes, exploration is, I think, possible.
Thank you. You understood my question.
Thanks so much. So we're going to switch over to the next conversation here. I know that there's a ton of questions that people have for the natural hydrogen story. Lots of mysteries already. Hopefully by the time I finish talking, they'll switch computers and I'll get a chance to introduce our next speaker. Our next speaker is from the Earth and Atmospheric Sciences Department here at the University of Houston. perhaps one of the most dynamic faculty, young faculty here at the university, Yingcai Zheng. Yingcai is going to talk to us a little bit about seismic data and the quest for fracture permeability. He's doing some amazing work, not only in oil and gas, but also geothermal, as well as in CCUS. So with that, Yingcai, you want to handheld mic, you can do that, or whichever way you want.
Hello? Too close. Everybody, so my name is Yingcai Zheng. I'm a professor at the Earth Science Department. I'm also director of Rock Physics Lab. So today I'm going to share with you some technical progresses we have, because I believe eventually we depend on the breakthroughs and the progress in technology. So with Utah colleagues, actually we have many years of collaboration already, and I hope we will have more collaboration in the following years. So these are 4 papers we published in the last 4 years with Utah Forge people, Joe Moore, Clay Jones, and Phil Wanamaker. So this is this year's paper about seismic anisotropy of granite rocks from the stimulation well at Utah Forge. I'm going to talk about the main findings in this paper. We have another paper, also EGS, Utah Forge, about using the shear wave splitting to measure the anisotropy in the reservoir. And this one is using the Utah Forge DAS data. We found some very interesting observations. I'm not going to talk about the findings here in this paper. That's a previous work about elastic waveform inversion at Raft River geothermal field. So this is my group. We have about more than 10 people, like 12 or 13 people. Most of them are students. Also, they are young students. The oldest student is third year, so fourth year. So also we have very active collaboration with research professors. I'm really happy to see that DOE, NSF, and some companies recognize the value of our work, so they provide the financial support. So what do we do here? So we focus on geothermal fields. Some of the technology actually is, can be used in CCS too. So as we know, the heat, fluid, permeability are the 3 very important elements in geothermal fields. And the permeability largely provided by fractures. So our research is centered on fractures. So we worked on both hydrogeothermal and EGS, and also rock physics. So in the hydrogeothermal, you don't see a pointer, okay. Oh, here, okay. So the challenges we try to solve is find new heat sources in the hidden geothermal systems. Jim Fald's group, they published some papers. They said more than half of the geothermal resources are hidden, which means no surface expressions. So how to find those hidden resources is a challenge. Second one is we want to also find a nearby hot resource for existing power facilities. For example, in Nevada, some places the geothermal power plant have been operating for decades and the temperature is going down. So they need to find a new wells to drill to extend the lifespan of existing facility. So in this domain of research, our work is focused on imaging fractures and infer permeability using seismic data. So this seismic data include the surface seismic data and also subsurface seismic data. The other one is EGS, Enhanced Geothermal System. This is about emerging or future technology So we focus on a new phenomenon discovered in my lab, which is called the pressure surge effect of fluid field fractures. So what it says is a fluid field fracture can act as a pressure amplifier in the subsurface around the fracture. So if you can locally enhance the pressure, you can develop a pressure gradient which can drive the fluid to flow. And this phenomenon can also be used to control fracture growth and stimulate permeability. Okay, this is about some future technology. And in rock physics, we do lab experiments. We measure the response of the rocks at different frequencies and also at the different pore pressures. So all this work, we focus on the value of seismic signals because a lot of the geothermal depend on EM and other type of technology. Not much about seismic. Seismic is usually used to monitor the reservoirs. So here I want to emphasize that using seismic, we can delineate the fracture network also to control the fracture under the subsurface fluid. So first part is hydrogeothermal. Jim Fald's group laid out some geological settings for exploring geothermal resources. Mainly these places you have extensional tectonics, so which means you can open fractures. The fluid can flow through the fracture. So our work is using the seismic. This time is the surface seismic. We can find the larger scale faults and the small scale fractures. Even in the Utah fault cores, we see a lot of small scale fractures in the cores. And then we can find the faults using AI, machine learning, and the small scale fractures. Those are like 10 meters in scale, orientation, density, compliance. You can optimize your reservoir for energy production. So everything is rests upon what is a fracture. A fracture is a broken surface, maybe with a certain width. We use this compliance model. So basically, you apply a pressure across the fault, across the fracture plane. You can increase the width of the fracture or the aperture of fracture a little bit, which is d meters over the applied pressure. You get a displacement over applied stress, which you get meter per Pascal. So this number, this ratio is called the fracture compliance. And we found that when the fracture compliance is large, so which means you can easily open close the fracture, you can see large seismic wave scattering coefficient of the fracture. On the other hand, researchers at Purdue University, they found this graph, so which means if you increase fracture compliance to the left, because originally they used the stiffness, which is inverse of fracture compliance on the x-axis. So if you increase fracture compliance, the flow rate increases. So basically it means compliant fracture, more flow. Previous slide, I showed that compliant fracture, more seismic scattering. So this provides a link to use seismic data to probe or infer fracture compliance, therefore the flow. Okay. Using seismic data to get the fracture distribution in the subsurface, we partition the reservoir into grid, essentially boxes. For each box, it may or may not have fractures, but we can shoot a directional beam. It's like a laser beam down to bombard this fracture unit. So the wave will interact with the fractures, create interference pattern observed at the surface. So basically, we just need to map this observed interference pattern to the subsurface fracture network geometry. And this can be done using a neural network. This is nothing magic. Even without it, we can do it. But with it, it's just more convenient using the already large amount of infrastructure in the AI community. So basically, we take the interference pattern at the surface, we produce the subsurface fracture distribution. We applied this in Soda Lake. For people who work in the geothermal, you know this field. It's been operating more than 40 years. And this is the surface seismic source receiver distribution. It's about 6 kilometers, more than 500,000 seismograms. So here is the model. So in the subsurface, there's a basaltic body, extrusive basaltic body. And there are two exploration targets above the basaltic body and below the basaltic body. So above the basalt, we found that there are 4 regions with very large compliance values. So which is this spot, this spot, this spot, and that spot. So this is about 250 meter depth. And we can slice down, we can move down to a deeper depth, 300 meters. We can still see this spot persists. And then we presented this data to our findings to the company. And we were told, oh, there is a steam cap in this P0 region. And now they are trying to drill well around here. And this steam cap was confirmed by our previous drilling. Okay, so that's a small scale fractures around a 10 meter scale. We have a new technology to delineate them, and this one is about larger scale faults. In the afternoon, you will see a poster, Joe McNeese poster about this. The second one is a new phenomenon called the pressure surge phenomenon for fluid field fracture. The first paper published 2017. The objective of this newly observed phenomenon we want to do is we want to create a localized pressure amplification which develops a pressure gradient which can drive fluid flow in the subsurface. So this everything is remote. So the second one is we want to use this phenomenon to control fracture growth. So you can frac the EGS reservoir, but in the meantime, you can control the fracture length and the width. So the idea is here's a rock, here's a fracture, and there's some fluid here. So if you perturb the fluid pressure at point A, what is the pressure at point B inside the fracture? The Pascal principle says they are equal. So if you have changed the pressure by 1 Pascal here is going to be 1 Pascal. But Pascal principle is a static principle. But when you have dynamic phenomena involved, so which means if you perturb the pressure at a certain frequency, and if you measure the pressure change here, you can actually get a very large amplitude. And this is called the pressure amplification effect. And I can take the ratio of the amplitude of the pressure inside the fracture and the stimulant pressure outside the fracture, define an amplification factor. We published this theoretical paper in 2017. Then later we did the experiment at UH-AGL facility. So basically we found there is a 25.2 times amplification. So this is very exciting because in theory we should be able to achieve amplification factor of more than 800 times. So basically it's like a lever rule. So you can have a very small perturbation but can achieve a very large pressure change inside the fracture. Here shows some pictures about the setup. And here, because the fracture is very thin, we have to make a very small sensor to measure the pressure change. So we made a sensor which is 0.2 millimeter thick. So we can directly put the sensor inside the fracture to measure the pressure during the wave propagation. Third part is rock physics. How am I doing on time? 2 minutes. 2 minutes, okay, good. Third part is rock physics on Utah Fault core sample. So with Clay Jones and Joe Moore, we got the rock core samples last year, September. They performed a lot of characterization work on the rock, including CT scan, mineral analysis. We found microcracks in the granite. And then we performed in our lab anisotropy measurement. We found if you increase fluid injection, if you start to inject fluid, the pore pressure will increase. Increase the pore pressure can increase seismic anisotropy more than 20% in both P wave and S wave. So this really provides some guidance on how to conduct seismic monitoring to track where the fluids are in the subsurface, because you can observe the anisotropy. This is a course we got from Utah. Here's the reservoir. I'm sure you will see this picture more later. And here the workflow, we did the sample preparation, mineralogy, ultrasonic measurement, fracture analysis. Okay. And then we conduct anisotropy measurement using our equipment. We conduct 1 megahertz anisotropy, ultrasonic wave measurement. This is the main result. So if you increase confining pressure, or basically if you move to the left, it's going to be increased pore pressure. The anisotropy will increase. So you can see a very nice line. This is a 5 megapascal. The right side is a 50 megapascal. So the P wave anisotropy, 23%. So this is very, very strong, and which is good because that it means we can detect it. To summarize, fractures are very important in geothermal fields, and they're also important in CCS. Actually, I have another DOE project working on site selection for gigaton storage. Basically, we detect faults and the fractures. And we have a novel method to image faults and the fractures in geothermal fields. We also applied to the Salt Lake geothermal field. And in rock physics work in granite, we found injection for fluids can increase pore pressure, can increase anisotropy. And this anisotropy is very strong, more than 20%. The other thing is we're working on another paper. So because we did a mineralogy analysis, we found only using the mineral composition, we cannot explain the measured anisotropy. So that means the fractures must play a role. So we have done the work in the process of submitting the paper. And finally, pressure surge phenomenon. This is really an ongoing and future research topic. The goal is to show that how we can activate local pressure gradient to drive fluid flow through the subsurface. So this is really engineering the fluid flow in the subsurface. And we also want to use this effect to control not only fluid flow, but the actual fracturing process and the growth pattern of the fractures. So thank you very much.
Thanks so much, Yingcai. So as we get ready for the next talk, if there's Brian come up, there's a quick question for Yingcai. We might have time to have that answered. Well, we're going to switch gears from seismic to something that's pretty comprehensive. And Brian McPherson from the University of Utah is going to talk to us about CCUS, 45Q, MRVs, and the whole value chain. So looking forward to that.
Thank you so much. Yes, my name is Brian McPherson with EGI. I've been with EGI since 2006, and then prior to being at EGI, I was at New Mexico for 10 years. Started working on carbon capture and storage in 1997. So I'm really pleased to be here, very grateful to have finally met Ganesh. He is a living legend of CCS, and so looking forward to our session, our panel tomorrow, because we will discuss how this scenario of the energy transition being facilitated in part by carbon neutrality, there's still some challenges that lie ahead. But EOR plays a critical part in that, and I think that will become very clear. It's already very clear, but we'll discuss it in great detail tomorrow. So I want to talk about the value chain, especially with respect to 45Q. It's really been a game changer for CCS. In 1997, I gave some of the same elements in talks that I will present today, and some things have not changed, but others have changed dramatically over the last almost 3 decades. I want to acknowledge EGI especially, but the Utah Science, Technology, and Research Initiative, which has funded a great deal of the local work at EGI, the U.S. Department of Energy, all the results, and the 30, 50 papers that we've published on this work, funded by the National Energy Technology Laboratory. Always must acknowledge their role in the work. And then lastly, but most importantly, the scholars who have worked on this at EGI with the team for decades. It's truly right now, I've said to Milind many times that this is the best group that we've worked with all along. And like I said, I've been doing this a long time. Just a fantastic group of people. So the motivation, really what it comes down to, OMB and others are updating these graphics in real time, but as oil price increases, the oil produced and carbon dioxide stored increases. Okay, they're tied together, inextricably tied together, coupled, cannot get around that at this time. At $75 per barrel and $30 per ton CO2, 7.5 BTSB is produced, 2.4 gigatons CO2 in a reservoir, for example. The U.S. consumes about 6 BTSB per year and produces about 4.5 and emits 3.5 gigatons per year from electricity generation and industrial sources. So it's a pretty convoluted picture, and the timing, the responses of the system are not immediate, okay? Sometimes the feedback comes much later. But then the net conclusion, the net point that we want to draw from this is as oil price increases, CO2 storage increases. As CO2 price decreases, oil produced and CO2 stored increase. It's just, it's a straightforward system, but also really complex and very sensitive. Right. Also, this is from 6 years ago, the IPCC report 2018 on 1.5 degree warming. This presentation will be archived and available, nothing proprietary in here. But I urge you, if you've not looked at this report lately, or if you've not looked at it at all, download it, read through it. It's an eye-opener. It's kind of disturbing in a way, but it's very helpful for providing the context for how climate, well, just check out the report. Overshoot is a likely, overshoot meaning that exceeding 1.5 degrees Celsius warming is a distinct possibility. In fact, it's almost impossible to ignore or avoid, rather. We'll need at least, I mean, almost a 10% increase in carbon intensity is needed to bring the curves, the warming curves down, okay? These are model predictions. That means a removal of 1,000 to 2,000 gigatons of CO2. We're too late to stop the 1.5. We will overshoot, but we can by 2050, as Ganesh mentioned earlier, we can reach that 1.5. It is possible, but it's a delicately balanced system, so. All right. Global strategies require sound and effective regional strategies. The national goals, of course, are rapid, and global goals, rapid transition to carbon neutral energy economies. Capturing CO2 is essential with rapid deployment of renewables, so that transition that we've been talking about this morning. And in my opinion, and every time I say this, I see lots of heads shaking in the room. Some people disagree, some people disagree. Mixed agreements on this. Coupling commercial scale storage to direct air capture is essential. My opinion only. But it's, again, it's to get 1,000 to 2,000 gigatons removal, it's, DAC, I think, is essential. And we've got some good news in that regard, but we also have some bad news, that being that the cost of DAC is still very high. Over $500 to $600 per ton, even more, depending on the technology. Economies of scale will drive that down. It is possible, but it's just not immediate. Again, much of the feedback into the cycle happens later on. So, and I've been, like I said, I've been talking about this for almost 30 years now, and it's this entire objective moves very slowly, which is okay, because we are making progress, though, as a community. All right, some previous projects based at in the Utah, New Mexico, Four Corner states. These are completed projects and ongoing projects. Over $90 million of federal funding. Actually, it's over $90 million of federal funding into these 4 projects that I'll summarize here. First, in southern Utah, the Aneth enhanced oil recovery and sequestration. Note that these are all hydrocarbon tied. So in enhanced oil recovery, the project began injecting in 2007 and officially over 3,000. This is the Southwest Regional Partnership on Carbon Sequestration, which I took sabbatical from New Mexico Tech at EGI in 2002, wrote a proposal for the Southwest Regional Partnership. That project just ended officially 2 months ago. So it went on for 22 years. And as part of that project, we completed completed injection of about 300,000 tons CO2 with enhanced oil recovery. Some terrific, the H index of these combined projects is about 30. It's an incredible project, incredible data set, terabytes of data that are available. I can't get excited enough about it because it's just, well, you work on something for 25 years and that's what happens. But it's especially induced seismicity. We had put in passive seismic monitoring at this site to capture CO2 seismic energy from the Paradox Valley in Colorado, but that was swamped by the local energy induced by water injection. So it was saltwater disposal that caused the induced events, dozens of induced events every day, less than magnitude 1, between -1 and +1, but still, nevertheless, it helped us identify previously unimaged faults, two major faults in the site. So it became a characterization tool. Induced seismicity as a characterization tool. Who would have thought of that? Another test was the San Juan Basin in northern New Mexico, Enhanced Coal Bed and Methane Project. We purchased for $5 per ton in 2006, 75,000 tons of CO2. We only managed to get in just under 18,500 tons because coal swelling just overwhelmed, closed up the cleats and the permeability. We calculated, it was actually Norm Rapinski, who was at Sandia at the time, now is still active at Pinnacle Technologies in Dallas. Norm calculated that swelling wouldn't start becoming significant until 75,000 tons. But the San Juan Basin coals are relatively dry compared to other coal bed methane fields, and so we just didn't think that the swelling would be that severe, but it was. But still, 18,400 tons is still one of the larger ECBM projects on record with the data collected that we had. And then thirdly, the project that Ganesh mentioned began in 1972. He was working on it, studying it back then. It's the hallmark CO2 EOR project. Just the Permian Basin, we conducted successful 4D seismic imaging, VSP, over 350,000 tons per year injection rate. So you do the math, there's over 30 million tons of CO2 coming from, and again, Ganesh mentioned it's anthropogenic CO2, it's natural CO2 actually, from the McElmo Dome in southern Colorado. 30 million tons per year piped from Colorado to Texas for this and other fields. And we were fortunate enough that Kinder Morgan at the time was very amenable to us coming in and monitoring the daylights out of it. Really successful project. We are still studying those data, collecting those data, and still working on that project. We transitioned to northern Texas and the Farnsworth Enhanced Oil Recovery Project. That began injection of CO2 in 2002, and it's still ongoing. And to date, there's over 1 million tons stored, well over 1 million tons injected, but over 1 million tons net storage in that project so far. And again, that we managed, because of the data and the great outcomes of this project, we managed to extend this project a lot of years beyond its original life. It just ended in 2020, officially 2 months ago, end of July. So great stuff. Some big picture lessons learned from these oil and gas fields. I say can play an important role. I think it's the important role. The limitation comes in Class 6 versus Class 2 UIC permits. Class 2 permits, the binder that describes the requirements for Class 2 is huge, but it's mature and can be achieved in a month, couple months, if needed. Class 6, though, looking at several years to permit a project, even with state primacy. So it's a very difficult achievement, and if only we could create a hybrid Class 2, Class 6 transitional permit, because EOR plays such a huge role in facilitating deep saline sequestration and storage of CO2 underneath those oil fields. There's almost always deep saline reservoirs available. Great way to tackle this. In all cases, difficult to predict geomechanical processes. In all cases, difficult to predict induced or triggered seismicity. Tracers and passive seismic monitoring are particularly cost effective. In fact, the team's most impressive work has come out of the tracers and the seismic monitoring work. Just incredible data sets. Now, I want to talk about EGI and its evolving, what's turning into a carbon management hub overall. Uinta Basin Carbon Safe Project begun less than a year ago. Rocky Mountain Carbon Safe Project just awarded last Friday. Red Rock Stack Hub with Fervo Energy, that was awarded last year. Just finishing negotiation. Basin and Range Carbon Safe Project, that was awarded last Friday. And the Southwest Regional DAC Hub, led by ASU, awarded last year and just completing negotiation now. All of these projects getting underway, getting traction in 2024, right now. It's a really exciting time. I'll talk about the funding of each of these and the interplay of that with 45Q tax credits. So I wanted to outline 45Q quickly. I think how am I doing on time? 5 minutes?
4 minutes.
4 minutes, okay. I will be quick. I'm going to jump to the punchline then. And Catch Act, IRA Inflation Reduction Act, it is extended. So 45Q begun a long time ago under the Trump administration, 2018, signed and then further expanded in the Inflation Reduction Act to 2033, and then also increasing, I'm going to get right up here, $60 per ton. It was $35 per ton for enhanced oil recovery, now $60. Originally $50 per ton in deep saline, now $85. Originally DAC fell under other categories, but now under the Inflation Reduction Act, $180 per ton. Great news, right? But for DAC in particular, the cost of DAC is still over $500 per ton. So $180 per ton is great, but it's still the feasibility, the practical application is still a little uncertain, let me put it that way. The new federal grants, over $26 million for DAC, almost $40 million in the new carbon safe projects. This is great stuff. This is really new. It's the new SWP. It's the Southwest Partnership. It's the new carbon hub. And Utah is doing some great stuff. But it all is predicated on 45Q. Because, again, $60 to $85 per ton, depending on whether or not EOR is utilized or not in deep saline. Likewise, Rocky Mountain Carbon Safe, it's going to be $85 per ton at most. Red Rock's, the Fervo DAC Hub, $180. The Southwest Regional DAC Hub, $180 per ton. But again, it depends on the sources, because the capital investment for retrofitting those power plants, the potential sources, and or the Rocky Mountain Carbon Safe actually offers a clean source of CO2. It's only about 70,000 tons per year, but it's still clean in the form of coal bed methane gas stripping. And then likewise, the Utah Iron DRI, that's a almost necessarily clean source of CO2, pure source of CO2, source of pure CO2. So looking great, but at the same time, it's the economics. That's what I want to set the stage for tomorrow. EOR, 45Q, and the economics with respect to moving forward in CCS. That session is at 10:45 a.m. tomorrow. Again, Ganesh and I are honored to moderate that session with you tomorrow. It'll just be terrific, but I want to discuss and leave it with, the economics, motivation of economics, the timing. Will 45Q knock CCS out of the park, and what's the role of direct air capture and all of that? So I think I have a minute left for questions, so leave it at that.
He can talk fast, can't he? Questions for Brian? Go ahead. So this is the Parish Power Plant, which had the first large-scale carbon capture as part of the ARA, 2008, 2009. Chuck McConnell was one of the people who got that funded and made that happen. It was a joint with Nippon. Mitsubishi had done this with NRG, and after operating for 5 years, they had to shut down when we hit the pandemic. So. It's come back up because it's gone into a new companies, but it's had hiccups. So
it's I liken that to, I compare it to the ADM project, which some of you may have seen the headlines in the past couple of days about the ADM project leaking. That's the storage project in Illinois. So the question becomes, what's the duration of the shutdown for capture? Does do the tax credits, if they end up driving it, how are those managed? The implications, this won't happen. None of this will happen without economic motivation. If you're given a tax rebate, are you going to reinvest that money in a interest-bearing account, or are you going to buy a new computer? I mean, it's we have to think about the motivation of the project, and the economics are a part of that. Likewise, leakage, we don't even know the rate of leakage from the ADM project. Yep. So I'm trying to say it ultimately comes back to the economics is my response. And
just to sort of give you a quick insight into that particular facility never used the 45Q credits that were available. They were subsidized for the front end, but never used the 45Q stuff.
Yeah.
So with that, I'm going to move on just so that we can keep on time, or at least close to time. We're not on time. I'm just trying to make sure we don't go too far off time. So it's my pleasure to introduce Christine Economides. Christine is another rock star from U of H. She cut her teeth, and her experiences have all been with subsurface reservoir engineering, well stimulation, and the work there. Today she's going to tell us something different. She's going to talk about methane and the use of methane to drive the transportation revolution of the future. So with that, Christine.
Yeah, could you advance? Okay, so I'm going to start with my title slide for a minute. Some of you may recognize the language on here if you supplied a concept paper to ARPA-E, because they were asking about intermodal energy superhighway. And I did submit a concept paper knowing it would be rejected. It was. I think there are a couple reasons why it had to be, it was basically non-compliant. First of all, what I proposed and what I will describe to you right now, its technical readiness level is 9. I think ARPA-E's interested in TRL 3, you know? So that's one reason. The other thing is, it's fashionable to talk about energy expansion. I'm going to talk to you about energy transition, I think. So it's not new energy, it's just using our existing energy and our infrastructure in a profitable way. So I want everyone in the room to do this with me. I want you to put your hand like this and put it towards the screen. Do I see you doing that? Okay. So my blue fingernails are either Halloween or political. You take your choice. Keep it there. Keep it there. Okay, now let's advance the screen and see what you are doing. See, I want you to remember what you do right now, because the palm of your hand is energy infrastructure in Texas, and your fingers are expanding out over the entire country. And what are we looking at? Methane infrastructure. We call it the natural gas pipeline system, but it's pipelining methane. Okay, now, what else is on there? You can see the dots that have to do with the storage. So a while back, I did also propose to DOE about using that methane system to blend with hydrogen. But I want to dispense with that idea today, because that's not the way I think about it today, because we can best use those pipelines to transport methane. You transport more energy with methane than blending in hydrogen. So if you want to get into the hydrogen business, your best bet is to generate your hydrogen near the market. So don't pipeline it all over the country, generate it near your market. Let's go to the next slide, please. This is looking at natural gas fields, and this map actually is focused on conventional. So it's missing natural gas that comes with oil, perhaps. We have a lot of associated natural gas. And I think it may also be missing the unconventional natural gas. So it's even more than what you see here. And this is already telling you we're not running out of natural gas anytime soon. I so fear I'm going to forget to mention this. So Paulo, if you will please stand and turn around so they can see you. He has a poster with more details about what I'm speaking today. So look for that later today. Next slide, please. All right, so here I want to just explain something to you, why what I'm saying might make a lot of sense. So first of all, we look at greenhouse gas emissions on the left by the gas. And so carbon dioxide dominates our greenhouse gas emissions. Then if we look at it by sector, we can see that the pale blue there, transportation, is a major factor in these greenhouse gas emissions. These are combustion emissions from our gasoline and diesel vehicles. And then if we look on the right, we see something else. That the pale blue is light-duty vehicles. So that's what we drive. That's our sedans, our SUVs, that's our vehicles. So DOE so far has been emphasizing, if we're going to talk about hydrogen to fuel vehicles, emphasizing medium and heavy duty, not light duty. But if you look at these pictures, you see why light duty deserves attention. Because light duty vehicles represent 20% of US CO2 emissions. So if we make low carbon intensity hydrogen for refueling of fuel cell electric vehicles, FCEVs, we can significantly lower CO2 emissions in the United States. Shifting from coal-fired electricity to natural gas-fired, 9% of CO2 emissions in the United States have been, that's the reduction that we have seen because of that shift. Looking at light duty, 20%, bigger than coal to natural gas in power generation. So we're not talking about a small target here. Okay, next slide. All right, so now I want your help again. We did this, and thank you very much. Does anyone here drive a battery electric vehicle, a BEV? Okay, we have a few people that do. So, may I ask you, how long does your charging take compared to use of the charge? Mm-hmm. I'm not asking you your range, but I'll answer the question because maybe it wasn't clear. And the thing is, I drove Tesla for 10 years. So top that in this room. I had a Roadster. I have done the EV thing, and I loved it. And I will tell you this, don't go test drive a Tesla unless you want to buy one, because you're very likely to step out of there saying, I gotta have this. They're so fun. But they're fun if you have your own garage to charge them in. And the reason she doesn't know the answer to the question is because she probably does have her own garage to charge them in. But if you live in a high-rise, which is what happened to me, I moved to a high-rise. Now I had to charge on public charger, and if I didn't go get my car as soon as it was fully charged, I kept paying. So couldn't leave it overnight, or I'm going to pay double. And I was suddenly acutely aware of what it does cost, which is virtually nothing. If you're charging in your garage, you don't even recognize that you have an EV. It is so low what you pay to charge a BEV. EVs are wonderful. EVs have virtually no maintenance to do. The only thing you have to do is replace your tires and actually the 12-volt battery. Can you believe that? There's a 12-volt battery in a Tesla, and you have to replace it. So fuel cells are also, FCEVs are also EVs, which means they will have these same advantages. But how long will it take you to refuel them? 5 minutes. So the Californians have demonstrated this for us, which is why everything I'm talking about is TRL 9. We already know everything I'm talking about today can be done. So if we use, which Californians don't, but if we use low carbon intensity hydrogen to refuel the vehicles, you are now lower carbon intensity than the battery electric vehicles, because the BEVs are using the grid, and the grid's not green. One day, maybe, but not today. Not today. So they charge faster, they have low maintenance, and that's compared to the internal combustion engine vehicles that everybody else in the room is driving. Let's go to one more slide. So this is kind of the punchline of this short presentation. It's a really messy graphic, I get it, but let me try to help you. So we already see, we can see the pipelines on there, that we looked at that before, and we can see some kind of greenish bluish blobs also shown on there. What are those? Those are identified pore space for CO2 storage. So what we have observed is that something like 94% of the locations in the United States are within 100 miles of an existing methane pipeline. So connect up to the pipeline and generate hydrogen. How? Well, it could be steam methane reforming. So steam methane reforming does produce CO2. Fine. Capture it and store it in the pore space. So what these dots are showing is the ratio between the cost, estimated cost of hydrogen refueling compared to the the known cost of gasoline or diesel at those locations. And the dots are a 40,000 square mile or square kilometer spacing. Why? Because we looked at trucking hydrogen from a hydrogen hub to a refueling station, and as long as you stay within 100 kilometers, it's comparable to pipelining. It's economically feasible. Now, I will specify those are the modern ton hydrogen carrier trucks, not 300 kilos. All right, so we've put our grid there. Those are potential hydrogen hubs, not 7 like DOE does, but around 300. So if you see green colors, estimates are that hydrogen is cheaper than gasoline there. Where you see yellow, look at that, it's unfortunately middle America. Hydrogen would be more expensive. Possibly the reason for that is that the gasoline is cheaper there. I'm not sure exactly. We have to look at the details in the models. The models we're using are national lab models. They're not cobbled up stuff that academics do. We're using national lab models. So this is a very interesting prospect, potentially. And the thing is, for the greater Houston area, we estimate that you can provide blue hydrogen in repurposed land where you take an existing gasoline station and make it a hydrogen station. You can do all this profitably and without the incentives. If you add the incentives that we're talking about, 45Q or 45V, even better, it is really potentially profitable. So that's my story, and we have, I think, time for questions. So if we'll go to the next slide, I think it just says, let's talk. So tell me, where's the flaw? If you tell me a real good flaw, I might be able to retire. But otherwise, let's talk about this. Yeah, go ahead.
So you do have to consider the cost of CO2 capture and storage.
Yes. Yes, absolutely. The map is including that. And if we stay with gray hydrogen, the CO2 reduction is still 2/3 of what you get to blue. So if you just use gray hydrogen like they do in California, it's already beneficial, hugely beneficial. You don't have to worry about the CO2 storage. But the map was SMR plus carbon capture and storage. Thank you for the question.
There's one question in the back. Go ahead.
I think you partly said why. Because the comparison I made was between hydrogen and liquid fuels, like gasoline and diesel. But you're bringing up the comparison between hydrogen EVs and BEVs. So I have to be upfront with you. BEVs are less. They cost less. The vehicles themselves are probably comparable in price, but the refueling cost for electricity at the moment is ridiculously cheap. It's like free. Hydrogen would not be free, but if it's comparable to gasoline and diesel, then it looks to be potentially attractive. So the belief currently is you can switch everybody to EVs. And now that I live in a high rise and I look at my neighborhood, at the people that are parking on the street, they don't have an assigned parking spot, which at least in the high rise I did have, but it wasn't powered. So I had to park somewhere else to go charge. I just don't think BEVs are going to cover all the needs. And I do think that hydrogen is the potential mechanism to enable a shift away from the combustion required for our current transportation habits. Does that help?
Well, thanks so much, Christine. If anybody's interested, UH Energy has published a white paper based on Christine's work. We'll be happy to get you copies of it, or you can find it on the website. Just let us know. We'll be happy to engage and get more conversation going. So Christine, thank you so much for that presentation. So the next presentation is from the chair of the Petroleum Engineering Department here at the University of Houston, Dimitrios Hatzignatiou, and he's going to talk about, and as you can tell, he's got a lot of Norwegian blood in him, right? No, but he did spend a lot of his career prior to coming to the University of Houston in Norway, and has worked pretty significantly in many of the fields in the North Sea. And today he's going to tell us a little bit about CO2 storage in gas fields and blue hydrogen generation. So with that, Dimitri.
It's a little bit strange to hold this microphone, so I'm going to try to use the podium. Good morning. I hope everybody is enjoying the presentations and having a good time. We'll start talking a little bit about CO2 sequestration in gas fields. And why gas fields? It's one of the main subsurface formations we can actually plan it to store CO2. The others being aquifers, and of course the third one being depleted oil fields. And when we talk about the gas fields can be old fields that have been produced. Some of them are about to be abandoned. Some of them have been abandoned several years. And we have new fields as well, of course. They're about to be produced, but also we have some other ones we are actually getting produced as we speak. So let's throw some equations here because we're engineers, I hope, or some of us geoscientists, but I think engineers love equations. All of us have seen some of this stuff, but I'm going to go rather quickly. So when we're talking about CO2 sequestration, we like to associate this with amount of gas produced. So typically speaking, as reservoir engineers, what we like to say is that the amount of gas recovered, this RF, the recovery factor, what we call, is a function of the initial pressure and the bottom pressure, PA, divided, of course, by the corresponding gas compressibility factors. So this is when we have no aquifer underlying the gas field. If we do, then the equations become a little more complicated. This is from Agrawal back in 1965. And it shows that it's kind of similar equation. Again, the ratio is the gas produced at the abandonment conditions when you have water drive. WD means water drive. And then we see we have some more terms here, which is the residual gas saturation, what do we call, the initial gas saturation, and also is the amount of water that encroached into gas fields. Because when we produce these gas fields, the water is going to start moving into the gas formation zone, and then we'll trap some part of this gas. At the end of the day, this is a very kind of quick summary of what actually we're looking at. We'll plot in P versus Z, P over Z, plotted versus the gas produced. And what do we see? We have a what we call volumetric reservoir. That means no aquifer. We're going to get a straight line. There it is. And depending on what pressure will end up being our abandonment pressure, that will be the amount of gas we produce. Now, when we have an aquifer underneath, that will create the pressure support, and the graph is going to look like this. It's going to curve. It's not going to be any more straight line, which means basically that there's a different mechanism for producing this gas. So while this stuff here, at the end of the day, we'll know these things, is because we need to talk about whether we're going to store CO2 in depleted gas fields or in new fields. So we like to maximize the amount of gas produced, but also we need to maximize how much of CO2 we store at the end of the day. So what is the advantages to store CO2 in a depleted gas field? First of all, we know quite well how much volume of CO2 we'll put there. We know how much gas we produce. We know how much we'll inject, practically. It is a proven ability of the capro will prevent the CO2 to escape, so that's very good. The trap is there. There is abundance of knowledge, data, and of course, infrastructure as well, that we can actually be utilized when we go from the production phase to the storage phase. Now, there is some issues with regards who is going to be produce the gas field, who is going to store the CO2. If the companies are the same, that's the best situation. Sometimes they're not. Sometimes if their fields are very, very old, then somebody else will step in and store the CO2 in the previously produced gas field. And so therefore, there may be some kind of difficulties of getting this data, and some knowledge is going to be lost. There is also the good thing is that the decommission cost has been delayed if we're going to store this in depleted gas fields. The other thing is that because it's very good, because we're going to have wells, we're going to have some infrastructure. So hopefully, if we're going transitionally very nicely, production to CO2 storage, then you can utilize this. But at the same time, we have several wells. Some of them are plug and abandoned. Some of them are old wells. Some of them, produce water, so they've been shut down and so on. So we don't know really the quality of the wells there. So this is something that we've really been very, very careful about that. And of course, there is an issue with regards to the mineral rights. Who is owing the gas that will be produced when you start injecting CO2? Because actually the CO2 is going to displace some of the gas. You can actually produce that gas. Well, if you don't want to produce the gas, you just shut the wells and just basically inject CO2. The mineral rights is not as important, of course, when you have the CO2 EUR issues. So this is what actually happens in depleted gas fields. Now let's look at the new fields or fields who are actually under production today. So can we do something different, perhaps? And what's the differences with regards to how much CO2 we can actually store there? Well, there is something we can actually propose in here is to generate blue hydrogen, utilize the natural gas, instead of just transporting the natural gas, sell the natural gas, and of course use the natural gas, and of course emitting the CO2, we're proposing actually to use an SMR process to actually convert the produced natural gas to hydrogen. And of course here there are the three types of hydrogen production. Is gray hydrogen if, of course, we don't capture CO2, we emit the CO2 in the atmosphere. We have the blue hydrogen, and this is the one we are proposing. We produce the natural gas, we convert it to hydrogen, we capture the CO2, and we store it back at underground conditions. And the third one, of course, we're not going to talk much about, this is way far down, is 2030, and even perhaps later, is the green hydrogen. We utilize, of course, the renewables. All these processes here require, of course, heat. What we're proposing is we can actually use the hydrogen generated from this process to generate the heat, so actually we can reduce the carbon footprint. So by injecting CO2 in the same reservoir we're producing the natural gas, what we'll see will enhance the gas recovery as well. And that is very, very good. So we're using one formation, we're producing the natural gas, and the same formation, we inject the CO2, we capture through the SMR process. So this is kind of what we're actually proposing here. You see here the results are astonishing. So here is some of things that we're proposing. Again, the process will apply to new and produce a gas field. We generate the hydrogen. It can be either in situ, or you can transport this, if you like, Dr. Economides, by the way, mentioned exactly that. We transport this natural gas, we generate hydrogen and capture the CO2 and move it back. Okay, this is a little bit more complicated. But best way is to generate, of course, hydrogen in situ, and generate, of course, they capture the CO2 in place and inject it in the same formation. And the last thing, of course, is we can send the hydrogen to some kind of hub. We can actually distribute for use. Okay, so what is the management constraint? We're gonna produce the natural gas at constant rate because we need to utilize the SMR process and we need to generate the hydrogen at the same rate. We're gonna capture CO2 because sooner or later CO2 will break through. So we'll capture the CO2, we'll separate it with natural gas, we'll combine it with the natural gas, CO2 that generated from SMR, and we inject it at the ground conditions. And eventually we'll avoid methane leaks. So we're not gonna use this methane transportation, we're gonna use the approach to utilize, generate the hydrogen in situ. I'm going to show you some results here. This is the data we use. The highlighted red entries, this is the height. Clearly, this is important. The other issue is the permeability, whether we're going to have low permeability or high permeability reservoirs. And the third one we utilize quite extensive is longitudinal dispersion, how well the CO2 is going to mix with natural gas in place. So we did some analysis. Okay, so the top pictures here shows the impact of molecular diffusion. So we have like natural gas, we put CO2 and they start mixing because of the molecular diffusion. And we see here as you increase the molecular diffusion, the mixing is much more aggressive. So we see here the range, red is CO2, and you go down here is methane. So you can see here what actually happens. And this is the longitudinal dispersion because actually the porous space is a confined porous space. we have what we call it longitudinal dispersivity. So the two are going to work together. And for our cases, the results I'm going to show you, we decided with these numbers over here. And you can see the production well is up here, and the injection well is down here. Remember, this is a box like this room here. So one corner we have a horizontal well producing, which is this one here. And the other bottom down here is the CO2 that we injected. Okay? So let's see some actual results. Again, this is the injection, CO2 injection. This is the methane production. We see here, again, the variation of CO2. You see at the end of the basically production, what we see is that the blue is the remaining methane. And everywhere else, everywhere you see red is pretty much 100% CO2. And somewhere in between is, of course, when we have this mixing zone. And the mixing zone is you have CO2 and methane as well. And the interesting part is here. Here it shows the pressure declines, of course. So we see here at the end of the production here, the pressure has declined, the average pressure, which means that actually we have more capacity in the formation to put even more CO2. So you have an additional CO2 amount you can actually store in there. You can see here the amount of CO2 you can go back, and you see, of course, the pressure increases. And we stopped at about 95% of the initial pressure to be on the safe side. So here is very, very promising. Here so you see the CO2 is going to break through, and basically we'll capture the CO2 and we'll inject it back in the reservoir altogether. All right, so some additional results here. The impact of permeability, we have very low permeable formation, rather very high permeable for gas fields. You see the green line is the constant methane gas production. You see this is the CO2 mole fraction. So we stop the process when we have 50-50. So 50% methane, 50% CO2. Then we stop the process. We say this is good enough. Of course, this has to be vetted based on cost considerations. And clearly, this is a very viable situation. We see here what happens to the injection pressure and the production pressure when the permeability is rather low. But regardless of whether we're looking at low permeability or high permeability, this process works quite fine. Now, these results I show you, we don't have any water underneath, which means it's very nice because I don't deal with water. So let's see what happens when I put water. So the same situation here is the box we saw earlier. And we have the production well up here. We have the injection well down here. And down here underneath, there is an aquifer. And the way the aquifer it is, we consider to be an open aquifer. It's basically a very large aquifer, so that at the boundary between the green, which is the natural gas, and the red, blue down here, which is the water, is a constant pressure boundary. So that basically one means that you remember the results I showed you, the pressure is going to be pressure support, the water is going to move upwards, and will trap some of the gas, and the recovery factor is going to be rather low. And that creates a problem, so many companies as well don't produce these fields because they are not really viable and very, very much attractive. Well, I'll show you some results here, make it very, very attractive based on the process we're actually describing, inject CO2. So we're going to produce again from up here, inject CO2 down here. You can do horizontal wells, so you can do vertical wells too, by the way. So here is again the natural gas. This is the aquifer. And the way we model it, I'm not going to go into details because I don't have the time. So here I'm going to show you some results with vertical wells, horizontal wells. We're talking about first to produce the natural gas and then store the CO2. And then I'm going to show you what's going to happen when we do this simultaneously. Production of natural gas and injection of CO2 at the same time. So we'll do this both for horizontal wells and vertical wells. And we see two cases. One will balance the rate, and the other one will balance the volume. Okay. So here is the case, the first one. We consider a vertical well centered in that box. We produce at the beginning, so you see the production, then we inject once the pressure depletes. So we see here a cross-section. You see the well over here. This is at the end of production. So we see here everywhere pretty much blue. This is the aquifer down here. This is the initial gas-water contact. And you see pretty much there is methane up there, but the water has moved in and basically trapped quite significant volume of natural gas because of the residual gas saturation. So that actually comes to a recovery factor of about 56%. When I don't have an aquifer, the recovery factor goes about 80, 85%. So it's quite different. So let's see what happens when I start injecting CO2. This is, remember, production and then CO2 injection. So we see here at the end of the process, this is the well here, you can see here the water saturation. So the CO2 actually displays some of the water downwards and actually penetrate into the aquifer zone. And now let's see where the CO2 lays. So the CO2, whatever you see, again, red is where the CO2 is, and whatever you see blue is where the water is. So you see here how the CO2 is distributed in the porous space. When I look at the amount of CO2 that actually I can place in there, it's somewhere about 75% when I reach back to the initial pressure. But if I allow the pressure to go about 1% above the initial pressure, I can go quite larger to about 110%, something like that. I cannot see the number from here, don't remember. Let's see what happens when I'll skip this on here. This is what actually happens when I have no aquifer. And this is what happens when I have an aquifer. And this is when I have a rate balance and I have the volume balance. What I see here, I have recovery factors very, very high, very comparable when I don't have an aquifer. This is something we cannot achieve without the CO2 injection. Furthermore, what I see here is the amount of CO2 that I can actually store, which is this green bars, is actually quite significant. It's even higher, especially in this case here, comparing to the volumetric system, one that did not have an aquifer. So I gain both. I increase the gas production, and I increase also how much CO2 I can put down subsurface. So I'll skip some of the results here. Let's show you some of the horizontal wells. Again, this is the well up here, the production well. This is the injection well. Here's the production. This is the injection. This is a cross-section, by the way. You see the initial gas-water contact. This is the aquifer down here. And this is the water saturation at the end of the process. You see here that CO2 is going to be in here. You can see it over in this graph. Again, red is CO2. And in this graph here, whenever it's a blue here, it shows there is water. Okay, so you see here, this part here, this has been encroached by water and basically capture and delay the water CO2 production. So we're out of time. Okay, well, right. Okay, let me show you this graph, I guess. So you can see here very, very well. Again, remember, this is the volumetric. This is the case when actually I can store significant amount of CO2. This is this. It's 130% of the volume because the CO2 pushes the water downwards. This is very important. And so also solubilizes the water. So this has increased the amount of CO2 that I actually store. Thank you very much. I'd like to acknowledge my co-worker, Professor Economides, and there is a student, Jihuan Li, is working also on that, and a master student. Thank you very much.
So as we get ready for the next talk, if there's a quick question for Dimitrios, we can probably take it. So, Jack, go ahead. Dimitrios, just a quick question.
Remember, what we're proposing here to do is that we'll produce the natural gas and we generate hydrogen in situ. So we're not going to transport the methane. That reduces the chances of actually leakage of methane, and that is actually quite beneficial. Also, we're not going to use the methane to actually generate energy or burn it or whatever the case might be. We're going to convert it to hydrogen. And so the hydrogen is going to be the source of energy for whatever, power generation or whatever the case might be. So we avoid altogether having any emissions of CO2, especially if the energy for heating or the SMR process, we utilize also hydrogen. So at the end of the day, this process is quite green.
Thank you. Thank you, Dimitrios. Thanks. So it's my sincere pleasure to introduce this next speaker, and that's Srinivasan. He is the Senior VP for Global Technology at Halliburton. He is a leader in various bleeding edge technologies, and today he's going to talk to us about the confluence of energy transition, geosciences, and AI. And with that, Sri?
Yeah, Ramanan, you're too kind. First of all, thank you for the invitation, and it's a pleasure to be here. And it's been a while since I was in front of a super technical audience like this, so we'll see how this goes. So at Halliburton, we are looking at how we use AI broadly. It's hard not to look at it. You know, with the Nobel Prize in Physics in 24 went to two people, highly deserving people, who are not physicists, but AI people. And so I personally actually have mixed feelings on this. I wonder how your physics department feels about it. But AI is here, it's important, and when applied properly, I think it will bring a lot of value. So I'll give you a glimpse of what we are doing, at least in the field of geosciences. So in geosciences, of course, you all know this, geology is super complex, and depending on which length scale you work at, sort of determines which physics you might want to use to model it. And that all sort of translates to creating maybe big physics models, which might be problematic to deal with. So that's sort of one point to remember. The second is that, as you all know, that especially seismic, but all kinds of geosciences, geophysical data is increasing in size. We have lots of it, and it's getting larger and larger, these data sets. So you wonder, you know, we might be able to augment the physics with data and things like this. And of course, the third is compute advances. It's clear that, you know, today's compute capabilities enable a lot of things which were not even possible 10 years ago. So the confluence of these three things is really allowing AI to, you know, to make an impact in the geosciences today and other aspects of the business as well. The way we look at the value that AI and ML might bring, at least in the geosciences, is twofold. On the left, for example, it's an efficiency play. You know, doing interpretation of seismic, for example, is prone to bias, it's manual, it's painful. You know, and so if properly done, you could use AI techniques to speed up that process, remove bias, and, you know, enable consistency and things like this. So it's purely an efficiency play. And then, more importantly, on the right-hand side, just because the sheer massive amounts of data, which is impossible for human beings to consume at scale, AI techniques will allow us to really mine this and look for hidden insights which might be missed by traditional means. So I think these are the two areas we feel, you know, is where AI brings value. We're looking at AI in many different sort of areas as shown in this table. And I don't know why it says top three, there's more than three, but in all of these use cases, we are exploring how AI can be used. And a lot of these techniques actually are in commercial products that we are now beginning to sell. So I'll just give you a glimpse of a few use cases. This is an interesting one. You know, we have a group in our landmark division called Neftex, which does geology. In fact, they have a huge data set, public and private data set on the geology of the Earth. And so there's huge amounts of geological data and geological models. And so the idea is that in some cases, there are gaps in our understanding of geology. How do you fill those gaps? Traditionally, geologists fill it literally by drawing lines and such. And so the idea is to explore the use of AI, in particular things like generative networks to help fill in the blanks, so to speak, in geology. And so this technique is surprisingly powerful and is helping us and our customers a lot in filling gaps in geology. This is, of course, pretty routine nowadays, seismic interpretation. And this is purely an efficiency play, consistency play. And so lots of people are doing this. We are as well. And this is becoming pretty routine to use supervised learning-based AI to do interpretation. We're also using some of these techniques to do inversion or augment the inversion process itself in seismic, and with surprisingly good results. And we find that when done right, when trained right, it reveals a lot of things which were previously missed by traditional means and things like this. So it's a powerful use case for sure. This is again an example or a use case of filling in the blanks. Often in lots of fields we find that we don't have seismic or poor seismic, but we might have a lot of logs. And so how do you then connect all of this in a systematic way? And so I think AI-based techniques are a powerful way of connecting and interpolating and these logs and sort of help build the Earth model out of it. This is for production or reservoirs, mature fields and things like this. A lot of reservoir models, the traditional ways of doing reservoir modeling is to do history matching with production data and so on. But if you look at sort of the inputs or the information that's available in a given mature field, things like seismic, logs, production data, etc., when you do history matching, to get a result which respects all of this data at any time is a challenging exercise. So you need a sort of a different way to assimilate all of this data to do history matching or make the model comply with all of this information simultaneously. And so we're exploring, these techniques of using graph networks and things like this to to create ensembles of models which respect the data, not just at one time instant, but at all time instance as you get more and more production data, for example. And so this is early days on this, but this is sort of a very powerful technique that we're finding for use in mature fields. Let me just switch to a different set of use cases. We, of course, do a lot of well logging. And here, too, AI plays a strong role. I'll just sort of give you a sense of it. In all of the well logging modalities, if you use resistivity or acoustic or nuclear or sonic, effectively, underlying it is the classical inversion problem, where the forward model is generally a PDE, or and then you do the inversion either in a classical sense or in a Bayesian sense. Either way, it requires that you have to run these forward models, and these forward models tend to be large. And then if you want to do real-time inversion, which is what you want to do with logging, either you have to log slowly, which nobody wants, or you do post-processing, which nobody wants. So everybody wants inversion to be done in real time when you're logging super fast. We're drilling faster and faster every day, and so while logging while drilling, the game is to do inversion in real time. And so this is where neural networks play a key role. In all of these kinds of cases, as I mentioned, we're trying to approximate the forward model PDEs with neural networks to enable inversion. So again, as I said, we do both kinds of inversions, deterministic and statistical. In each case, the forward model is huge, and in many cases, you cannot do real-time inversion. It's so big. So just to give you a sense of the size of these models that you have to solve in terms of the matrix size that you have to solve once you discretize. And so you need to do something different. And we're using different techniques to do this approximation of the forward model by neural networks. And we are applying this actually commercially. We're using these things commercially in resistivity tools and ultrasonics and things like this. I'll give you a quick glimpse of some of these kinds of things. So this is sort of the forward model approximation with these FNOs, Fourier neural operators. They are super powerful and for approximating PDEs. And there's upfront cost to train them in your domain of interest. So for example, if you're using this for electromagnetic use cases, across different formation types and things like this, you have to make sure your training sets span all possible formations you might expect. And then once you do it once, then you're done. Then the speed up is dramatic. So this is an example of a three-dimensional EM electromagnetic tool for resistivity. But just give you a sense, on the left, pictures show you the amplitude and phase of this FNO prediction versus the classical PDE solver. There's essentially no difference. But the speed up is dramatic, 0.05 versus 80 seconds. This sort of speed up enables real-time inversion during high-speed logging, and that's really what this is about. Similarly, this is an example of looking through multiple layers of casings to detect corrosion from within the well. And it's a tricky problem, but here too we are approximating the forward models with FNOs or neural networks of some kind. I don't remember exactly what. Again, dramatic improvements in speed, in compute speeds. Similarly, on ultrasonic cement evaluation-based tools, same sort of thing. So, with these kinds of speed up, it just reduces logging time, increases logging speed, and so it translates to real business value. The other, in petrophysics, for example, since we have so much data, you have traditional closed form equations which are used in classical petrophysics. And so the idea here is to use a lot of this data to augment some of these closed form formulas and stuff like this with regressions, symbolic regressions, and they work surprisingly well. And so in many cases, we are developing these symbolically regressed petrophysical formulas on a formation by formation basis. So especially in the Middle East, we do a lot of work where we fine-tune these formulas for specific formations, and it works quite well. This is an interesting example of using, again, generative type of AI for translating models trained on, let's say, Gulf of Mexico to Norway. So, oftentimes data is limited, and, if you train something on one data in one formation, how you translate to the other or if done naively, it generally fails. So this approach of using like these VAEs, variational and autoencoders and things like this, effectively solves this problem or attempts to solve this problem by viewing, let me see if I have a, yes. So if you have, in this, I should explain this a bit better. So typically, what we're trying to do here is to eliminate sonic. You know, sonic logging is important to understand the mechanics of the formation, Young's modulus, Poisson's ratio, and things like this. But it's expensive. For example, in North America, nobody wants to run sonic. So what do you do on the left picture? You have a poor man's sonic. So you have drill bits which are censored with accelerometers and strain gauges and things like this. And so can you then invert this data to say something about Young's modulus and Poisson's ratio of the formation? So hence poor man's sonic. In principle, you can approach this problem as a physics problem. You know exactly how this should translate, but it doesn't work quite well. So, or it needs to be grounded because you just do not have enough information to do it. And so the idea here is to use these kinds of models, these generative models, to effectively look at the vibration, ROP, strain gauge data, sort of as random variables, and learn the joint distribution of these things through these VAEs. And then use all of this information to help translate or calibrate the physics, which are quite well known from a bit-rock interaction model physics to different formation types. So techniques like this are surprisingly powerful, we're finding, and it solves a real problem, where people don't want to use sonic because it's expensive, and so you can use cheaper sensors, bits, to actually learn something about the formation while drilling. So I'll just pause. In each of these topics is, we could talk about at length, but I just wanted to give you all a glimpse of the kinds of things that us and our peers as companies are also doing. So thank you.
Fascinating work, Sri. I want to open it up to questions from the audience.
So what does it have to do with the energy transition on this?
Our view on this is as follows. We are, as an oil and gas service company, we are super active in CCUS projects and in geothermal projects. So these are near adjacent to CCS sequestration. So since we're talking about this, for example, we're doing work in the area of material science, because a CO2 well, a completion system for CO2 sequestration has a lot of material science challenges. Number one, in cement. Portland cement and CO2 don't go well. CO2 plus water, carbonic acid attacks Portland cement, potentially degrades it. So we're doing a lot of work in the area of, cement or Portland cement and what happens to it over 100 years with CO2, and what are non-Portland cements, for example. The other thing is elastomers. Every completion tool system and every well in a CCUS well will require completion systems are filled with elastomers, seals and stuff. Again, rapid gas decompression, things like this will literally explode these seals potentially. So you have to really do some new material science to really make sure that the seals will survive supercritical CO2 and things like this. CO2 plume migration, CO2 plume monitoring, these are things that we are doing. I mean, a lot of things that we do, information evaluation, seismic, fiber optic sensing, EM fiber optic sensing, the combination thereof. These are all techniques that oil and gas has proven and are directly applicable to CO2 sequestration. In geothermal, since I'm on a roll, in geothermal, we're doing similar things. I know that you have a talk with Fervo later today. And so, you know, for EGS systems, you know, we're doing a lot of work, also with Fervo. But, you know, we're also looking at pumpless geothermal, you know, meaning that, you know, super deep drilled wells such that you have a thermosiphon effect, so you don't need pumps, which is really, I think, is what would be a game changer for geothermal. And so for that, you require completely unknown drilling technologies. The tradition, I mean, if you're doing basement rock drilling for like 10 miles, the traditional diamond bits will not work. It would be uneconomical to drill like a heat exchanger of wells that deep. And so we are working on electric arc drilling, for example. You know, so there's a lot of things that the oil and gas, you know, a traditional oil and gas company like us are at least working in these two spaces. It's just to give you a sense of what we're doing.
Yeah, just a different kind of question, which is more about your team. As you are doing this kind of work now, has the number of people on your team shifted, and how has the skill mix shifted? Then the second question is, as you think about advice you would give researchers at Utah and U of H, what kinds of areas are you finding most helpful in terms of the work places like Utah and U of H are doing?
Yes, thank you, great question. So I think from a skills perspective, I mean, just to give you a sense of we have about, you know, 2,100 engineers and scientists, you know, of multiple disciplines, of course. So the bulk of and if you track the makeup of this, you know, we have about 800 or so mechanical engineers, you know, and this has been steady because our business is hardcore tool development and stuff. And so that's going to always be big. You know, 5 years ago, the next big group would be like electrical or the geosciences, but now it's software and data science type people. So, so digital automation, data science, AI, you know, is causing us to actually hire more people in this area, for example. Although, you know, we much would prefer that I mean, to me, every engineer is by definition a data scientist. And so our approach is to actually have our you know, regular engineers and scientists become data scientists. I mean, so in that sense, you know, we are training a lot of our people to become one. I mean, to me, it's not rocket science. It's something that good engineers already know, statistics and stuff like this. So yes, I mean, I think we're hiring more doing more software, more digital, more AI and things like this. When it comes to AI, I mean, I wouldn't say that we're doing fundamental things like coming up with dramatically different neural network architectures or training pipelines or things like this. We are mostly applying it. So, I mean, there are lots of people in the world doing cutting-edge research in neural networks. So I think translating all of that cutting-edge research, which is happening in so many industries, to our context is where we are focusing. I mean, all of these use cases is how do you use VAEs or generative networks or graph neural networks, and for our use case, this is our sweet spot. And if you ask me, you know, especially in the area of AI and the geosciences, what should you do from a research perspective? It's exactly this. I think we are finding that traditional, you know, the architectures that Google and the others work on may or may not be directly applicable, for example. And so I think much work has to be done to, fine-tune these foundational neural network and other architectures for this context.
Any other questions? If not, let's give a big round of applause for So before we get to Scott Tinker, I'm going to make a quick request of everybody. If you want to take 5 minutes, go outside, grab lunch. There's lunch on both sides of the corridor there. Bring it back, and then we'll get started here. So
we're very excited to introduce our lunchtime speaker today, a good friend and colleague, Dr. Scott Tinker, who's Director Emeritus from the Bureau of Economic Geology at the University of Texas. I'm Joe Powell. I work under Ramanan as the Energy Transition Institute Director, and we're very happy to have you engaged here in the program today. Scott has a long and distinguished career at BEG. He's been involved in that institute, but also the Switch Energy Alliance. And so he's a film director and actor, been to more than 60 countries. And how many of you have seen the Switch or the Switch On videos with Dr. Tinker here involved? So really just a tremendous outreach. When it comes to dealing with the energy transition, most of us are in the developed world, but Scott actually gets out to the developing world, which is where we really need the energy transition to happen. And so he's going to be very provocative and engaging today, I can guarantee, and look forward to his presentation. He's been on public radio and public television as well, and also has numerous medals because of his accomplishments in this space. And so, Scott, we're very honored to have you speak with us today on your views of energy and sustainability.
All righty. I'm here to wreck your lunch. So I hope you've eaten some, because we're going to get busy and thinking. It's great to be here with you in Houston. Students from U of H and University of Utah, terrific to have students here, and we're all students, so we just keep learning. So I actually changed the title from what's in your program, whatever. I gave me an extra 10 minutes, so I changed the title. So what's my goal today? It's not to tell you what to think, okay, but it is to share some data and engage in civil dialogue and some critical thinking. And hopefully laugh a little bit along the way too. So here we go, start with some philosophy right off the bat to encourage your digestion. It's a mark of an educated mind to be able to entertain a thought without accepting it. Wouldn't that be nice, right? Let's just have some civil dialogue, do some critical thinking. You're not going to agree with everything I say, I promise you. But that's okay. The point is, we're going to think about things. So I'm going to start framing this way. The geologists in the room, we love these triangle diagrams. Energy security, which underpins economic security. Healthy economies have secure energy. That allows for investment in the environment. Healthy economies can afford to invest in the environment. We want our energy affordable, we want it reliable, and we want low emissions. Wouldn't that be great if we could have it all? If you want 100% low emissions, you're not going to get much of anything else in the real world. These things come together. There are trade-offs. There are trade-offs we have to make as we go through that. I call that the radical middle. Radically lonely most of the time, okay? So we're framing it. What is energy? This is the only point I'm going to look at the screen because this is hard to do. You can clap when I'm done. This is your Dr. Seuss moment. Ready? What is energy? It's our homes and our phones. It's our pets and our jets. It's our heaters and our beaters. It's our water, our daughters and our sons and everything they wear. It's our packs and our snacks. It's our frames and our games. It's our waste and our paste, our light and our sight. It's our stuffy nose and our clothes, and it's our wheels and our meals. Everything depends on energy. Okay, come on, that was hard. All right. We don't know this. Everybody in the world think, oh, it's a socket and my gasoline. That's energy. No, it's everything. And the sad truth is, energy powers the world. It improves our lives, but there's a lot of people in the world, the reality is, that don't have much, if any. They don't even have the basics: light, food, shelter, clean water. And I've gotten to visit a lot of them, so let's talk about this a little bit, poverty. Look, 3 kinds of people in the world: those who are good at math and those who aren't. Okay, so which of the 3 are you? Here's some simple arithmetic. This is the amount of electricity consumed by a human being in these countries in Africa, and here's my fridge. Okay, that's energy poverty, 9 times more than a person. And I have more than one fridge. I'm a geologist, I have a beer fridge. Okay, keep it in the in the garage in Houston, really efficient. That's it. It underpins human flourishing. And I've been fortunate, Joe mentioned, I've been to 60 countries. They're color-coded by the number of visits and met a lot of people. 2 feature-length films with Harry Lynch on the energy transition, kind of, we released in 2012. And then this energy poverty film. So I met some folks. This man in Ethiopia had tears in his eyes when he told me his kids and grandkids and great-grandkids had just come out of the bush, and they were in school for the very first time in his family. We head over to Nepal and meet Sanakanchi, cooking indoors with wood, like 2.6 billion people in the world still do. And we go to the SETI Memorial Hospital, a tough part of the film, and watch kids die from breathing indoor smoke, and moms with cataracts and cancer. 3 million people a year dying of this, breathing indoor smoke still. Come back to Africa, Kibra, the giant slum outside of Nairobi, and you see a church that doubles as a school here, 2 dangling light bulbs. And the kids in their uniforms, I remember punching in to take this picture, mounds of garbage and polluted water and polluted soils, but they're going to school. Head over to Vietnam and meet Thon in that red shack, and she lives there with her crippled son and carries him on her back every morning across that plank so he can go to a school. Over and over, this education theme is repeating. In India, we see the most severe poverty I've seen. We went looking for it, and we found it. And severe wealth, tremendous disparity in that big, big country. And then back to the Western Hemisphere, we actually brought solar, first electricity, to the indigenous village of Gunchukwa, the Arwako people. And you can see the array there on the left, and it, 3.5 kilowatt. It put some light bulbs in mud huts and a couple ceiling fans and a fridge. These kids of the Arwako people, they'll die, half of them before they become adults, from simple things that wouldn't kill us in the rich world. A tooth infection, dysentery. So that last night, we turned the lights on with the chief or the mamu. It was really powerful. They hadn't seen each other in their own village at night, except over a fire before. So that's the world in many ways, and I'm not going to talk about ESG, except right now. The environment matters in that world. Clean soil, clean water, clean air, governance, get me out from under this autocrat. Social, how about a school or some health care? Something to improve my life. ESG matters. And there's a lot of optimism and hope. I'm always remarked by it. They see a future that's brighter than the one they're in today, as opposed to the pessimism and fear in the rich world. Protesting from rural folks, extensively, and urban folks. Burn capitalism, not coal, in Europe, okay? And that's fine. I love the passion, but man, fire up that sign and end global poverty. Wouldn't that be amazing if Greta led a movement to end global poverty? And we could actually see the results of that happening very powerfully. Poverty is the worst form of violence, Gandhi reminds us. It's the worst form. So I'm going to ask questions today, 5 of them. It's the honor system. You get about 10 seconds. Just keep track of your score, and we'll answer. What percentage of people in the world lack secure energy today? What percent in your head? Okay, just keep track of it, and we'll answer it now. So here's the world, countries in the world, gross national income across the bottom against energy consumed across up the y-axis, electricity. There's a correlation, pretty strong trend. The average income in the world is 13 grand. They're both on log scales. 13 grand, 7,000 kilowatt hour. That's the average. And if you go the other way, the average, 3,200 kilowatt hour, average for all the countries, and that's 8,000 bucks a year, $22 a day for the globe. There's a whole group of countries that consume less energy than my refrigerator, 500 kilowatt hours, and they don't make much money, 100, 200, 2,000 bucks. They're emerging, if you will. The next cluster, let's call that developing, 500 to 7,000 kilowatt hours, more income. And then there's the rich world, 7,000 up, over 50,000, 70 grand or more, developed world. This is kind of how it lays out. Guess what? Those emerging economies want to become developing. And the developing want to become developed. This is emerging from poverty, okay? And it has to happen. We have a few countries that are secure and most of the world that isn't when it comes to energy or economic security. Same colors code here, same color scheme. Let's look at it on a map. Look where the reds and yellows are, the poorest. And then the purples, and then the blues. I'm going to overlay the least livable cities now in the world. Look where the least livable cities are, right on top of poverty. No shock. And here's the most livable cities on blue wealth. We love the livable cities because it's rich. And as I look at the emerging down here, severe poverty, energy poverty, economic poverty, mostly subequatorial. There's some wealth there, but large majority need something to get started. Affordable energy, just to get started. Now we go to the developing world, that big middle of the graph, and it sits up in here. It's everywhere, but clustered again, Latin America, Eastern Europe, Russia. They've got some energy, but it's not secure. It comes and goes. They need something reliable. And then there's 60%, more than 60% lack secure energy. Keep track of your own score, okay? How many got that right? Good, good, good. All right. And I put out a piece talking about this. What's net zero poverty? What does it look like? Editors changed the title. And then we have the developed world, that's us, the rich world. We want climate security. We want it clean. Fine. Now look around the world at the variability. What's clean even mean anymore? In the rich world, it means atmospheric emissions. You say clean, it's CO2, maybe methane. The rest of the world, water, land, air. Okay, the cleanest air in the world, the stuff you breathe, green. Where? Rich. Dirtiest air, red. Where? Poor. Over and over, this theme repeats. Poor countries can't afford to clean up the land, the air, and the water. They have other priorities. Eating, shelter, education. Bring that all together, and you see there's a lot of variability in secure energy. Varies tremendously across the globe. 60%, okay? So it's a paradox. I said this down in Quito, I think, many years ago. Energy won't end poverty, but we can't end poverty without energy. This is the great dilemma that we face. It's time to power the people. It's time to provide energy access for everyone. Affordable, reliable energy for everyone. So let's talk about that energy. We used to cook indoors with wood, kept ourselves warm thousands of years ago. The first form of energy is the sun, not the most recent, the oldest. It grew the hay, powered our vehicles. We captured the motion of wind and water, and bigger dams we built and killed whales to get their oil and light our homes with whale oil. That's old energy, okay? And then we found coal. Carbon, nature had densified it. Burn coal, boil water, make steam, turn a turbine, run a generator, make light. Okay? That changed the world, the rich world. Then we found liquid hydrocarbons. Many of you are studying and refine them, put in our vehicles. Methane came along, and finally nuclear. Okay? So this is the new energy, if you will. Yet we still have Sanakanchi and 2.6 billion people cooking like we used to. A third of the world. How is that possible? And I'm showing you this because this is one of the most important concepts in energy, I think. Density of energy. Specific energy. Let's call it energy by weight. Log scale on the left to right. Through time, we've seen this change. Nuclear is 1,000,000 times denser by weight than dung and wood. Right? And I've put lithium-ion batteries on here because they're a lot less dense than dung. Okay, just for scale, by weight. Dense energy secure. Now, take off the nuclear so we can start to see a little more spread. The gases on the right are denser, and they don't have as much SOx, NOx, mercury, particulates, the other kinds of pollutants that burning solid fuels have. And you can't weigh the sun or the wind, where would they fit on this? Well, somewhere down in here. So Václav Smil came up with a new scale, surface power density, energy by area, watts per meter squared, and the same trends. And we put names on these things, right? Renewable and thermal. We'll talk about that. Clean and dirty. Some of you probably learned this. A little judgmental. Okay. Industry has its own terms, intermittent and reliable. All right. Yeah, all right. Weather dependent and firm. Okay. All true in some level. Let's call them electrons and molecules. The stuff on the left makes electricity. On the right, we can burn molecules, make electricity, but we need molecules for lots of other stuff. A lot of heat to make cement and steel, mostly from burning molecules. Ammonia for fertilizers, to grow the agriculture for the world, plastics and other things, molecules. Joe is a molecule guy. You know, he understands these things. We need both. We're not going to electrify everything. It's a false goal. We have to have both. And I want to remind everyone, electricity is only it's less than 25% of total energy consumption. 75% industrial, residential, commercial, transportation uses that aren't electrified yet. Okay, less than 25%. So I said to Manchin's hearing a couple years back, it's really important to be completely factual, but also factually complete. Factually complete is hard. Nobody can do it. Try to engage it all, but we try our best. What percentage of the global energy demand is provided by solar and wind? What percent? In your heads, let's take a look. These are the data. This isn't capacity, this is actual energy production in the world. Coal and oil are still going up. They're very dense. They make a lot of CO2 when you burn them. Natural gas is going up tremendously in the world. So is nuclear still. Very dense, make less CO2. Emit some more methane. And then hydro and everything else going up. They're not dense, but they make less CO2, a lot less. They're trade-offs. If you're just looking at CO2, there are trade-offs in these things for sure. Remember the Great Recession of '09? Some of you do. That when the world goes in recession, we consume less energy. You can see the dimple. We don't move around as much. And here's the COVID recession, deeper, but we're back. We're already consuming more energy than we ever did pre-COVID. There was nothing structural that changed there, okay? We consume more coal and oil than everything else in the world combined today, by a lot. We're actually, coal and oil are still the dominant two sources. Nothing has gone down globally, nothing. We just keep adding wedges. Hay hasn't even gone down. We consume more hay than we used to consume. More people, more things eating it and burning it. It's completely factual. Solar and wind are the fastest growing sources. Look at them. Incredible. Incredible progress in solar and wind. This is a rate. Fastest growing. Early stages. Let's try to make it a little more factually complete. We scale it. And there it is in the data. It's not hidden. It's right there. About 10% of the growth in energy demand globally since they started. 10% of the growth is solar and wind, not the base. Scale, 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 scale. Less, about 5% of the global energy. How many got that right? Okay, good. You're getting your dessert. You're starting to feel it. All right. Annual coal consumption. This is global. Been flat in the rich world. Yet we've doubled our economies and come down, and starting in about 85 or so, we've cut it in half, coal consumption in the rich world. Here's Asia, and here's the rest of the world, hardly any, okay? And there it is on a map. Asia consumes a ton of coal, no pun intended. South Africa, Poland, and a few other places, but mostly it's coal's an Asian story. Unless what? Unless you're Germany and you lose your gas from Russia. And what did Germany do? Increase their coal electricity for baseload electricity generation and continue to shut down their last 3 nuclear power plants. Climate scientists were aghast. They should be. What are you thinking? There's a lot of reasons for this. The point of that is, when leaders are stressed under a little tension or pressure, what do? They choose energy security over climate security almost every time. Not what they say, what they do. Even Germany. Okay. What else is growing? There's solar and wind, well, oil and gas. In percentage terms, almost the same over 60 years, 1% different. Actual units, tremendous increase in gas and even in oil. So there's coal. I'm going to lay natural gas right on top of it, same scale. Gas has grown tremendously, and not just in Asia, in every geopolitical region, more gas is being consumed. It's kind of flat in Europe. The gas to coal ratio, 39 to 91%, and growing. Gas will probably pass coal sometime in the next decade or so. It's a global story. So you can see here the consumption of gas by regions in the world, the big regions. North America, we consume the most natural gas. Here's the production in those same regions. Only 2 regions in the world that consume more gas than they produce. Europe and Asia, okay? Consume more than they produce. They need options. And by the way, low reserves, either don't have it or they won't produce it. And a lot of LNG. Okay, we won't go into that story today. They need options to gas. So Europe, again, electricity generation, not total energy, has brought down coal and gas in their power sector, has brought down nuclear and hydro and grown a solar and wind and other wedge, if you will. And this started back in 2007, pretty important year to remember. 2007, not Ukraine. This is policy much earlier than that. And it's nice. The right side has a lot more diversity in that mix. Policy underpins that. That's Energiewende in Germany with Angela Merkel and others. This is policy. How's that working? Well, on a cost basis, it's expensive. 40, 50, 60 cents a kilowatt hour. That's 300, 400, 500% more than we pay here. And a lot of industries and companies are suffering and leaving. It's very expensive to run industries. But I heard solar and wind are cheaper. Yeah. Yeah, right. You know. When you hear that, what does that mean? Is it just a lie? It's not a lie. It means this number from Lazar, levelized cost of electricity or energy, where it's generated at the plant gate, has come way down with solar wind. It's really phenomenal at the plant gate. Not to you. To get it to you takes something there when the sun's not out and the wind's not blowing to make it reliable. That something, giant grid-scale batteries, a load-following gas, is expensive because it's not always on. So you have to, reliability costs money, all right? And look, it's not judgment against solar and wind, it's physics. Night happens, okay? You can't avoid it. You need something else there. This is the GDP of the US. Here's the GDP growth of China over the last almost quarter century. China accelerating, now flattening in the last few years. What do you think Europe looks like? Up to 2007, it actually passed the US. And it went flat. Since those policies, not the only reason, one of the reasons, it's expensive. Europe is struggling right now economically in many ways, okay? Affordable, reliable energy underpins healthy economies. Energy, economy, invest in the environment. Let's bring it back home. Here's California, their electricity mix since in the last 20 years, and here's Florida. Same scale, 2 big states, consuming about the same amount of electricity. Look at the difference in the choices, though, since 2003. Florida wind, gas, and some other things. California, solar, wind, other importing electricity, etc. Very different choices. Some would celebrate the left as a success, others the right. If you're paying for it, here's Florida's cost of electricity over that time period, and here's California. 32 cents a kilowatt hour. We pay 12 or 13 here in Texas, something like that. This is data, not my data, the data, okay. And just this week, 10/22, approval for a double-digit increase in California. Again. Let's lay the US right on top of this, same scale. We consume a little more electricity than Europe. Ironically, in 07, we went flat as well, but look at the right side. Here we have a different set of things that we've done, and that red is shale gas. Shale gas made it cheap. Gas was cheap. A lot went into the power sector. So here I am, a little geologist, next to an outcrop of shale. I want to show you, if you have never seen what shale looks like, maybe this is 6 or 7 vertical feet, 8 feet. Let's zoom in and take a look. When I say in, I mean way in. That's the SEM of the Barnett, some early work at the Bureau. Those little pores are in the nanometer scale. Here's a hypothetical pore throat, if you will, of methane molecule, CH4. I'm going to scale them to be the same as this figure. It almost goes away, but Christine right up front can still see it. Molecules? Here's a human hair. Let's put those Barnett pores on the width of a human hair. There'd be 100 to 200 pores across the width of one human hair. That's how little they are. That's why you have to crack that rock. You have to frack it to get the molecules to flow out. What percentage of oil and gas comes from shale today? Take a look. Get it in your head. All right, here's the data. Shale oil in 07 was 4%, now it's 60%. Shale gas, 7%, over 60%. Starting to flatten up there. Incredible technological change, economic and technological change. 60% comes from shale now, all right? And what has that done? Well, these were our imports going into 2000, ironically 7. And here were our exports of energy, basically unchanged. And this was the trade balance for energy in the US. And then shale happened. Completely reversed it. We net export energy now. It doesn't mean we're energy independent. We're still importing a lot of energy, oil, okay? But net. It's incredible change that happened as a result of all that. Oil. Asia consumes more oil. North America is next. Here's the production. Only 2 regions in the world that consume more oil than they produce. Europe and Asia. Low reserves, high imports. What does that mean? They need options to oil. We get it. What are those options? Well, here's an electric car. It says it right on the license plate, electrons. And they're charging with diesel. Okay. These are diesel generators making electricity to charge a car. This is really stupid. I mean, okay, it's funny. And it's remote Australia. Those close can see it. It's ironic. It's not representative. I've had people say, I didn't know. Okay, here's what is representative. Remarkably, we see almost 1 out of 5 EVs sold in the world today to be electric. 1 out of 5. A vehicle isn't a car. It can be. It's a scooter, a 2-wheeler, a 3-wheeler. Anything with a motor and a battery is a vehicle, okay? But still, 1 out of 5. Where? Who needs options to oil? Where are they sold? Say it. Okay. China. 10 million. And in fact, China is exporting about 60% of those now to the world. Brilliant. Need options, they're doing it. Europe. US. Rest of the world. 85% of the EVs are China and Asia. It's not a global thing yet. About 55 million sold under that curve, 55 million vehicles. That's a lot. So look, how many batteries would it take to electrify half the world's vehicles? There's 1.4 billion vehicles in the world. Let's electrify 700 million of them. How many batteries would it take? Okay. Well, here's my 55 million. First of all, it's going to take some charging connections to charge all those. I don't have any accurate numbers, so I just made this one up. Studies have shown accurate numbers aren't any more useful than the ones you make up. How many studies showed that? 87. Okay. So, all right, let's just make up a number. Let's electrify half the world's vehicle fleet. Where'd that come from? By 2040. All right? It's going to take 300 million charging stations up from today. And we fit our 55 million vehicles in there and take that up to 700 million in 16 years. Really? You know what this is? The floor bed of a Tesla S. You know how many batteries are in it? Not pack, the batteries. 7,000. One car. 7,000 cell phones. All right? Let's make the math easy. 5,000 batteries per vehicle times 700 million, 3.5 trillion batteries. And they wear out. You gotta make them again. 3.5 trillion. I did the math once, I can't remember what it was, like 35 or 40 years to make 3.5 trillion batteries if we could make, I think it was 1 a second. Never stop. More than a trillion, okay? And they come from somewhere, they come from these metals, and that's why an electric vehicle takes 600% more metal than a combustion engine. Not the car, the fuel in the battery, 600% more metals. And so you can say on your car, EV, ex-polluter in Colorado, if you think mining's green, how many think mining's green? Put them up proudly. You're consistent. Nobody's ever raised their hand. I'm a geologist, I don't mind mining. It's not green, okay? I took this picture in Michigan, kilowatt on the Tesla, a kilowatt of electricity, all right? Same story, kilograms per megawatt of metals, gas and coal versus solar and wind, 500% more. Not judgment, physics. It's density. It just takes more stuff to collect that material. So at least the Tesla driver in Alberta knows it. Coal powered, you know, right on the license plate. And the Lambo doesn't even give a crap. It just says CO2. You know, it's a fill me up, gasoline. And these things come from somewhere. Top 3 producing countries of oil and gas in the world. The U.S. is in there today. We won't always be, but with our shale extraction. And here's some of the top 5 metals that we need for solar, wind, and batteries. And it's pretty diverse extraction. Where is it processed? Watch close. Brilliant, China. Belt and Roads and other initiatives bought the processing for all the metals. Who needs the options? Who's making the panels and the turbines and the batteries? China. Brilliant, by the way. Tightens its chokehold on graphite, lithium. Just go down the list of metals. This is an energy security issue, and we're really not talking about it much. Okay. Electric vehicles, there's issues. There's a lot of good stuff. We hear about it. There's safety, cost, resale, that people aren't buying them. They're getting very cheap to buy a used one for reasons. Mining disposal impacts, range, security of supply. These are real issues. I'm not making them up. I like EVs, especially hybrids. I'm kind of a big fan of those. But the industry is retreating from them. I could put 100 articles on here from the last 2 weeks, company by company. They're backing off and saying, well, hey, hold on a minute. The backlash in Michigan over the EV mandate that exists there, et cetera. So optionality. Smaller vehicles, less weight in the battery, electrify it. EV, you know, a hybrid vehicle, awesome. As the vehicle gets bigger, you're hauling more weight in the fuel. Hydrogen, right? Fuel cells, compressed natural gas. And larger vehicles, I'm flying in the morning, it'll be on jet fuel. It is not going to be on a battery airplane. And if it was, I wouldn't get on it. Okay, I really wouldn't. Not just for the range. Okay, there's a reason you can't put your battery, the reason you can't check it, a lithium-ion battery. It's a safety issue. I put out a piece saying reducing options doesn't work. Markets hate fewer options. They like more options. Mandates and heavy incentives reduce options. That's what they do by design. So you're a proud Tesla driver in Colorado, no oil, you know, no tires, no plastic, no battery, no electronics, whatever, no knowledge. This is the problem. May as well say, I love mining. They like mining in Colorado. Maybe they'll start doing that again. No. John Hickenlooper's senator there, he's a geologist. Number of states proposing EV mandates grows. In spite of you can't buy that diesel truck in California. You got to sell one electric for every diesel truck. Mandates are reducing the options. And the future looks bright for electric school buses no matter who wins. This was October 7th. This article actually terrified me. Again, not for EV reasons, for this reason. Have you seen these? Buses lined up, they're open, but they're electric buses. And then one starts to smoke a little. And bam. And then the two next to it. And then it keeps going. And in a matter of minutes, we had this. And the firemen were there very quickly. Everything is dangerous. Liquids, gas, whatever. But these are not safe either, necessarily, depending on how they're handled. So that brings me to climate and the environment. Put your big picture hat on, the age of the universe. Here's the age of Earth, relatively, 4.6 billion years. Let's just focus in on the last 565 or 70 million years. This is the temperature on Earth through time, proxies, going back. And that's the average of 1960 to 1990. I didn't put this together, I'm just animating it for you, which took work. So let's take a look at that. Remember, this is how much of the Earth time and universal time we're going to look at. It's a log scale across the bottom, 500 million years. That's a big chunk of this 560 million years. It was warmer. The Mesozoic, dinosaurs, Triassic, Jurassic, Cretaceous, it was warmer. Okay? A lot warmer. 4, 5, 6, 7 degrees C. Now we're going to strip off 100 million years, ever smaller chunks, and it starts to cool. Let's pull off 5 million years, and it goes below the average. And we're going to pull off 1 million years of time, and we start to see these cycles. Every 100,000 years or so, cold, warm, cold, warm. And then we'll pull off the last 20,000 years, where we are today. Those glacial interglacial cycles look kind of like this. For 80,000 years, there was ice covering New York City and Michigan and Minnesota, really well documented. 1,000, 2,000 feet of it. And for 20,000 years, it melts back. So for a long time, Manhattan looked like the left, and today it looks like the right. Okay. Every 100,000 years or so. And the Stone Age arguably started around 3 million years ago, so things like humans survived these things. Okay. There weren't many people, relatively. And then we're in our current interglacial, 20,000 years of it. Let's strip off the last 2,000 years. Now we're measuring things with stronger data. This is the temperature of the Earth in the northern hemisphere, and those are all the different measurement points, kind of scattered. Somebody fit a mean through it, and so there it is. And we'll strip off the last 50 years, plus 50 looking forward. And those are the best climate modelers in the world at the IPCC, and they're damn good. And they ran 4 scenarios. But there's a lot of scatter around their future scenarios. A lot of scatter, because it's a bloody hard problem, modeling the Earth's climate. It's not a 1-for-1 CO2 temperature knob, no matter what you hear. That doesn't exist. All the climate modelers in the world pretty much today agree that the pink and the orange, the 2 high ones, are not going to happen. Things are better than that. But I'm going to pick the high one in here, this next one, RCP 4.5, and we'll lay that on this graph. And it leaves the graph. It goes up another degree C above it. This is what you're hearing, and this is what that forecast would say. I'll scale that back onto my figure. You're thinking, this guy's good with PowerPoint. And this took a long time. Trust me, a lot of flights. And now I'm going to scale that 20,000 years back so it fits in the interglacial. There's the one we're in today. It's right about the peak, if we went up 3 degrees more, would be right about where the last 4 were. Okay, warm. Here's the mean without us doing that. And then I can shrink that back and you kind of see where it sits in the chatter. So we've been getting a little bit warmer, but overall, we're in one of the coolest periods in Earth history today. But in the interglacials, it's warmer. And humans are influencing it. There's just big debates that go on about either or here. It's not it's and. These two things are happening, okay? Why? CO2 emissions. North America, flat, doubled our economy. Asia, you've seen the coal, you know why, up. Rest of the world, just getting started. So there's the actual emissions. Asia emits more than the rest of the world combined today. We used to. They do now. And it's not because Asia's bad, it's for this reason. Above that red line, countries consume more stuff than they produce. And below it, they produce more stuff. It's a CO2 emissions scale across the bottom. We make 5 billion tons of CO2 every year in the US, but we consume more than we produce. China makes double that, 10 billion tons of CO2, but they're net producers. In fact, most of the non-rich world, the non-OECDs, are producers in blue. The rich world, us in Europe, we're consumers in green, and we're saying, send us our stuff, okay? Asia makes stuff, and we get it on an Amazon truck. One item at a time at our bloody front door. Hey, a Twinkie, you know. What are we effectively saying? Yeah, why you do that, put out the CO2. Use coal because we want it cheap. Use coal, put out the CO2 for us. And we'll just consume this stuff. Is that zero emissions? There's only one atmosphere in the world, last time I checked. This doesn't address climate change. This is just a shell game. This is rich countries saying, we're cleaner. Some states doing it. Companies are doing it. Buying offsets. From who? This just came out. Climate policies achieve major emission reductions for 2 decades. They looked at 1,500 policies. The New York Times, known for its right-leaning Fox-like reporting, puts it out and says, hey, only a few of them worked. 63 is what they quoted. Worked. Out of 1,500 policies. Not that unusual. Policy is hard. These guys had good intentions. And policy have good intentions. They were putting in posts to keep people from parking next to the building. All right? They forgot where they parked. Okay. They're not getting out. And that's what policy does. It pins you in. You got to be able to get rid of the policies that aren't working without being called a flip-flop. Emissions reductions is a really tough problem. You have to have the right tech. It has to be the right price. It has to be able to scale in the time frames that are needed. This is really hard. Some of the things that are working, I heard talked about some this morning, natural gas replacing coal, nuclear replacing coal. Big tech is finally saying we need reliable, affordable electricity, and they're going nuclear. Amazon, 3 Mile Island, et cetera, et cetera. I just read about another one this morning in Ohio. They're unmothballing the power plant. Hydrogen, geothermal, hydro, the things you're starting to talk about and hear about. Carbon capture, direct air capture, nature solutions. Now, none of these are easy. Exxon just announced the largest USA offshore carbon storage, 271,000 acres offshore. It'll do 6.7 million tons a year. Impressive. That's 0.13% of US emissions and 6 hours of China emissions. 271,000 acres. How much is that going to cost? I love Exxon, by the way. I love you, Exxon. I do. My daughter-in-law works there. In the carbon group, okay? Scale. Solar, wind, batteries, yes, this is another wedge, and finally efficiency and conservation. These are the things we can start to do to try to lower emissions. Climate matters a lot. What are the impacts of climate change? Nobody's talking about this. It's incredible to me. This is the table in the IPCC most recent report, AR6, Working Group 1, Chapter 12, Table 12.12. These are the impacts of climate change summarized. On the left are the things that have started to leave the historical window. And pink and blue don't meet their standards yet for statistical virility. So it's temperature and CO2 have left the window. They're going up. That column have not yet left the statistical past. What's in there? Oh, floods, droughts, fires, wind, hurricanes, snow and ice, sea level rate, floods. None of it has left its historical. Yet we hear all the time the most rapid acceleration, the worst on record. It just keeps getting worse. The models on the right say it could, some of those things. This is out of the IPCC report. This isn't some crack university that got paid to do this. These are the top people in the world, and nobody's reporting on it. What does that mean? It means we have some time, okay? It's not a panic. I want to communicate that clearly to you. The land, the air, and the water, it all works together. We've got to work on protecting all of it as we move forward with energy. Which primary sources are renewable? Take a look. Okay. Let's look at the data. Life cycle impacts, from biofuels all the way to nuclear. I think every form of energy just thinks of itself as the bald eagle. You know? I'm just the bald eagle of energy. But when you take a slightly different look at eagles, they're kind of funky looking from the front. You know, and so is energy. All of them have some pros and cons. Biofuels, you got to grow the stuff, process, refine it, transport it, then we burn it. It's not clean. It has emissions big time along that. Solar, wind, batteries, you mine for the stuff, you make the turbines and panels. I mean, look, solar field, this was in our first film in Spain. I'm thinking, where do these go when they wear out? And they do wear out. This is after a hailstorm. Did you see the one in the tornado after Milton in Florida? Just ripped through a field. And they wear out on their own. Where do they go? You've seen lithium mining, both from hard rocks and at the surface in South America, the footprint of one wind turbine. This rebar will be filled with concrete so it won't tip over. The blades, we're just burying them in Wyoming, and we're burying more of them in Texas. We don't recycle them. They wear out too. They fail catastrophically. Nantucket, fiberglass everywhere. They close the beaches. Coal, oil, gas? Are you kidding? Coal mines? You know, coal power plants? This is right here, power in Houston, the Parrish power plant, if you haven't been there. Hydraulic fracturing sites. Here's nuclear reprocessing in France. All of these things happen. The reality is, to collect energy, you got to mine stuff, build collection systems, and then when it wears out, you dump it back in the earth and the air, and do it again. There's no renewable energy, okay? It's just a word we use. It's not renewable. You mine, make, dump over and over. It's not renewable, okay? I said this to a TED Talk, 1,100 kids, students, college students. You know. I'm still here, alive, barely. They're looking at me like, who invited this guy? All right? All forms of energy have trade-offs. On the road to success, there are no shortcuts. Ask this poor bastard. We can keep telling our kids there's pretty energy and there's ugly energy. Right. But we're not doing them any favors. It's more complicated than that. There's more than that involved. Nothing is renewable. There's no renewable energy. How many got that right? Wow, a very select few. Okay, let's wrap it up. I ran this scenario out to 2065, one of an infinite number. The actual data on the left, the scenario to the right, coal coming down a lot, oil starting to, gas and nuclear growing, everything else growing a lot. The actual energy demand on the left, I start to roll it over with population and efficiency as we go forward. But still, there's a lot of coal, oil, and gas in that so-called fossil fuels. It scares young people. They see that, they feel like they're in the running of the bulls, right? Just getting trampled. I thought it'd be gone in 10 years. This is one scenario. The winner of the last photo taken contest. All right, there it is. Some good runner-ups. There it is. But that would be called business as usual. Exact same data, left to right now as a percentage. As a percentage. Same data. You don't even see the COVID dimple. You cut coal and oil more than in half as a percentage of the mix. Gas and nuclear more than double, and everything else goes from 6 to 30%. The right looks nothing like the left. You're going from carbon to hydrocarbons to methane, hydrogen, uranium, and thorium. This is a density driver. This is physics pushing it out into the future. You're balancing intermittent things with dispatchable things to make it reliable. I like the right side. There's more options in it. But if you take away fossil fuels and nuclear, there are fewer options in it, and they're intermittent. That's not reliable. We need optionality for reliable energy. So what is this transition? I think our leaders, it's hard for me to say that, leaders, the people that are running for president, I think they believe this. Here we sit, today's energy, and we're going to go to tomorrow's energy like this dude does. He's wearing flip-flops, okay? That is not a transition. That is a leap of faith. And if he doesn't land it, it's over. Let's just agree on one thing today. That is stupid. All right? He's an idiot. Don't do that. So what is it? As simple as I can say it, energy addition plus emissions reduction. Setting everything else aside. That's our transition. We come back to our world, our income, fade into the world at night. There we are, the lights at night, a remarkable composite satellite image. Look where the lights are on. Look where they're off. Look at the energy mix that varies around the world. Oil, gas, coal. Take away and grow them. That's how much is actually consumed in those regions now. That's why the lights are off. Take away coal and oil. Take away gas and nuclear. And hydro has environmental impacts. Get rid of it, we got 6% left. If we just did it instantly. I can dim the world's lights by 94%. Here we go. How's that looking to you? Like the past, right? Not the future. The future, lights are on, and they are on in more places. Because we need it. 1 billion people don't have hunger, or don't have food, or clothing, or shelter, or water. Education and healthcare are another 1 to 2 billion people. Women are disadvantaged by energy poverty. They're cooking. They're going for the water. They're not in the schools. Population growth tied directly to education. Immigration, migration away from terrible situations and autocrats, investing in the environment, adapting and mitigating climate change. The big issues are addressed by secure energy. So what's the answer, Doc? I'll save you asking me the question. Okay. Well, nothing is written in stone, okay, except for this expression, which is carved in a stone. It's complicated. It's not binary. I can say that with confidence. There are a lot of things that go into it, and more than on my list. But I know that energy security underpins economic security. I hope I've showed that with data today that allows you to invest in the environment. And there's a tremendous amount of fear out there, pumping fear into young people and all of us about things, particularly climate these days. Just pumping fear, all right? The beginning of wisdom is to do away with fear. So we've got to, in unison, get rid of the fear. It doesn't solve anything. In fact, it makes it worse. Okay. Emerging economies need affordable energy. Developing economies need reliable energy. Developed economies, we want sustainable energy. And it flows that direction. We've got to accelerate economic growth. This might seem ironic or counterintuitive. Accelerate growth of everybody in the world so that they can begin to invest in the environment. I call that the radical middle. We've got to grow it, and we've got to grow it faster. Human flourishing and protect the environment. That's the challenge. That's our charge, and I believe we can do it. That's a framework for secure energy. So I'll leave you with some summary thoughts. Energy enables human flourishing. Many nations don't have it. Global demand will grow until population stops growing, which it will soon. No source of energy has gone down. All forms have environmental impacts, and we need a portfolio of options, just like in anything. And a couple musings, if you will. It's tough to negotiate with physics. We try, but physics wins in the long run. No one has a patent on truth. I sure don't. We're just seeking it. Keep learning. End the fear narrative. Civil dialogue is vital. Canceling. We have to think critically. We have to act wisely. And we have time to do that. We have time. That's the biggest point I want to leave with you. We have time. We don't have to do this in 10 years. We have to do it, but not in a decade. Okay. A lot of free resources, some films for you, the TED Talk out there, got a PBS show. Houston's going to start running in January. the last major network in the country that didn't run Energy Switch, talk show, 2 guests. Classroom materials for your K through 12 kids, other talks, a lot of podcasts. He was on with Jordan Peterson. That was a romp, as you might imagine. So you can put your phones up here and have access to these things and a lot more. And thanks for your attention today. Quiz.
Yeah, I'm going to do the quiz.
Oh, you're going to do it?
But you're going to be in the picture, so.
Oh, I am?
Yeah,
Coming up?
I'm coming up safely. Alrighty, so this was actually a contest. And those of you who had perfect scores, the first 10 of you can come up here and you're going to win a business card from me, a $25 Starbucks gift card, and then a picture of you with Scott Tinker. And so this is a contest then, and you're on your honor. No AI used here. So the first 10 of you who have a perfect score, please go stand with Scott in front of the screen there, and we'll give out the gift cards, and I'll have the business card. You can send me your email. It'll come back on an email to you. So let's finish the contests. I know we had winners here. So they're coming up. Let's move over to this side. I want to minimize the people breaking their bones on the stage here. I guess we'll do on the stage here, so.
Hey, perfect. Joe, we did good. 7. And we have 10 gift cards. Yeah, there you go.
And you get a free photo of Scott along with this Let's Make a Deal. Love it. Here we are.
What's that big black thing in your hands?
No, we want to have good pictures. So, yeah, no. I will, now, wait for the gift card. First, I'm going to give Scott his speaker's gift here. I'm blocking somebody's view. And then here is the ticket to your gift card. Send me an email. How much you charge for the business card? I know you, I'll send an email. Very good, send me an action. Okay. All righty. Another round of applause. We have time for 2 questions for Scott.
Are there any questions? Questions for Scott? Scott, there's a question.
Hello. Let me put it this way, that there's a $2 trillion pork barrel, as you know, in this country, and you won't be able to get any of that, as I see. So how do you make a living?
The question is, there's a $2 trillion pot of money out there, and with that talk, I won't be able to get any of it. So how do I make a living? I don't know. I don't make a great living, but I try to tell the truth, at least as I see it. And a lot of more people these days are doing that. We're starting to see, in fact, just in the Washington Post today, an article came out about the hurricanes. Shocking they published it. It's actually telling the truth about the 2 hurricanes, Helene and Milton, that they're not the largest. They're not bigger than ever. I think Helene was number 28 in the US in the last century. The reason that the costs are going up so much more is because there's more of us and we're building in the way of these danger. And I'm not trying to minimize the death and suffering that's gone on. I have a good friend in Asheville. It's awful. It was devastating. But it wasn't outside of norms other than what we've done, building in the way and building stuff that doesn't sustain these as much. So tremendous increase in costs, and I think we all need to start to tell the actual data. The IPCC is doing it, it's just not getting reported. What else? Yes, ma'am. To accomplish what? To accomplish what? Yeah, good question. You know, how does policy help to move us forward? And forward in this, my sense, would be toward that radical middle, acknowledging that there's trade-offs. First, we have to recognize there's not a single policy or set of policies that applies everywhere. I showed you the global variances in that, even within the states. I mean, Washington State is very different from Florida. Texas is different from New York, okay? We have different resources, different politics, different educational systems, et cetera, economies. So don't try to force single policies down on top of these. You're going to have more regional solutions and be good with those. They're not going to be perfect. It might not reduce CO2 to net zero, probably never will. But it might reduce it some. And in the meantime, we protect some water and land along the way. We don't blanket it with solar panels only. A blend of nuclear, natural gas, maybe some hydrogen, et cetera. So it's the policies that set some goals and then allow for those who are actually setting policy and regulating those policies to administer them in ways that fit the circumstances. And it's not, so it's more squishy. You just have to accept that people are going to do reasonable things if motivated to do so and incentivized to do so. Now, if incentives force essentially a mandate, you know, some states are masking mandates with incentives by saying you have to do this to get this giant incentive, and that this is getting rid of this other thing. That's a mandate. Then you lose options. And policies that reduce our options, again, markets like options. In order to scale any of these things, you have to have markets do it. Markets, you talked about TR9 or something, I think, Christine, from the DOE. I mean, by the time you're up at technology readiness level 9 or 10, markets are ready to, we'll start to implement some things. Markets have to do that. Governments can't do it all. And that's the Exxon example I gave you of incredible thing going on. They've been working on it a long time. I'm very proud of that effort. And also 6 hours of China emissions. Okay, so we have to balance those things off. Policy's tough.
Last question.
Yeah.
So you will be pleased to note what I noted when my phone beeped just now while you were talking. The UN released a report on the progress since the meeting last year when many nations promised to make environmental advances. So the report released today say they had made hardly any progress at all on any of their goals.
Yeah. Yeah, and you know, that doesn't please me. It saddens me. I'd like to see more progress being made, but I think COP, which is, IPCC is a Intergovernmental Panel on Climate Change, is a UN stand-up. And the UN is behind a lot of this. And the UN leader right now really has got to read more. Okay, things he says are nuts, sadly. But I'd like to see more progress coming out of COP or Davos or these other big global forums where a lot of very wealthy people who have the capacity and the influence to make change would get together and talk about real things and make incremental steps instead of setting up goals that are so artificial and unrealistic that everybody there knows it's not going to happen. Let's talk real turkey. Let's see what can happen. And I think the possible is really what I'm about more than you know, the ideal, if you will. And we see that coming out of the IEA in Europe more and more now too. Fatih Birol leads that. Just these things that anybody who understands energy reads this latest thing out of there and just goes, whatever. You know, that's just not going to happen. So more realism, more data, try to get more fact-based, and then more understanding of the complexities. It isn't simple, but it is solvable. And that's what a message I'd like to leave, particularly with our young folks who are going to be working on this for many decades to come. So keep up the good work, and thanks again for the invite.
Thank you. Well, that was delightful. We got an agenda here. We're going to try and move through this with speed and with clarity. And speaking about realism, we've got Seetharam, one of my colleagues here at the University of Houston, who's going to give two talks in one single shot, right, according to the agenda. So he's going to tell us about how to repurpose offshore infrastructure to drive the energy transition. So, Ram?
If I had known I was going to be following Mr. Tinker, I would have refused to talk. I mean, how do you follow up an act like that, right? Okay. Go ahead and advance a little bit more. So I'll pick up one of the musings or conclusions that Mr. Tinker left us with, which is you need optionality. And the optionality that I'm going to talk to you all about is energy transition offshore. A lot of what you heard today talks about how do you implement some of these projects onshore. You're going to need all of the above. And so what we're looking at here is what does energy transition look like in an offshore setting. And specifically, we have a program called ROICE that is part of UH Energy, and that stands for Repurposing Offshore Infrastructure for Clean Energy, driven by the fact that the Gulf of Mexico, even today, has about 1,500 plus platforms out there that are going to be decommissioned according to the regulations when they're done with their oil and gas life. And the idea here is, can we breathe some new life into that infrastructure for another 10 or 20 years, keep that economy going, especially for the Gulf area, by creating some new revenue streams through clean energy while we utilize those structures. And the structure specifically would be the platforms, pipelines, and maybe some of the wells if you're talking about offshore CO2 sequestration. And so that's the program that we're running. Our hope is to set up a demonstration project in the Gulf of Mexico using one of these platforms, which then allows all of you to come out and test new technologies in an offshore setting at scale. Our initial thrust is to support offshore wind or offshore wind to hydrogen and potentially bring that hydrogen back to shore using one of the existing pipelines. But there's other options too that you can look at for clean energy. We're exploring wave energy converters, of ocean thermal energy, floating solar, offshore CO2 sequestration, etc. So if you click to the next slide. While our current work focuses on offshore Gulf of Mexico, we are looking at other areas as well. But if you look at the Gulf of Mexico, it has been an energy powerhouse for past several decades, driven by the sheer amount of oil and gas developments that it has supported, starting with the shelf and shallow water and slowly going into deeper and deeper waters. So we have a large inventory of assets that we could explore the potential to repurpose. And then you've got things like a favorable wind speed patterns, very nice and ordered pattern, including some reasonable wind speeds close to the shore. If you look at California, for example, that's not the case. You're going to have to go deeper, further away from shore to get to reasonable wind speeds. But we're blessed with some good wind speeds close to shore, which means shallower water, and which means lower cost. And a very nice ordered bathymetry, a very nice shelf that extends out for several miles, and it takes a while before you get into some deep water. Again, that impacts the cost. So we need to leverage that infrastructure, and more importantly, the workforce. I think several of the speakers talked about how the skill sets that we have in the oil and gas industry are very transferable to the energy transition into clean energy, whether it's the geoscience skills or drilling skills for geothermal, project management. I mean, oil and gas has executed complicated projects, high dollar projects for decades now. Relatively speaking, the clean energy projects are less complex, less expensive, and we should be able to leverage that skill sets in order to be able to pull off these projects. And there's multiple options for these offshore energy technology, energy transition, as I said, and a few of them are listed there. Next slide, please. So what we've done with the Royce program is to set up the or at least I said done, we're not done yet. We're in the process of setting up the infrastructure to evaluate these clean energy options. As initially starting off with the Gulf of Mexico, but we're looking at the potential to expand this to California. We have some joint work with Harriet Watt to evaluate this kind of repurposing in the North Sea. In initial conversations with some Brazilian professors to see if there's potential for such repurposing in the Brazilian offshore as well. So our goal is to develop that methodology and to start putting the tools together, starting with the levelized cost model. Several levelized cost models exist out there, developed by the national labs, fairly comprehensive. And similar to that, we are adding in the repurposing piece of it. We're adding in the ability to evaluate different kinds of clean energy technology. A lot of the models out there are focused on wind. This one can handle wind or wind to hydrogen, and we want to be able to extend it to include CO2 sequestration, wave energy conversion, etc. So it's a combination of different parameters that go into ultimately determining the levelized cost. And then we've used that model to generate levelized cost geospatial maps like the one you see, which is for a 435 megawatt new build hydrogen export project. So given any location in the Gulf of Mexico, we're able to generate a levelized cost model for this, which means for any asset, which is all those yellow dots on there, we're able to determine where you have favorable levelized cost optionalities and where you don't. But the bottom line is, in general, offshore is expensive. So at today's costs and today's technology, for example, levelized cost ranges anywhere from $4 to $8 for a kilogram of hydrogen. And the equivalent, thank you. The equivalent clean hydrogen, whatever color you want to associate with it, is more in the range of $1 to $2 onshore. So you're adding a fair amount of costs moving this offshore. So there's some work that needs to be done to bring these costs down. And that's a general theme running through this to say, yes, we can bring offshore into the mix. It's not a technology readiness issue. It's more an economics issue, and things need to be done to make that better. And this is a comparison right there. The top 4 bars in each of these graphs, on the left you're seeing power generation, on the right you're seeing hydrogen generation, and you see the comparison to renewable power onshore and on the bottom there. And you can see most of the offshore options are to the right of what we're looking at over here. There is a bit of an overlap, and that overlap represents shallow water locations, favorable wind speed locations, etc. But one thing we should point out is this is based on 2023 CapEx. And as costs stand today, and no incentives applied yet. So right now, just want to say as is, what does that look like? What does that comparison look like? Similarly, on the hydrogen side, you can see that equivalent onshore electrolysis wind, electrolysis solar is more to the left. And then if you go with SMR, with carbon capture, or SMR, it's even more of a tougher competition. So you need those incentives, you need cost reductions, you need improvements in performance, greater amount of hydrogen produced per kilowatt of energy, for example, electrolyzer improvements, or greater amount of kilowatts produced per meter per second of wind speed, improved turbine designs, etc., that will help us get to. And this is an example of the kind of improvements you could see in this levelized cost with cost reductions as well as performance improvements. We just took a small 10% improvement in cost and a 10% reduction in cost and a 10% improvement in the performance, and you're able to see about 15% reduction in the levelized cost. So technology is important. We need to find ways to make electrolyzers and turbines. Turbines are the biggest cost element there. So if we can bring those costs down, the general feeling is that costs of turbines today are more supply chain issues rather than actual material, mostly because a lot of the components are not manufactured in the US, cable costs for cables, for example, or the turbines themselves. So when all of that starts to scale up with the East Coast wind projects that are being implemented right now, and a greater amount of wind projects onshore as well, some of those costs are bound to come down. And similarly with electrolyzers as well. We've seen that kind of significant reduction on the solar panel side, and you could expect similar cost reductions happening for wind turbines and electrolyzers as well. But we need all of those, and we need better incentives to be able to make this competitive if you want offshore energy transition to add to the optionality that Mr. Tinker talked about in his previous talk. So what are the keys to profitability of these ROIS projects? We need improved energy output from performance and technology improvements. We need an optimal combination of clean energy options. One of the things we're going to look at in this project is to say, maybe it isn't just one technology out there on a platform, it's a combination of technologies that will give you a profitable option that will let industry come in and start developing these. We're finding that scale is important. The larger the project, I mean, again, you all have heard of economies of scale. The larger the project, the better the economics. However, if you're going to be placing these projects on offshore platforms, your footprint limited. So you have to make sure that you maximize the size of project that you can put on any given platform. And that's some of the work that we're doing as part of the project. Hydrogen takes up a lot more space. A power export project doesn't require as much equipment to be placed on those platforms, so you can increase the size of the project. We need this green premiums and offtake incentives. We've taken a look at modeling the impact of the PTC, ITC credits, as well as 45V credits. And yes, definitely it helps. In fact, it's needed. But it's not sufficient at this point, today's cost, to make it competitive with onshore alternatives. So we're looking at potential ways of identifying the kind of incentives that are needed and coming up with practical ways. For example, using clean energy projects like this to incentivize decommissioning of these assets and allowing for a proper transition from oil and gas over to clean energy, and adding some incentives for that kind of transition. And then we need CapEx reductions. You need anywhere from 30 to 50% of CapEx reduction from today's CapEx, which is a big ask, but it has happened in other industries over time as industries develop and the volume of the installations increase. Low-cost loans. The CapEx required for these projects can be quite significant, and so to be able to borrow that kind of money at low-cost loans is another way of helping the profitability of these projects. methods. So that's what I had. The bottom line being, you need a little bit of all of the above, and we're looking to see if repurposing and a combination of clean energy options helps us put together a viable alternative. And I'm here to say, as of now, we haven't found a solution. We'll keep working it, and we'll look for the right combination of technologies, incentives, and other optionalities to try and make some of these projects more profitable and add to the energy transition mix.
Thanks, Ram. We can open it up for some questions.
Yes, sir. At this point in time, we're not, so that's part of the mix that we're looking at. For example, can hydrogen as a battery to solve the intermittency problem for wind power export. Then hydrogen storage and fuel cells, et cetera, are an option. And so we're going to start adding those options into our model here. Otherwise, the point right now is assume that you can send intermittent hydrogen, and then there's line packing in the pipeline that you could use as storage as well. So those are the assumptions we're making at this point. We have not included storage as such. More cost, more footprint, so you have to factor that into. Yes, yeah.
Well, thank you so much, Ram. Appreciate it. Sort of an inside sort of secret for all of you. Milind and Ram were classmates as undergraduates, and and as grad students.
And as grads. So we did our PhD together at University of Houston at the same time. We joined university together, graduated maybe a year apart under the same professor. So, and we did our undergraduate work under the same professor as well. So we go back a long, long ways. So it's nice to be back in touch with you guys. Exactly.
So if nothing else this conference achieved, it's got a reunion happening. The next talk, and Joe Powell is my colleague here at the University of Houston. He is leading the Energy Transition Institute, and as you'll see, he is a boundless source of energy for all of us. And so Joe, such a pleasure to have you here. Talk about the hydrogen economy.
All righty, well, super. Thank you, Ramanan. As Ramanan indicates, I've been here about a year and a half, but teaching a hydrogen economy course for about 3.5 years. And I'm going to really talk today about geosciences and I guess I'll call it now the so-called energy transition. And so how do the two overlap, regardless of the different scenarios that we will be coming up with. And so you heard during lunch that those scenarios can vary widely. And to get into the talk, we'll talk quite a bit about the steps, which are the stated policies that the IEA is looking at in terms of the way forward in energy. But then there's also the pledges, the promised pledges. And so we've been running experiments since COVID or so in terms of what is really happening out there in the marketplace with the pledges. Well, here we go. That's me. And I call that sort of the heaven on earth. And so if you look at what's happened over the last few years, various companies have made commitments over and above what the policies will support in terms of decarbonizing, but they haven't really been rewarded in the marketplace. The marketplace really doubles down on the economics that go with the policies. And so that's been something to keep in mind in terms of going forward about how do we really move forward with the policies that we need to succeed in this space. And then there's the net zero. You'll see a lot of net zero by 2050 slides. And that is what you would have to do to get to net zero. But we've got no plan of how we're going to do that currently. And so that's strictly aspirational, and keep that in mind as we go forward. So again, I lecture at a hydrogen economy course. I give a lot of slides, and so you'll get copies of these. Don't worry about taking notes on the slides today. I'm also running the hydrogen mobility pilot for Christine. And so reach out to me if you want to sign up to be looking at fuel cell mobility options in the Houston area. We're forming a group. We've got a DOE grant. We'd love to have you join us. So we've already heard this from Scott. Industrial revolution was coal. We've moved away from fossil fuels as an aspiration, but they still underpin our economy, and we're attempting to grow our renewable energies as a way forward in this energy space. The key issue is that as we move to renewables, they're not storable, and that's where the challenge lies in. This is the net zero plan of how we will transition away from oil and gas and be adding those renewables. There's a lot of technology change in there. For the first time, we're making electricity directly from wind and solar. We don't have to burn a fuel, go through the Carnot inefficiency. And so that's really great, but it's great for instantaneous energy. The problem that comes in is the high cost of storage as we try to balance this in our economy. Where we've come from is that most of our energy is coming from about 9 large basins in the world, which are traded internationally in terms of coal, oil, and gas. It's going to change going forward. On the upper left, you see where the high renewable intensity, the combination of wind and solar and capacity factors exist. It's not in the same places in the world where we're getting oil and gas. In the middle, you see again an energy density plot. You can barely find the lithium-ion batteries. The fuels and vectors that we are using have much higher energy density. And so you can look at this opportunity space as how do you use those vectors to get renewable energy transported and stored across the world. This lecture is about hydrogen. Hydrogen is one of the best of the vectors. I tell my class, electrify first if you can, but when you need the storage and when you need the transport, hydrogen is the next best vector because you can make it cleanly and you can use it cleanly. And so we'll talk about that as we move forward today. This is that latest Outlook 2024 from the IEA on the World Energy Outlook. And you see, again, the steps scenario on the left there. We're hardly changing our oil and gas demands currently in terms of the response to the stated policies. The APS, the stated policies that have no really economic underpinnings. So that's saying, I want to be good. I'm going to quit drinking and gambling. Be nice. We're going to end wars. We're going to essentially deal with poverty. All the things that we pledge we want to do. But if you don't have policies to underpin an economic value to those pledges, we're good at pledges, but we don't always come true with our pledges. So that's what the middle ground is there. And then the right is the net zero emission scenario. So a poll was done in the developed world, I think it was in the US, of how much were people really willing to spend on dealing with climate change. And it was about 2 dinners out a month for a family. But when you look at the cost, it is half of your discretionary income. And so people have not really come to grips with how expensive it is to transition to net zero. So keep that in mind with the policies. What we see on the hydrogen side, on the right hand, is that the blue line there, deep blue right underneath the light blue, is the anticipated growth in hydrogen. And what we saw coming out of COVID was a lot of interest in hydrogen as aspirational, but after looking at the cost factors, it's really waned slightly in terms of ability to commit beyond the pledges to deploying those options. Case in point on the left, so it varies globally. Currently, if you look at gas prices in the US, I drew in the red line there for $1 a kilogram hydrogen. That's the DOE's goal for what the hydrogen price we want to get to. It's currently significantly higher than that. But if we get to that price, that's $8.8 a million BTUs. That's extensively above the natural gas price here on the Gulf Coast. Without policies, you just can't afford to be paying 2.5 to 3 times more for energy. You'll go out of business because global competition is absolutely brutal. If you look at the middle in terms of the prices in Asia and in Japan, you find that they're relying upon imported LNG. Their energy prices are high. you can almost afford to have hydrogen as a vector there. So as a consultant on global projects, I see people putting in either green hydrogen via electrolysis to ammonia to be shipping to Japan from energy research regions, or blue hydrogen, which could come from the Gulf Coast with methane, natural gas reforming, and carbon capture and storage, but shipping it to Japan because that's where the policy incentives are for uptake. If you look on the left, I worked on biofuels for 10 years at Shell. Shell spent $1 billion on it back when we thought oil prices may be $100, $120 a barrel. They're never predicted to come below that again. Why? Because of fracking, light, tight gas and oil. We've unlocked that, and those, we will always have to have an incentive to implement biofuels in the US because of that. And so think about that in terms of the policy. Hydrogen as that opportunity space. We've already heard about natural hydrogen this morning, and so we don't need to talk about that. There's actually several forms of it, from the orange of injecting water to induce some of the hydrogen formation, to the white, which is already there, and then to the gold, which is the microbial conversion of hydrocarbons in the oil wells that exist. So many different approaches to what the subsurface geologic hydrogen can be. People are talking about, well, what's the best way to make it today? Should we be reforming natural gas and doing CCS, or we should be moving to the more expensive renewable electricity and doing electrolysis? So about 2 years ago, it was nearly even. And in the earlier scenarios that I had showed you, it's really tipping a little bit more towards electrolysis and renewables than the natural gas. So here's the DOE's plot of how we're trying to get that at $1 a kilogram hydrogen. There's the cheat sheet for my class. $1 a kilogram is a gallon of gasoline equivalent in fuel cost, but it's also $8.8 a million BTUs in terms of natural gas. So you have to keep those factors in mind in terms of looking across the space here. We've heard this morning the IRA has passed very supportive legislation in terms of supporting low carbon hydrogen, but the scales tip a little bit towards the electrolysis versus the natural gas and reforming because the way that that was written and credited. And a big part of the issue is the methane emissions in the natural gas supply chain. And so what the producers have to be doing in order to make that effective is really tighten down on those emissions and then giving credit for it. Because methane has up to 25 to 100 times more damaging global warming potential than does CO2, depending upon your time frame, and small leakage rates can be an issue. Very controversial studies being published out of academia and around the world on what those emission rates are. This is a group that I've worked with across the world who's kind of a balance set, and they still see it's really borderline for natural gas reforming unless we really tighten down on those emissions and move with advanced technologies such as partial oxidation for the reforming of the methane, where you can capture most of the CO2 coming out and get really high capture efficiencies. It can also impact where do you want to produce the oil from, because what you see now are companies are going in and picking their prime plays basis the lower CO2 footprints. And so if you look at what the emissions are as a function of where you're producing oil and gas from, offshore tends to be lower in terms of CO2 footprints and methane emissions. And so you see companies really right-sizing their asset bases in order to be looking at and doing it. One of the things that hydrogen can be really good at is a storage vector, not just for a short duration, but also seasonal. So speaking of Utah, that has one of the brand new salt dome storage sites. So California is trying to decarbonize with renewable energy. They have no salt domes. And so there is one in Utah, and you can actually grid that energy that far between Utah and California. And so that is one of the new plays in terms of salt dome storage for hydrogen. So that's something that those of you in the geosciences can focus on. Here's a map in the upper right about the salt areas within the US, and then the various salt projects there in the middle. And we are blessed with some of the best salt in the world here around the US Gulf Coast. And so if you look at, this is now that purely speculative net zero emission scenario in terms of how much hydrogen transmission can be occurring, and also underground storage of hydrogen using these geological formations. And so opportunity space from a growth in demand. Also looking at carbon capture and storage. Also now, this is again that net zero emissions roadmap. We don't have a clue to how to get there, but if we did get there, there would be a lot of CCS, and there would be a lot of hydrogen manufactured by that route with carbon capture and storage. Opportunities to keep in mind. This is the Net Zero America study from that was Princeton University, and you find amongst the various opportunities for sequestration, most of it is really coming along the Gulf Coast because of the opportunity to play in the depleted hydrocarbon reservoirs. There's a map from Scott's group on what some of that looks like in our area here now. And managing how you do that. So induced seismicity, a good calculation and approach from my colleague Mark Zobak at Stanford on how you can perhaps succeed at predicting what some of that seismicity will be, and perhaps the mathematics isn't that difficult. We know a lot of the geology in these depleted reservoirs to be able to manage those issues. Now people say CCS hasn't been done. You know, I work for Shell, and we've been doing it for up to 7 years now at a million tons a year, and did it quite successfully. There was a little bit of cost overruns on the engineering side of the construction, but the injectivity and the lack of seismicity was done well. And so hopefully we got the geology right, but I think it's really, really important if you want to do a CCS project, you got to know what your injectivity and seismicity is. You cannot build a surface facility and then not be able to inject and store, because the costs just go out of the roof if you have that. So you really got to be able to predict the geology and the injectivity with high accuracy in order to make that happen. This is another plot from the looking at commitments. Again, the top bar is the stated policies. We don't have too many. The pledges, if we're going to live in an ideal world, we could have more. And if we really wanted to get net zero, we would have a heck of a lot more even pledges. And the bottom line here is CCS plays a very strong role in that play, and hydrogen is a big portion of where that CCS is coming from. I'm also on a National Academy study team about carbon capture utilization versus storage. So you geologists may worry, well, maybe we'll utilize it rather than storage. But you thermodynamicists, I would say, it takes a heck of a lot of energy to turn CO2 into a useful hydrocarbon. And it may take something like 4 times the number of solar or wind farms versus just electrifying. And that shows up in the National Academy report. So you may find CO2 utilization, but you're probably better off decarbonizing the grid first. And you would probably consider storing it first, because it takes a lot less energy to store it than to try to convert it into a useful material. Decarbonizing chemicals, carbon capture and storage comes into play there. Again, a good geologic play. Negative emissions, so people don't like pipelines, they don't always like CCS, but they love negative emissions, even if that requires pipelines and CCS. And so that is something that, because the thought of taking it out of the atmosphere and making it happen is really attractive to the population. So to make a summary short, there are good blue hydrogen plays today to be moving clean hydrogen from natural gas and CCS primarily to Japan as a market. Certainly CCS is a challenge. You better get the injectivity and seismicity correct in your project, or you'll be in trouble. Direct air capture is quite an option at a Sustainable Aviation Fuels conference. If you look at how expensive it is to produce sustainable aviation fuel from CO2 or even some of the bioresources, you could consider just pulling it out of the air and using petroleum and taking that offset, because the two are starting to get close together in overall cost. You've really got to worry about the methane emissions if you're managing that natural gas supply chain to be competitive. Hydrogen storage in salt domes is wonderful for that seasonal, and do that where you can. And always electrify first, but hydrogen is the next important vector. So to quote from, I think, a Mad Magazine exercise, the good and bad. I don't know who of you took the Mad Magazine back in the 70s, but you always say there's a good side and a bad side, but if you're in the geosciences, you win either way, because either you're producing a lot more oil and gas continuing, or we're going to go way over and do a lot of capture, sequestration, but hydrogen will be in the middle of that in terms of an energy vector playing there, and also in the subsurface storage. So you can't lose by being in the geosciences. That's my talk for today, Ramanan. I didn't do too bad.
You did good. Good timing. I wish we had more students to hear that they would all should go sign up as geoscience majors. So it is something that we should take to the high schools. It is a big challenge, as everybody knows. The pipeline coming into petroleum engineering and geosciences continues to be a challenge. So Joe, once again, thanks a lot. We do have another Powell to follow Joe Powell, and that's Cody Powell. And Cody is from the University of Utah, and he's going to tell us, and he's got the right degree. He's a chemical engineer. He's got the right background. So he's going to tell us a little bit about decarbonization, working smarter, not harder. So love that. So thank you.
Thank you very much. So we've heard some really big ideas today. I want to set expectations for my talk. I'm hoping to be the second best Dr. Powell you'll hear from today. So I'm Cody. I'm talking about working smarter, not just harder, pathways to the energy transition and decarbonization. At the University of Utah, I was born and raised in Utah. I spent about 7 years in Texas, though. I did my PhD at UT Austin, so I think Dr. Tinker would know my PhD advisor and committee members pretty well. Then I worked for ExxonMobil. I'm a downstream guy. I lived in Humble when I was here, and I called it Humble when we first bought a home and moved here. And eventually, of course, I was corrected. No, it's Humble. And I couldn't figure out why, but I eventually realized you're not allowed to use the word humble and the word Texas in the same sentence. And so that's why it's Humble, Texas. Anyway, very grateful to be here. I do miss my time being in Texas. Love it here. Okay, so I'm going to talk about, my work is energy systems analysis, so I'm kind of a jack of all trades and master of none. We're doing high-level energy analysis, looking at complex systems and how we get all this stuff to work well together. So we've heard some similar themes today. So I'm showing data from an NREL study on the declining cost of solar. So this is probably not a huge surprise to anyone. Over the last, this study was dated from 2010 to 2020, and so we saw the installed cost of solar photovoltaic technology come down by nearly an order of magnitude. So that is pretty phenomenal. So pop quiz, someone's got to know this, especially after hearing Professor Tinker speak. Which state in the US has the most installed solar generation capacity? It's actually not Texas. It's California. It used to be California by a pretty wide margin. Texas is catching up fast. So here is a map of the United States. This was an article I just pulled as I was preparing for this talk. So very recent. This is from Forbes magazine. And it's they put together this this system with different metrics for which are the best states to install solar power, which states are doing the best at solar. So it's color-coded, where white means you're the very best state for solar power, and then as you go to the kind of orangey brown color, that's burnt orange, I guess, then those are the worst states for solar. So you can see in the southwestern US, obviously this is a place where we get a lot of solar intensity. As a person from Utah, I am actually pretty jealous of California. They are taking advantage of all of this really cheap solar. So this has got to be working wonders for them. So let's check in. Professor Tinker kind of gave away the answer here a little bit. So let's see how this really cheap solar is impacting the total price of electricity in California. So this is the average electricity price by state, and as you can see in the western US for sure, California is a very clear outlier for the most expensive electricity. So there is obviously some kind of a paradox here that as scientists and engineers will figure this out pretty quickly, and I'll give kind of a hand-wavy quick explanation for why this is happening. But if you look at California installing all this solar, if you look at all the neighboring states, California is at least double the total price of electricity, and this is levelized costs. This is probably familiar for all of you, and I'm a downstream guy, and I have my research now is renewable, so I don't speak the geoscience and subsurface language, but hopefully you guys are learning to speak this language a little bit. So most of us have heard of the duck curve. So what this curve is, this was we started seeing this in about 2012. They started forecasting if California keeps installing solar at these really rapid rates, what does the net demand look like over the course of a typical day? And so that net demand metric is on the right. That's the grid demand minus wind and solar generation. So California has been very aggressively installing solar. So that duck curve is now becoming the canyon curve. It's getting so deep that during the day, during the shoulder seasons, like in spring and early fall, they're actually seeing points of the day where they are overproducing solar. They're producing more than they're consuming. So one of the reasons, and this isn't an anti-solar talk, again, I'm looking at the mix, looking at how do we get all these things to work together. We're just pointing out some facts. One of the reasons that electricity has gotten so expensive is that you essentially have to build two different energy infrastructures here. So you have the solar energy infrastructure that's generating, of course, when the sun is shining. Then when the sun goes down and your net demand starts to shoot back up, now you're relying entirely on other technologies, and a lot of that is fossil fuel. I loved the discussion of the hydrogen storage project in Utah. We're exporting electricity into California. So you've got, I guess this laser pointer probably won't work. So you've got the solar part of the day, and then you've got the other parts of the day. So you have to have these two energy infrastructures. We've certainly seen this, so we've done studies in Utah has a lot of coal power, so we have partnered with some of our coal-fired power plants to do studies. We've actually been developing technologies to help coal power plants deal with all the fluctuations that come from the changing market that's caused by renewable energies. So this is one of our power plants. This was actually my hometown of Huntington, Utah. We looked at data from this power plant before, that's the data in the red, and after our utility entering the California energy imbalance market. So at some point in between there, these power plants started pushing more power into California and ramping up and down to shore up what's happening in California. So it's pretty easy to see that we were mostly base loaded and keeping a pretty steady rate before entering the energy imbalance market. So since then, now we're seeing these coal power plants do this tremendous amount of ramping, and they're ramping deep and they're ramping often. So what's happening with the renewable energy market is certainly impacting what's happening elsewhere in our fossil fuel assets. Again, I mentioned this is where I grew up, this power plant. This is where my dad worked as a little kid. When I was a little kid, he wasn't a little kid. We had normal child labor laws there. I was a little kid. This is where my dad worked. So this place is kind of near and dear to my heart. And now we're dealing with this. We're trying to figure out how does this place transition. So one of the, again, I'm not trying to be pro or against any particular technology, just pointing out things that we're finding in our research. But one of the cool takeaways from this is that these coal power plants are actually they're enabling renewables. They're providing that reliability. So we're seeing that the capacity factors of these power plants are pretty low, and that's often something that the critics point out is that capacity factor is low. And I would actually say these power plants what they're selling is flexibility as much as they're selling power. They are the ones that are helping to maintain voltages and frequencies on the grid so that supply and demand stay in equilibrium. So my research group, we have done some studies. I just sort of picked out some of the topics I wanted to cover for today. So we did a study where if you took a greenfield place and you could just design your energy system from scratch from a combination of sort of the most ubiquitously available technologies. So this would be solar, wind, natural gas combined cycle power plants, and then battery storage. How could you build your energy system to minimize your cost of energy? And we did this for different areas. So because we're in Texas, I'm showing data from Texas. So we, on the x-axis, you'll see the renewable energy fraction. On the y-axis, you'll see the levelized cost of electricity, and I'm showing the levelized full system cost of electricity. So we're not showing that super cheap solar. We're saying what would it take to build this entire energy system for this place. The lines going up are if you applied different CO2 taxes. We just wanted to look at some way to help incentivize getting more renewable energy on the grid. So what do we learn from this? Well, all the dots are the optimal point. That's the point where you get the lowest levelized cost of electricity by renewable energy fraction. So the story here is actually pretty cool. Because of that cheap solar and cheap wind, you can get pretty high renewable energy fractions without dramatically impacting the total cost of your system. Then, of course, as you hit about 70%, and as you go above that, then the costs start to really skyrocket. And so as a chemical engineer, this is an energy balance problem. And essentially what you're doing on your system is you have to build so much solar and wind capacity that when those energy sources are available, like in the summer or in the shoulder seasons, you have overbuilt this plant so much that you are able to store up energy and save that for the fall and for the winter. So, and then you've got to be matching this exactly right every year, either or you've underbuilt or you've overbuilt. So just the costs of doing that get astronomical, and you end up, if you have overbuilt, then you end up having all this extra energy that you never use. And if you have underbuilt and you have a fully electrified system, I think people die. That sounds dramatic. I'm coming from Utah, where we all rely on natural gas to heat our homes, and we have very cold, snowy winters, and we don't see the sun often for several weeks at a time. So if we have fully electrified and decarbonized, if we don't have that electricity available, then we're not able to heat our homes. So, so there are just some trade-offs here. I think there's a really good story. We can get really high renewable energy fractions, but I still think we're waiting for those technologies to come along where we can fully decarbonize. And I think hydrogen is super promising as a long-term energy storage option. So what we have done historically for the last century or so is that when we need more power, what do? We build more power plants, and that's sort of all we do, and there hasn't been a lot of sophistication to what we're doing. We need more, so we build more. So I love this quote. I'm not sure if it's an exact quote from Albert Einstein, but it's often attributed to him. He says, we can't solve problems by using the same kind of thinking we used when we created them. So as we go through this transition, there's certainly some kind of a transition happening. It feels like it's different all the time. I mean, we're hearing about power demands maybe doubling in the next decade because of the big AI boom. So this is all very new developments. We're hearing about Google and Microsoft investing in nuclear power and resurrecting the 3 Mile Island project. So it's really hard to keep up with all of this stuff. But I think it's critical that as we do this, we try to be intelligent about it, and we don't just build more because we need more. I think we should do this much smarter. So we have this vision. One of the ways that you can help to lower the cost is by making your energy use much more flexible. So one of the aspects of my research is looking at industrial load flexibility and finding built assets out there that are that can be very flexible in the way they use energy, that could respond to some kind of incentive program or some kind of real-time signal from the grid to change when and how they're using energy. And I think the when part of that equation is becoming much more important. When you use energy is becoming much more important even than how much energy you're using. So what we've found in surveying a number, I run a DOE center where we do energy assessments for industry. So what we find is often that industrial facilities, they have some kind of a process that is flexible, that they could reasonably shift when it's using energy without dramatically impacting their production process. So in this little animation, you see that one of the industries on the far right has a tank that you can fill that tank up or discharge the tank in response to how energy is changing. Or if you wanted to get a little bit more into it, you could have a process that's actually ramping up and ramping down based on energy prices. So in our center, we try to find these opportunities where companies can do this economically. This is not meant to be a replacement for energy storage. I think we're very much going to need active energy storage. But this is some low-hanging fruit where if we just operated a little bit more intelligently, we could have a pretty big impact on grid operations and helping this supply-demand mismatch issue. So I'm showing you, this is hypothetical data for, this is an industrial demand profile. So I've seen the electricity bills for hundreds of facilities. Typically, especially in our area, their billing structure is somewhat crude, but on their bill they have a charge for their energy, so that's dollars per kilowatt hour. Then they have another charge for their demand, which is measured in dollars per kilowatt. So, and typically the dollars per kilowatt charge, that is based on your highest power demand within a month, the highest 15-minute power demand. So you could be pulling 3 megawatts for just a single 15-minute period, and that can set your energy demand cost. So this can be astronomical for some facilities. Typically, that's about 50% of the energy costs. But if your facility starts doing things like shifting when you're using energy, you can dramatically reduce your peak, you can fill in those troughs, or you could be actively responding to signals from the grid. So this is just one of my favorite pet examples. We visited a facility that does mineral processing. So they need quite a bit of water to feed their process, and they're pulling that water from underground wells. They store that water they have about 6.2 million gallons of water storage capacity, and then that feeds into their process. So they invited my team out to do this energy analysis. They were particularly interested in solar. So they said, we want you to model what it would look like for us to install solar here on site. How does that impact our bills? So I've plotted their actual energy usage in blue, and then their net demand in yellow, so you could see if they installed solar. Certainly that's bringing down their total energy demand. So this is for one week of operation, and you don't have to say this out loud, but look at where the peak is on that graph. So the peak is right about there. The sun is not shining at that particular moment, so the solar does nothing to reduce their peak demand. It's going to save them on the kilowatt hour part of their bill, but not on the kilowatt part of their bill. So what we suggested to them was, hey, you have this process where you are pumping water from the ground into these big storage tanks. Their pumps were pulling about 3 megawatts, and their tanks could hold 6.2 million gallons. That was equivalent, I believe it was equivalent to several hours of storage, and this is an asset they already have. All the pumps already have variable frequency drives on them, so they can ramp them up and down. So we did this analysis to tell them that, hey, you could essentially use this water storage and your pumping system like a battery. You could fill up the tank when you're off peak, and then you could drain the tank, turn down your pumps. So we discovered that they could reduce their peak demand by about 2.5 megawatts by doing this. We ran the economic numbers for them, looking at the different prices, so you don't have to look at all these in detail. We looked at what are they doing, business as usual, if they installed solar. So that second row, if they installed solar, we estimated that would be a $7.6 million project. It would save them $270,000 per year, and that would have a 28-year payback. So you saw the pictures of the solar panels degrading. Solar panels don't last 28 years, so this would be a net negative NPV project. Batteries make it better because you can use the batteries to actively shift your peak. The batteries bring that payback down to about 11.5 years. If you look at that second to last row though, doing this intelligent pumping is just instrumentation and controls and just operating more intelligently. And so we found with about a $250,000 project, they could be saving $370,000 a year in their peak demand charges, and that's a 0.7-year payback. So this project doesn't have quite the same flashiness and PR attributes as having big shiny solar panels on your site, but this actually makes the most economic sense. And then what you're actually doing is you're supporting the grid. So you're helping to enhance grid reliability. so that someone somewhere else can put solar panels on the grid. All right, so I'm going to wrap up my talk. I mentioned my group is covering a whole bunch of different things, so I just want to highlight some of the different research projects, some of the different research questions that we're focused on answering. So we do a lot of work with hybrid energy systems. I'm a big believer in hybrid energy systems. I don't think you should build a solar plant over here and then build a fossil fuel power plant over here if you can find ways to make those synergistic. So we have done work with solar thermal power and found that if you couple a solar thermal power plant with a natural gas power plant, you actually end up extracting more solar energy because combining the two lowers your capital costs. It gives you a lot more degrees of freedom over which you can optimize so that you can actually find the global optimum. We have done some work with those same coal power plants. We actually have developed software that is actively controlling 2 about gigawatt scale coal power plants right now. So our algorithms are making decisions on about 100 decision variables that normally an operator would have to decide. We are working on minimizing emissions and reducing the coal consumption. So our algorithms save enough energy for the coal power plant to power the server that runs our algorithm. That's a joke, okay. So we actually, our software at these power plants is actually saving roughly $2 million per year in coal costs, where we're just trying to operate those coal power plants more intelligently using some of these great tools that are coming from the tech boom. We're running scenarios. Can we realistically transition to 100% renewable energy? That was the slides I showed you early on, and what we found is that it gets very expensive. You can do it cost effectively up to a certain point, and then it gets really expensive. And I think we need researchers who are actively figuring this stuff out, especially that issue of long-term energy storage. We're looking at industrial decarbonization. We're looking at nuclear power. I'm actually pretty encouraged that these tech companies are investing in nuclear. I think that's absolutely something as a society that we should be pursuing. We're looking at electrification. What does it take to really, truly electrify a whole city or a whole state? Long-term energy storage. Can we harvest renewable energy from food waste, and looking at the life of batteries. So at EGI, we are actively researching a lot of these different topics, and I showed you just kind of a slice of some of the things that we're working on. So in conclusion, I think we need to operate smarter. We shouldn't just say our power demand is going up, we need more power plants. I think first we need to figure out how do we operate all of these assets more intelligently, because maybe there are scenarios where we don't have to build those power plants because we have improved our efficiency and we've improved the intelligent way that we operate these systems much better. I do think we will need to build, of course, especially as this AI boom continues, but I think we should build intelligently, and you're certainly seeing this in the types of designs of power plants that are being proposed, where they are power plants coupled with energy storage. And then if we are going to be transitioning, we need to be doing that thoughtfully and intelligently. I would definitely want to thank all the sponsors of our center and EGI. Huge thanks to the University of Houston folks for having us here today.
Thanks so much, Cody. We're probably running out of time, so I'm going to quickly move to the next talk here. The next one is also from the University of Utah. Sorry if Cody is going to be around, so please, we'll get some questions to him directly. But in the meantime, let's get started with Masood. Masood is also from the University of Utah. We're going to take on this thread about AI and grid resilience. So, Masood, thank you.
Yes, thank you. Good afternoon, everybody. So I think we should wait a few minutes for for the slides to come up. But yeah, so while we are waiting, so my name is Masood Parvani. I'm an associate professor of electrical and computer engineering. So like they mentioned to Cody, that's from the good degree. So I'm hoping that electrical engineering is also like the good degree here. So, but we work very closely with Cody and EGI and all the colleagues in the room. But it's coming? Oh, okay, that's great. So, again, so my name is Masood Parvani. So today I'm going to talk about a little bit about like resilience, the topic of resilience. Which is the grid resilience, which includes of course, like resilience against extreme weather events, but also resilience towards long-term changes that is happening on the grid, including the change in the generation mix, plus like the integration of new types of loads and resources on the grid. So specifically, I'm representing and I'm the director of this new NSF center that we just established in the University of Utah last year. It's called US-Canada Center on Climate Resilient Western Interconnection, or NSF Wired Global Center. This was funded as part of NSF Global Center program, the competition that NSF ran last year. They only funded 7 of it. We were one of them. NSF was response to this NSF Global Center program. NSF was looking to establish centers around energy and climate, that very broad topic internationally between US, UK, Canada, and Australia. So it made sense for us to propose something with Canada, because we share the Western grid, which is called the Western Interconnection with Canada. And we have the same problem. They are dealing with extreme weather events. We deal with the extreme events and also impact on the grid. And we are working on the same problem. We have the same expertise, but working across the border. So it made sense for us to bring this together. Working together, we have 11 universities. This is co-funded by NSF and NSEC in Canada. You see some of the academic 11 universities, but also we have a lot of power utilities in the West, plus some government agencies, including WEC, and also US Forest Services, FEMA, and some of the other agencies that are working with us. So what we do, we look at the 4 major activities here: use-inspired research, climate and grid data infrastructure, community engagement, and innovation. We are developing an innovation ecosystem for commercializing the resilience technologies we are developing. Okay, so this is, oh yeah, movie. So extreme weather events, it's not climate change. So we are not we are not talking about the change, climate is changing or not. As long as things are happening, as long as we have heat waves, as long as we have hurricanes, as long as we have storms, we just need to make sure that grid is resisting and is withstanding some of those, and being able to power the communities as it has done in the past many years, right? So it's not about we are not advocating for changing climate, but we just want to make sure as long as the extreme weather happens, we are securing the grid against this. The grid is resilient against it. So these are the maps that are past. These are not future forecasts. These are the maps of things happening. As you see, things happening in the West are different from things happening in the South and in in Texas. But we are all dealing with similar things, right? So there are problems here on the on the climate side, on the weather side, and whenever it happens, whenever anything happens, the first thing it impacts, the grid is on the news, right? So the grid is on the news, and we are hearing about the fact that this many people don't have the power. So we just need to make sure that as long as things keep happening, we are making the grid resilient against that. In the West, the problem is different. We don't get hurricanes. We get a lot of wildfires, and we get heat waves. Specifically, heat wave is something that is has been in in the center of attention the past 5 years, since 2020 almost. The first one, the first graph here, kind of the map here showing the map of the Western US in 2020 August, and down there it's showing the kind of the same on another day, September 2022. So what's happening, you see that almost all major cities on the West are above 100 degrees on a given day. And it's not just one day, a few days before this, few days after that, that was the case over there. So what's happening is that this is putting a lot of pressure on the grid. So grid is not built to, a grid of the West, it's not built to tolerate this much of heat all over the West, and for a longer period of time. So what's happening is that this was very eye-opening for the grid. We call it silent killer. It's not impacting the grid immediately like hurricane that is like putting down the whole grid, but it's like impacting and putting a strain on the grid. Specifically, you see that these are some metrics that are published by Western Electricity Coordinating Council that are showing like how the grid is impacted in terms of the number of like interruption and the duration of interruption in those specific 2 quarters that I just mentioned, 2020 and 2022. As you see, like just because of heat wave, there was nothing else happening. Like you see a lot of like increase in the like number of like outages and like frequency of outages. So we just need to work on that, right? That's one of the problems we are working on in the center. But the way we are looking at it, we are taking a data-driven approach. We are not just like stipulating the future. We are looking at a lot of data. One of the things we are developing in the center, we call it weather and grid data cyber infrastructure. One of the challenges when it comes to like studying the like extreme weather events and their impact on the energy to power grid is that we need data. We need high quality data, and it turns out there's a lot of data. But the weather data are some of the like largest data you can imagine. But one of the challenges is that how like engineers who don't necessarily use those data in everyday kind of like type of practices we do. In our studies. So we developed this like a cyber infrastructure that is shared between the institution across the West to be able to share easily the data that we all have access to and we measure. In addition to this infrastructure that we have created, we are bringing a lot of data to that, raw data to that. So like this map is showing like these dots here are showing like more than 35,000 weather stations that we have access to across the Western US. And those are just like the raw data that we bring to the center to do the analysis and the forecast. But in addition to that, we have like a post-analysis that is very common in like climate science. And those are like the data that are post-processed, the raw data that are post-processed, and like to make sense out of them, like in terms of like how much they deviate, for example, from from the norms. That map in like that map here shows like one specific week back in June this year that shows that like weather in the West was so hot that it was more than like at some point it was more than like 10 to 15 degree above average in an early week in June. So that shows that like we are getting some of this like hot weather earlier in the year, and like that is taking like longer and like impacting a large geographic area. And that's that is done by some of our partners in Desert Research Institute at the University of Nevada. And then we are also, in addition to that, we are also working at wildfire and the smoke out of the wildfire. We have like a wealth of data that shows how wildfires are generated and how they are impacting the environment in terms of the smoke transfer and then how they are impacting the power grid. So one of the things that we have access to is like some of our partners in University of British Columbia. They are well known like globally for the like wildfire model and wildfire forecast that they are generating, plus the smoke model and the smoke forecast that they are generating. But they were like their funding was limited to the work that they do in Canada. Since opening this center, we have enabled them to bring some of those models that are some of the best models in the world to the US and to the Western US, and now they are doing like this globally. This is like this is ironic. I intentionally brought it here. So back in September 12, we had the first grid resilience symposium of this center in Salt Lake City, and then like wildfire was happening, and the whole weather on September 11, the day before, it was like a smoggy because of the smoke we had on the day. So this, but then it turns out that some of the like models that we have here, like it was developed by our partners in University of British Columbia, was actually predicting this pretty accurately, and it was showing exactly by the hour in the day the smoke that we were seeing on the air, like in that the day before the symposium. You can just click on this, you can just scan this QR code and you will see the live map and the live forecast that they are generating every day for the center. But in addition to the weather data, we also need grid data. So the grid we see here, like we see today, and it's been like in the past like 100 some years, it's been very good. It's been delivering reliable power to us. But then there's not a lot of like measurement that we are taking from the grid in terms of the like outages and also situational awareness. So one of the things we are working on to get more data out of the grid, and more data could come in terms of the measurements that we are measuring, voltage, current, power, but also in terms of the outage data that we are getting. In a recent project with our local utility Pacific Core, we installed these like little devices called CFCIs, communicating fault current indicators, that we just basically install on the power lines. And what they do, they send information about the outage current as it passes through the lines. And this has been game changing for recovery and outage management on the grid, specifically in remote areas. When like you don't something happens, you really don't know where it has happened. Like you just have an information about the outages and where you have outages, but where the actual damage has happened, you don't know. But these things, these like devices, and using the information you collect using this from these devices and some AI algorithm, you can narrow down the area that the damage has potentially has happened. So you could actually send the crew there faster and fix the grid, and bring it back to a normal operation as soon as possible. So, but then talking about heat wave like is very complex problem. At the same time, it's increasing the demand. And the way it increases demand is just like by AC, right? So everybody is just cranking the ACs like all day, and nobody wants to let it go. Everybody has to be 74 degree or lower, right? But then on the other side, it's also impacting the rest of the grid, reducing the generation capacity. From the thermal generating units that can't operate in the normal capacity when it's hotter, but also like the solar generation. It turns out that the solar generation, it's not actually as reliable, and it cannot work as reliably when like there's a smoke on the air, when like the air is thinner because of the hot weather. So we have like been able to model the output of the solar generation. We have some models for that is showing how the atmosphere is interacting with the grid components. Specifically, we call it the land atmosphere interaction model, and then how that is impacting the generation on like the grid side. But also it's impacting the power equipment, the power lines, the power transformer. They just don't have, they can't operate in the rated capacity that they are designed to. So you see a situation that there's no immediate outage. Nothing is failing at the moment, but you have an increased demand, you have a reduced capacity of the generation and the grid component. That is putting the strain, the stress on the grid, and which is lasting for a few days. In Arizona and Utah, we just experienced some of the worst heats in the past few years. In Utah, I think this year we had the record number of days with 100+ degrees during the day. In Arizona, I think in Phoenix, we had more than 80 days of consecutive days that it was like 100+ degrees during the day. So this is like, just imagine a grid that is not designed 20 years ago, 30 years ago, 40 years ago to tolerate that much heat, let alone the generation. So this is like a problem that we are working, and also we are looking into the future. What's going to happen like 20 years from now? The utilities don't have the answer for that. But also we are looking at the impact on the communities. So one of the problems we are looking at is that, so now you have a community that is like overheated, all the houses, some of them have access to ACs, and some of them have access to better ACs, and some of them have access to better cooling system in their house, and also like insulation in their houses. So it's not the same. So some of the houses are better insulation, and some of the houses don't have that, right? So it turns out that it's like a kind of there is also an equity issue, that there are some households that don't have access to enough AC, or like their houses is not insulated well, so they get like impacted more. And when it comes to like also demographic of the age demographic, some people are impacted more by the heat, some people are impacted less. So we are also we just recently published a paper that looked at that like kind of community impacts of some of these heat wave, not only on the infrastructure, but also on the community. One of the solutions we are working at is resilience hub. How many of you have heard about resilience hubs? One, that's great. This is a new concept. We just published the paper. There's no academic paper about this, and this is the first academic paper we just published, and that's a QR code about that. It's basically, I think you've all heard about cooling centers, right? So it's kind of an extension of the cooling center, but also bringing it not only like at the community level, just go there and be cool, but also bringing to the infrastructure level. So like trying to serve many purposes, trying to serve the community, trying to serve the grid, trying to like bring many other services that are not available during disaster into one location, into one a building or like a community that could serve the community, not in terms of just like providing the power and also providing the AC, but also providing other like critical services. So as like I've just like mentioned a few examples of that, like we can increase like using resilience hub can help like integrate more renewable energy, provide energy flexibility, enhancing resilience, enhancing critical load backup, and also providing grid services. Specifically, a resilience hub can provide services, all of this during multiple modes, right? During normal operation, it just happens that maybe a few days, few weeks, a year, you have an emergency. But during normal operation, resilience hub also provides services that are very important for the grid and for the community. We just did an analysis on that in Salt Lake City. We identified like using the demographic data, using the like impact of heating, heat and hot weather on the grid. We identified 7 different locations that are potentially that we potentially could install a resilience hub in Salt Lake City to not only tackle the problem of the infrastructure, but also tackle the problem of communities that are impacted by the hot weather. I know this is taking long, so I'm going to make it short. So we develop a lot of AI data. This Wired Global Center is identified by NSF as an AI plus energy center that we just received last year. So what we do, we just have data, and we develop AI tools to make use and make sense of that data. Specifically, we have developed this tool that we call it GAPSIM, Geospatial Atmospheric Power System Interaction Model, that is basically trying to understand the interaction between those extreme weather events and the grid. And it's not as simple as just mapping those like data with the grid component. We are also looking at the interaction between those, which is like much more complex than just mapping. So, and also we are looking at like how we could modernize the operation of the grid using AI tools. We are developing enhanced outage observability and situational awareness tools, enhanced controllability of resources and grid architecture, and enabling automation and AI for grid resilience. Specifically, this is one of our patented models that we have implemented in my lab and in a pilot project with Pacific Core. This is a hierarchical AI-based controller that enables like automatic like restoration of the grid after an outage, and that's been a very successful project that we just like a $5 million project we just ran with DOE. We are developing not only like on the application side, but also theoretical side. We are also trying to see how AI and some of these methods that we are developing are predictable. We don't want to like in a physical world, we don't want like an AI solution that is not feasible, that is putting garbage out there, right? So we've developed some practices and some models that is making sure that the AI solutions are feasible, at least for the grid operation, even if they are not optimal. And one of the other topics that we just started recently working on it last year is like looking at how we can serve the needs of data, the energy requirements of AI and data centers. You all know that. I think power industry has totally missed this. One of the biggest things we do in power industry is to forecast the load. But one of the things that we miss to forecast is how fast the AI and data center energy requirements are going to grow. But then we are catching up, and some of it, not utilities are trying to do that. The industry has taken it in their hand, right? So you all have heard about this news. This is in the news every day. Amazon just invested $500 million on nuclear. Microsoft invested on that. But also one of the projects that I really like, and it's happening in our neighborhood, is geothermal. Fervo Energy is doing great. They just signed this contract with Google. And what I like about it is not just like buying some power. They are developing innovative rates to actually be able to make it economically viable for everybody, for the utility, for the off-takers, and for the others. Just like last month, we had this grid resilience symposium in University of Utah that I myself moderated this panel session, that we brought together all the kind of parties into the same table to discuss about that. Please watch for recording of this that is coming up in our YouTube channel. But we had a representation from Google or local utility, Pacificor, plus Fervo Energy and the Utah Office of Energy Development, plus TerraPower, the nuclear solution. We need more of this innovation happening, and we need all parties to come together. It's not just the utility can make it happen. The user, the generator, the demand, and also the policymakers should make it happen together. We have the work on hydrogen on the workforce development side, and also on the innovation side that we are trying to commercialize some of the technologies. So another plug to some of the things we are doing, and thank you.
Thank you so much. We'll get moving with the next talk, and that's the last one before our panel, and that is my colleague Devin Schaefer, who's going to talk about direct lithium extraction through a successful commercialization pathway. So with that, Devin, just watch out, don't do a face plant. So, thank you.
Thank you. Good afternoon. I'm Devin Schaefer. I'm an assistant professor of civil and environmental engineering here at the University of Houston. That's me. And today I want to talk to you about membrane separations research here at the University of Houston, focusing especially on direct lithium extraction. All right. And very broadly, the focus of my research here is promoting resilient communities and ecosystems through membrane separations that create and recover valuable resources. And so today, especially, we're looking at recovering valuable resources like lithium from brine streams. And what I want to focus on are covalent organic frameworks, which are a new type of membrane material for liquid separations. And they enable us to start to explore membrane design for different applications like fit-for-purpose desalination, separators for organic batteries, and of course, direct lithium extraction. And this work that I'll be discussing today is funded by the National Science Foundation. And so broadly, the challenge for membrane separations is this permeability selectivity trade-off that limits their performance. And this is for any type of application. And so this is one of the main goals that we have to address. And in general, you're going to see this expressed as some version of selectivity, say it's salt rejection for desalination, versus some version of throughput, which might be water permeability if we're thinking about desalination. And across all types of membranes, all types of materials, all types of applications, there's really this trade-off that appears in which high selectivity is achieved at the expense of throughput. High throughput is only achieved with a reduction in selectivity. And so our goal, obviously, is to move into the upper right-hand corner here. How can we achieve both high selectivity and high throughput to be able to produce clean water or to recover valuable resources in an economic way? So I'll show a couple of these trade-off plots and look for moving into the upper right corner is generally the goal. Covalent organic frameworks can help us overcome this trade-off because they are crystalline porous polymers. And so they have some unique properties. They have a very high density of this crystalline structural pore network. So in theory, we can achieve high throughput through pore flow because we have a very high density of pores. At the same time, we can achieve high selectivity because we have a very narrow pore size distribution, so we can maintain a high selectivity. So that's been the underpinning theme of a lot of this membrane research. And especially with these covalent organic frameworks, we have the opportunity to tune the membrane pore size and tune the membrane chemistry by selecting different monomers for the synthesis of these covalent organic frameworks. For the frameworks I'll talk about, probably the most commonly studied, we use the central aldehyde monomer, this blue monomer, and then we can react it with different diamine monomers to achieve different types of pore sizes and pore functionalities. So for example, today I'll show you a pyridine diamine monomer. We'll compare that performance to a benzidine diamine and show how we can adjust the pore size just by changing this diamine monomer. Or, for example, we can start to introduce functionality, working with this diaminobenzene sulfonic acid to introduce a sulfonic acid functional group into the pore while maintaining essentially the same size as another type of COF material. We make these membranes as a composite with a very, very thin layer of this covalent organic framework, tens of nanometers thick. It needs to be supported on a support material. And we do that through an interfacial polymerization process. So first, our diamine is introduced in an aqueous solution. We put our membrane at the bottom of this trough. We then overlay that with an organic solution of the aldehyde. These are immiscible solutions. The monomers stay in their organic or aqueous phases. Only at the interface can these monomers react and form a thin covalent organic framework layer at this confined interface. This happens over a long duration, usually 72 hours. After the film forms, we drain the trough from the bottom, we land our thin film COF onto our support, and we have a composite membrane. Here's a photo of what that looks like, the actual reaction and then some of the resulting materials. Even though we form it in two different parts, the support is separate from the COF layer, they actually are very durable, and we're able to subject them to mechanical stress, and they hold up. So they've been very useful materials. We're up to about maybe 50 square centimeters with this kind of trough technique. And overall, as nanofiltration membranes, they do perform very well compared to other commercial and emerging nanofiltration materials. In this trade-off plot, rejection versus permeance, you can see our work highlighted here against some other emerging materials. And we're doing pretty well. We're moving into that upper right corner, achieving high selectivity while also maintaining high throughput. And this was great work led by Dr. Rasoul Shevte. So once we kind of figured out how to make these and how to start applying them, how to control their thickness, how to control their pore size and chemistry, my students have started applying them in a lot of interesting ways. Dana Flores, PhD student, is using these as kind of model materials to understand the transport of solutes through nanofiltration membranes. Nanofiltration is an interesting size range where, looking at a cross-section, a pore, we have pore flow, but the pores are small enough that we have charge effects, we have solvent effects, and we have dielectric exclusion, we have Donan exclusion. There's lots of things going on. They're sort of convoluted, they're hard to understand. COFs allow us to start controlling these pore properties so we can really model solute transport. Dana made two different materials with the same pore size, but with different charges by introducing the sulfonic acid functional group. Then by applying the Donan steric pore model with dielectric exclusion, she's able to study the relative contributions of different separation mechanisms with these different types of materials and give us insight into solute transport in nanofiltration. Aaron Picton has applied these COF membranes as separators to improve the performance of organic batteries. This is work that's done in collaboration with Dr. Yan Yao here at UH. Basically, they've developed organic batteries, lithium organic batteries, where they're seeing a degradation in performance because a lithium PTO intermediate is shuttling across the separator and depositing on the anode. we developed this COF membrane separator, applied it as a separator in their organic battery. Aaron made the material, characterized its pore size and other physicochemical characteristics. And we saw that it improved the initial efficiency and the overall capacity retention of these organic batteries. Erin's continuing to work with these materials, focusing her PhD research on direct lithium extraction from environmental brines like produced water or geothermal brine. And this is research that is sponsored actually by UH Energy. Erin is a UH Energy Fellow, so we're very grateful for that support. And in this work, Erin's focusing on the lithium extraction process from brines, which is shown in red in this flow schematic. It's very complicated. It involves a lot of separation steps, especially to separate magnesium from lithium. They have very similar physicochemical properties. If we could implement direct lithium extraction in green, we have the opportunity to really simplify this process and to make it more economical and hopefully to increase purity in production at the same time. And so two different applications Erin's looking at using COFs is first for supported ionic liquid membranes, studying what are the performance limiting trade-offs that define the design conditions for a supported ionic liquid membrane to achieve at the system level, but getting down to even the interactions between the membrane and the ionic liquid. And these covalent organic frameworks with their controlled pore sizes and tunable pore properties can be great hosts for very selective ionic liquids to achieve high purity lithium products in direct lithium extraction. The second application we're looking at is engineering the COF pore chemistry to change the solvation environment inside the pore and help facilitate lithium transport directly from the brine feed source. And this is specifically looking at polyethylene glycol chains, which can help dehydrate the lithium and draw it through the pore. And we're looking at trying to scale that up and apply it at a larger material scale based on some initial work promising work that's been reported in this area. And then our initial results have been promising. Erin's shown enhanced lithium transport for materials that have been functionalized in these different ways. So we're excited about the initial results and looking forward to continuing to pursue this in collaboration with some researchers in France. And then finally, kind of commercializing this technology, Erin's very interested in transitioning some of her lab work into the commercial space. And she, as you saw, one of the limitations is really the way we fabricate these membranes. At a liquid-liquid interface, long durations, it's limited in area. We produce large volumes of solvent waste. So it's not a very scalable process. Erin paired with Parisa Taheri, who's also working on these materials. Parisa is working on scaling up the production of covalent organic framework membranes. So Parisa is using electrospray deposition to create these COF membranes, again, COF composites. And she has tested lots of different conditions, different catalysts, different solvents, different electrospray conditions, and basically has shown that we can control the development of covalent organic framework membranes. We can achieve membranes with the same crystalline properties as some of these other techniques, and we can do so much more rapidly and using a much more scalable technique that's electrospray. And she showed that these are the stars here, comparing the interfacially polymerized membranes to the electrosprayed ones. They essentially perform the same. They essentially have the same physicochemical properties, just a much more scalable production. And then we're also looking at durability testing, which is really key for trying to commercialize these. And we see that the membranes perform well in very low pH conditions. They stand up to mechanical stress, sonication, bending. We do see a little bit of loss in performance at very high pH conditions and high temperatures, so we're continuing to study that. And then finally, Erin and Parisa teamed up to really try to start commercializing this and start understanding where this has a role in the marketplace. So together they formed a company called Liquidium, and they started, along with Pranjal Sheth, who's very involved in UH Energy as well, he's a finance student, they started exploring the market. They started doing customer interviews, talking to lithium producers, trying to understand if there could really be an impact for this technology. And through these interviews, through their discovery process, they learned that really there is a desire for some sort of plug-in unit that can replace existing water-intensive, chemical-intensive, time-intensive processes like adsorption and like liquid-liquid extraction. So they're very motivated by this idea. They started building a business plan. Even though the technology readiness is still fairly low, they really see a lot of opportunity here. And they started refining that business plan through participating in these student pitch competitions, like competitions hosted by UH Energy. They participated in the DOE Energy Tech Up competition, winning their regional competition and presenting at the national competition. They went to Singapore. It's been this great experience for them to get lots of feedback, meet lots of interesting people, and really help hone their research questions. Most recently, they participated in the Rice Business Plan competition and won the NOV Energy Innovation Prize for their business pitch. So it's been really a wonderful experience. It has shown a commercial path forward, and I would say it's been very motivating for their research and has really helped them refine their research questions. For example, we're focusing a lot on durability because that was a persistent question from the commercial partners. So I really encourage, you probably have students that are involved in things like this. I think it's been a wonderful experience. I think it's been very motivating for them, and it's been very positive for their research as well. So thank you for your attention.
Thank you, Devin. Appreciate that. There's one quick question. We can take it.
Yeah. Yeah, the DLE process, did it focus on large or small scale? The business plan that they came up with was a large scale on a sort of on a service basis where they would provide the material, provide the service, and provide the maintenance to like a geothermal brine producer. And then the lithium product would be shared in some, I forget the exact arrangement for the business, but the lithium would be shared, yeah. Sure. Maximum and minimum temperature. We're still exploring those bounds. We do see some degradation in performance at 80 degrees Celsius. So we haven't tested the lower end of that, and we're working to try to improve the temperature range for operation.
Thanks so much, Devin. Appreciate that. And, we are now ready for the panel. Before we get started with the panel, I just thought if anybody needs to take a quick break, we can take a quick break, and in 5 minutes we'll get started. But I'll sort of ask Joe and the panelists to come up and get started here, get situated, and then in 5 minutes we'll get started.
All righty, everyone. Well, I'm Joe Powell again from the University of Houston Energy Transition Institute. I'll be moderator today, and I'm going to kick off geothermal. We're going to ask each of our panelists how they got started in geothermal, and then they'll tell you more about themselves and then a little about the activities that they're up to. And so I'll get it kicked off. I got started in geothermal about 3 days ago when Ramanan asked me to chair this panel. I am from Shell. We gatekeeped on geothermal for quite some time. I don't think we dived in because of how globally impactful and the amount of penetration. So that'll be one of the questions to resolve today. But excited to be here and talking about it. I picked up some neat history slides about some of the early developments going back to the early 1900s, quite a bit on the West Coast area there in California and such, and in France. And so it's not exactly new technology, but in terms of impact moving forward, and certainly exciting to see about what were some early deployments of renewable energy, quite a bit on the western part of the U.S. is some of the leading development opportunities there. And so our panel today, we have Professor Joe Moore from the University of Utah, Tim Latimer, CEO of Fervo, Mike Eros, who's Chief Geoscientist at Sage Geosystems, and John McLennan, also of the University of Utah. And they'll be teeing up their response to my question of how do they get started in this field, a little bit more of the details about them. Just a few pieces of data on geothermal. So looking again, going back to some of the IEA reports on installed capacity and in renewables. And again, you see the steps, the stated policies, the pledges, APS, and then the net zero emissions type profiles that the IEA and others are looking at, and where solar PV, wind, and other renewables are playing. Geothermal is usually appearing in the other renewables, and you really have to dive into that to see how much is taking place. And as we discussed in the hydrogen part of the rollout, there are a lot of different scenarios in terms of really how deeply the world is going after decarbonization in terms of how much penetration there will be in that space. And so I really had to dive into the appendix of the latest IEA report of the World Energy Outlook of 2024 to find the geothermal numbers in there underpinning those graphs. And they are pretty small, so they've been ticking up, but you can see that in general, geothermal is on the lower side in terms of the penetration to date, in terms of renewable sector contributions to decarbonization. Now, I'm also doing direct air capture work for Shell, the DOE, and projects there, and so it's pretty exciting to see some of the integrations of geothermal with direct air capture, namely what's happening with Climeworks in Iceland. So you've got this wonderful combination of basalt formation where you can actually just capture the CO2 in water, and you've got enough water you can pump it under the ground, and the basalt is taking it up very quickly, much faster than the studies were indicating. And you've got a geothermal plant that's actually powering that. And so you see some really exciting developments. That may be the only place in the world where that combination is happening. I'll be asking the panel about that. But the integrations are really exciting to see of where the opportunities can be in terms of the use of geothermal as 24/7 power. And then the DOE is talking about advanced geothermal. And so I think that's the first time I've done a presentation with only 8 slides, but I'm going to stop here and then go to our first contestant, which will be Professor Joe Moore from the University of Utah, and be speaking on how did you get started in geothermal, and then tell us a little bit more about yourself and what you're working on today.
Absolutely, happy to do it. So I've got a few more days than you do, Joe. I started in the mid-'70s and in geothermal and have been active since then, primarily on conventional geothermal systems, those that are currently being produced today, and then moved on to EGS, enhanced geothermal systems. I got involved, I worked for a short stint at the uranium company, Anaconda Uranium Company, and we were looking at hydrothermal uranium deposits, those deposits that were effectively geothermal systems. And at about that time in the early to mid-'70s, DOE started to take an interest in geothermal. They were thinking about how do hydrothermal systems work. And I left Anaconda and joined EGI, where I still am. My background is in geology from Penn State University. It was a great place to be, and I really enjoyed that. But lately we've been working on FORD, Frontier Observatory for Research in Geothermal Energy. I serve as the project manager of that project, and we'll talk about that in a few minutes.
And you passed that test, so you go ahead and you get to go ahead and show your work now. So
oh,
go ahead,
nice
Joe.
slides. Is that how it works? It's great. All right. This is John's slides.
Go ahead.
I can talk about them.
Okay, well, let's, John, why don't you tell us about yourself and how you got started in geothermal?
It'd be appropriate if Joe went first, but
You did go first, so, but yeah, we'll go over to John now.
We'll change the slides
Yeah,
then.
yeah.
You know, 3 days does qualify you as an expert these days.
I'm glad to hear that.
And my background started with my PhD thesis, which was sponsored by Los Alamos Scientific Lab back then, to do research related to fracture mechanics at Fenton Hill, which was a pioneering hot dry rock project. And then after a career in oil and gas and the last 15 years at the University of Utah, I've been lucky enough to ride on Joe Moore's coattails and get back into the geothermal business, particularly on the Forge project.
All right, and you have again passed the test, and let's go ahead, and I think you're going to be able to show your slides, so let's try that out here. And are these your slides then?
No, these are mine, but
okay, no, go ahead. No, go ahead. All right. We'll continue on, and we've got a plan here.
I don't think we do, but so it would have been ideal if Joe could have introduced the Forge site.
Okay, well, let's try that. We'll toggle through the slides.
So thank you very much. I really appreciate this opportunity.
And show me when, are these your slides, Joe? Show me when you're...
Keep going. Keep going. You're getting there.
That's going to be Mike.
Yeah.
Okay.
Doing great. Doing great.
Next steps, reception networking. All right. So I think we've got Sage in there. And Furbo, we had the link that we needed to show. No, we're looking for the other set of...
Yeah, I'll put them in the box. Are they not there?
Okay.
They were called more?
Yeah. And so let's go ahead with
These are close.
John. And we're just going to have to continue with the Plan B, and let me find the other slides to get going forward then. So I'll leave that with you for now. And good luck. Always the Plan B.
So, well, thanks for having me back. So Joe will tell you later on about the Forge project. But the basis of the Forge project, it's a Department of Energy sponsored field laboratory where wells are interconnected by hydraulic fracturing, so that you have an injection well and a production well interconnected by hydraulic fracturing to form a heat exchange network in situ. That's opposed to conventional geothermal, which is basically you're drilling a well till you find a fracture, till you find fluid that is produced at a hot enough temperature. And so just in terms of this, Joe was going to tell you about that, and he will. Well, I think he will.
Yeah, I will.
But you know, the message here is that we see a lot of excitement about geothermal today. And I just want to walk through the life cycle of a geothermal project and talk about ways that we can maintain this momentum. The truth is, the way we maintain the momentum is the success of these folks and their companies. But there are some technical issues that will help us maintain the momentum. And the first is with continued exploration. And one of the things about enhanced geothermal systems is that you don't necessarily need to be beside a plate boundary. That basically you can drill till you find adequate heat, then you can create your own reservoir. And so that's the nice thing about an enhanced geothermal system. So you might ask yourself a couple of questions. First of all, where Forge is. It is probably one of the premier enhanced geothermal systems reservoirs in the world. So is it a unicorn? Is this just a delightful anomaly? And can we progressively have an eastward expansion of enhanced geothermal systems? Is that legitimately reasonable? And southward, too, I might add. And so one of the ways to do that is by continuing to develop improved exploration technologies. And I was glad to see the talk this morning by Yingcai that 3D seismic is going to be particularly important. One of the troubles that we particularly run into is the lack of impedance contrast in some of these granitic reservoirs. And so anything, as he talked about, for example, AI or whatever technologies that can improve the resolution for determining faults is going to help that. Because the thing that is going to restrict the use of this in urban areas is potentially seismic hazards. And identifying those is particularly important. The second is continuing to upgrade methods for geothermal exploration in general. That it's not my specialty, but it seems like magnetotellurics and those technologies are great, but they don't give you necessarily the resolution that is required to make intelligent financial decisions. Whoops. The third thing is moving eastward and southward. We have the opportunity of looking at so many penetrations from the oil and gas industry. So I think back analysis of that is really going to help out. And finally, water, no matter where we are, is going to be an issue. So understanding the availability of water is going to be important. So then the next thing down the line is you have to drill these wells. And drilling technologies has dramatically improved with the introduction of polycrystalline diamond compact bits to the geothermal industry. Yes, that sounds surprising to people from the oil and gas industry, that the geothermal industry has been using roller cone bits for a substantial period of time. But there's been a lot of progress recently, and I think maybe Tim, are you going to talk about it? You'll hear a real success story on drilling technology, at least in these relatively homogeneous reservoirs. Where more trouble has been encountered with PDC bits has been situations with interfacial severity. And same in the oil and gas business, where you're going from one formation to another, or you're hitting some sort of a natural fracture. And I think research needs to continue on that, as it does in terms of increasing the applicability for use in higher and higher temperature environments. Ruggedized RSS, rotary steerable systems, I'm not sure you need them, but it's something that's potentially useful. The other thing, and I was particularly interested in the presentation from Dr. Srinivasan this morning, is that I think a real opportunity is using the bit as a laboratory. I think we are on exactly the same page on that particular category. Is that taking the signals that you can measure from sensors at the bit or just raw bit performance in general and making inference about the mechanical properties of the rock, the characteristics of the reservoir, is absolutely a logical next step for the oil and gas and the petroleum industries in general. And so that was a very nice coincidence with his talk this morning. The next step, so you can drill these, and the next step is appropriate reservoir characterization. And one of the things that we found on the Forge project, and I think folks have found it on other commercial projects, is fiber optics, just like in the oil and gas industry, has been very, very helpful to us. We have found, we managed to ruggedize these so that they lasted for at least a year, and they provided outstanding information, and I think continue efforts to ruggedize these and deploy them economically and flexibly is going to be something that we're going to be looking at in the geothermal industry in general. The next thing is understanding fracture growth. And we do it normally by monitoring microseismicity, but any sort of methodology to do that cheaply, at least on pilot projects, is going to be particularly appropriate. We have found, in terms of geophone technology, that 150 degrees C, I think Joe can vouch for that, is about the limit where we can keep geophones in the hole for extended periods of time. And then the final thing is a chicken and egg. Okay, we want to extend the thermal characteristics of logging technologies, but we have to establish that there's a market for those before it's going to be substantial. It's going to substantially happen. And so it looks like the market is coming. It's exciting, and so we're waiting for the service companies to roll out those new tools. Cementing and casing, I think, remains a bit of an issue. We've had difficulties at Forge in terms of cementing, and I think that continuing to look at it, particularly if we go, as we go, that is, above 200 C, that we're going to have more and more difficulties with cementing, and maybe we're going to have to really think about cementing to avoid casing failures because of the amount of hydraulic fracturing that is really required in these particular wells. And in terms of hydraulic fracturing, well, we could spend a whole session on this, but I think one of the things that intrigues me is at Forge, we put one well immediately above another. And that may not have been the best choice. Initially, we were basing it on buoyancy and the movement of fluids. But probably, I think some of the technologies that Fervo has adopted, where there's a lateral displacement as well as a vertical displacement between the injector and the producer, is going to get better heat efficiency. And so I think that there's a lot of room for people studying this, along with studying the actual materials. I'm convinced from our recent experience that proppant is required in these wells to guarantee conductivity. What we don't at the present time know is how long sand as a proppant is going to hold up in these high temperature aqueous environments. Maybe it's not going to be too much of a problem once the fluids are equilibrated in a continuous loop, but I think we're waiting to see a little bit whether or not proppant, more sophisticated proppant may be required. And we're hoping that that's not the case because of additional expense. To carry that proppant, we probably have to go back to chemistry with fracturing fluids. At least that's my opinion. That if you want to carry these proppants higher up and have them remain suspended, we may need to be using viscosified fluids, and we may need to be looking at agents that hinder settling in terms of these proppants so that they don't fall out. The work that Resman did for us substantiated that a lot of our proppant probably settled out, and we pumped both slick water and cross-linked carboxymethyl hydroxypropyl guar in different stages. And so maintaining that proppant and having some form of hindered settling may be an appropriate consideration. The other thing that worries us at Forge are some of our parasitic losses. We carried out a really successful circulation test back in August and September, and we found that the temperatures were constant and stayed up for 30 days. Constant, stayed up at about 385 degrees Fahrenheit, but we had to pump at about 2,900 PSI. And the parasitic losses for doing that at a long period of time are probably not economically successful. They may not kill a project, but we'd like to reduce them. Then ultimately, this is truthfully one of the more interesting findings from Forge. And maybe if I'll just spend a little time on it, because the debate in geothermal as opposed to petroleum is whether or not natural fractures really matter. We've seen a lot of the work from the HFTS projects where it suggests that fractures are relatively planar and don't interact, and that natural fractures don't necessarily play a substantial role. However, this is our injector, and you can see a dot with each one of our clusters that we used. And this is the producer, and we had fiber optics in the producer, and we monitored the hits. And what we noticed is that stage 3, 4, and 5 all came out at the same place. Stage 6 was like this. Stage 7 came out like this. Stage 8 spanned about 400 feet, and stages 9 and 10 occupied the same production zone as the end of stage 8. So it strongly suggests, at least in our case, in this particular situation, that natural fractures do play a role in these, and that there are corridors, just as has been found elsewhere in the oil and gas business. Tim may want to say more about this because they may have slightly different experience. But ours is that we see these natural fractures exist, and we need to deal with them. I'm also convinced that you have to frack both the injector and the producer in these cases. I think that's almost essential to do that. And so the really important thing coming out of this is the ability to forecast thermal resilience over the long term. And I'd like to come up with tests where we can use AI and machine learning and other technologies so we don't have to inject for a year to figure out whether or not we're going to have thermal depletion. So that's a challenge. And then the final area is topsides. I don't know much about topsides, but I won't let that stop me. So I think one of the things that we want to consider is cascading use of power, is combined heating and electricity generation in terms of geothermal in general. Hybridization is absolutely essential. I think that that's the key. Geothermal can provide the supporting power to solar and wind at night. And I think that there are huge, huge applications for that. As long as we can get through some of the permitting and financing challenges that are associated with those activities. Reduction in parasitic loads, as I mentioned, new refrigerants. Water usage is going to be a big deal, particularly in the western United States, because we'll lose some, and so we may have to deal with them. And we also have to anticipate that there are going to be chemical treatments that are likely required for corrosion and for carbonate inhibition, scaling inhibition. And then finally, a couple of things that have made this happen and will drive it forward and will maintain the momentum. And the first that has helped this seriously is your federal government has been at work for you. And actually, this has been a very, very useful exercise and expenditure of federal money to establish the feasibility of enhanced geothermal systems. And the second thing is the success of companies like Sage and Fervo, because nothing will drive this and maintain the momentum more than their success. And so we're, no pressure, guys. Anyways, just want to acknowledge the Department of Energy, and you'll be able to hear what Forge is about when we find Joe's slides.
And we're there, so thank you so much,
okay,
John.
Thank you.
I'm thinking this mic is working, and so now keep all of that in mind. And I think, Joe, you're going to paint a picture about how we got there. So I'll let you take it off as part A now.
I'm certainly going to try.
There's a slide advancer. And look and behold.
Look at that. Yeah, that's familiar.
Very familiar. Okay.
Wow. Well, I hope we've been entertained at this point. It's going to be hard to fill in what John left out. But this is obviously Utah Forge, Frontier Observatory for Research in Geothermal Energy. I'm sorry, is the mic not on?
No, but hold it up to you.
Oh, is that working better? All right. Thank you. Okay. So just to back up a little bit, U.S. currently produces about 3,900 megawatts of electricity from geothermal systems. Tiny, tiny amount, 0.04% or so. We'll hear more about that. But virtually all of this electricity is coming from hot springs. Okay? Around the world, 16 gigawatts around the world. And really, if you look at what DOE's goal, and these are DOE's goals for Earthshot 4, which I think gave everybody a kick in the pants to move forward. The Secretary 2 years ago announced 60,000 megawatts of geothermal energy by 2050 and reducing the cost of EGS by 90% to $45. You're going to do that, aren't you? You're going to drop the cost? Yeah, good. Good. We can drill cheaper, that's for sure. Jeff Tester, a couple of years ago, in 2006, in fact, came out with the conclusion that tapping 2% of the energy between 2 and 6 miles would provide more than 2,000 times the yearly U.S. usage. Okay, and this let people know that you can produce geothermal energy east of the Mississippi. And in this plot I've taken at 4 miles, we'll put electric generation about 150 C. Okay, that works. And a lot of the new systems are at that. But basically take away that the heat's inexhaustible. Okay? So I'm not going to talk much about the geology. The geology is very well defined at Utah Forge in the neighboring mountain ranges. Sorry, there's no pointer. We see this nice lime green and red and magenta rocks. Those are 28 to 11 million year old granites, and they extend under the Forge site, and they extend further to the west at about 25 degrees below the Fervo, below Tim's site. So we understand these rocks quite well. You can see here that what the Forge site looks like. To the east, where it says thermal ground, that's an active geothermal system. It's been producing since 1984. So long-term, 36 megawatts, called Blundell plant. To the west of us and north are 168 windmills. To the west of that is solar fields. So this is part of Utah's renewable energy corridor, and that's an important component. Let's move forward. The concept behind Utah Forge was really to build a field-scale national laboratory for de-risking tools and technologies for enhanced geothermal systems. And when we went into this, it was really hydrofracking. Okay? That was the concept. It was not advanced geothermal systems at that point. It was just crack the rocks, push water through, and make electricity. So our job was to develop the techniques for that. We've drilled 8 wells, 7 of them are shown here. There's a water well that isn't shown. You can see the depths, and on the right, the temperatures. Highest temperature's been about 240 degrees C at 9,500 feet. And that's well 78B32. Okay? Point out that 56, 58, 68, 78 A and B, those are vertical wells. Those are really used for monitoring. I'll talk about that in just a moment. Wells A and B are directionally drilled, and that's our production injection pair. As John said, A is the deeper of the two, and it's both wells are deviated. We drilled 4,000 to 5,000 feet, 65-degree deviation from vertical, and you can see the dash line as the tracks of the lateral. Okay? The B well, the production well, is about 300 feet, 100 meters vertically above the injection well. In the spring and fall, we did stimulation and circulation tests. John alludes to some of this. I'll come back to it. And that was important. It was a commercial level project, commercial level circulation test. We injected, 13 barrels or so an hour. We recovered about 90% recovery at a temperature of about 193 C. So commercial results, commercial scale test. Very, very successful. And we'll hear more about these tests, I think, in a little while. Okay? So with that in mind, we use 2 different methods to monitor. And I think both of these methods pushed the methods further, and they yielded really unanticipated results. So the first was the seismic data that we collected. This was data from the stimulation. There were 10 stages with a maximum of 8 clusters. Stages 1 through 10, they start at the toe and work their way up. One of the unanticipated results is, as you can see on the right, and what looks like a structure, a crescent-shaped structure. And on the right-hand side, 2 wells, this is looking down on the 2 wells, that trajectory of that structure follows sigma H max. On the other side of the 2 wells, it's more northerly. That's probably a natural fracture that's taking some of the fluid. The black dots and the orange dots are magnitudes. Orange is greater than 0.6. The black is greater than 1, and the maximum magnitude is about 2.3. We have a very strict traffic light system here that tells us what to do if we exceed both 2s and 3s. I don't know if I can get the left hand to work. I'll give it a try. Oh, there we go. So we'll see these stages being populated with the seismic events with time. We'll just watch what happens. So these were the early stages. Now we're seeing some of the later stages. Maximum magnitudes are occurring on the margins of these seismic fields. There's our, so we just watch this and see what it looks like. We're seeing about equal height versus depth, which is, guess what we hope for here. And so this will move on for just a minute, and then we'll move on. Okay? Get some idea what this looks like in 3D. Okay. Okay. The second thing that John mentioned was deployment of optical fibers. 3 different fibers were deployed in our production well. One was a flat pack, UT Austin, and the second was a Silixa packed by Rice University. And the third one was just a pressure temperature gauge. So we had in both of the optic fibers that I mentioned, Silixa and the flat pack, we had DTS, so we had multi-mode and single-mode fibers. We were monitoring distributed temperature, strain, and seismic acoustics. And in the third one, that was a gauge that went to the heel of the well, and that was just for temperature and pressure. So here you can see a plot of strain change rate, and we don't spend much time at this right now, but if we look at stage 8, and John mentioned that stage 8, 9, and 10 coalesced, right? What we see is that the uppermost frac hit, which is to the left, so the y-axis is in depth, the x-axis is in time. So if we look at the earliest time, we see that stage 8 was fracked at the shallowest depth. And then with time, the fracks move down, not at all expected. As John showed you also, what we saw was that the fracks were oblique to the wells. We expected hydraulic fracturing, that the fracks would grow perpendicular to the wells. I didn't do that, suggesting that DFN, natural fractures, played a role in controlling fluid flow between the 2 wells. So all of the data we've collected is in the public domain. I think this is unusual for any company, oil, gas, or geothermal. All of this is available. This is all of the seismic data, all of the pressure data, temperature data, well data, drilling data. It's all available to you. Go to GDR, Geothermal Data Repository. It's free. You can access it. If you can't find it, call me, because sometimes it's a little difficult to extract that data. But there's a lot of it there, and we hope you'll use it. So, left it open to questions later.
Well, thank you so much, Joe, for Plan A, backfilling here. And let's see what's up next for us here. Roll the dice. And Mike, tell us about how you got into geothermal, and tell us about yourself, and then if you pass that test, we'll go on to the slide deck.
Great, thank you everybody. I appreciate the opportunity to be here, and in particular I want to express the gratitude also of Cindy Taff, my boss. She's the CEO of Sage Geosystems. She unfortunately had a family incident happen and she couldn't make it unexpectedly today, so I'm going to pinch hit for her with this illustrious panel. I also just want to say it's a pleasure to be at the University of Houston. The chief modeler on our team is a Cougar. All the mathematicians on our team are from the University of Houston, so big respect to that team there. Also, as a Houston-based startup, we build on the shoulders of the innovators like Fervo who've been doing this much longer than us. And so today, I'm going to give you a taste of what we're doing, hopefully explain a little bit more about our technology, pique your interest, and give you more to think about. I'm a geologist. My background, University of California at Davis. I grew up in West Virginia. I ended up working for ExxonMobil for 12 years, technical team lead for U.S. assets. I developed an interest in geothermal during my time at ExxonMobil and kind of discovered from that corporate perspective what the risk profile tolerance was for things like geothermal, and attended actually Pivot 2020, the first conference that Jamie Beard hosted and got folks interested from the oil and gas industry into learning more about geothermal. Had the opportunity to meet Lev Ring, the founder of Sage, co-founder with Lance Cook and Cindy Taff, and they made an opportunity for me to come and test their technologies in the subsurface. But I'm a geologist by background. And today I'm going to give you a little bit of a perspective on two business lines that we're pursuing in particular: underground energy storage, subsurface energy storage, and geothermal power. This is too small to read, but essentially, as I mentioned, these two business lines, we have a bias towards testing things in the field. We've raised more than $50 million since 2020. We've spent probably 30. We have a long way to go. We're trying to raise a lot more. We recently signed an agreement with Meta to provide 150 megawatts of power by 2027. That's kind of the far end of this graph on the right. But you can see in the middle these boxes which signify how we re-entered a well in Starr County, which is near the Mexican border, that Shell had drilled in 2008, large casing. We're innovating around completion styles at the same time that we're trying to innovate around surface plant equipment, because as John mentioned, the surface side and the subsurface side really are necessary to make more efficient, to make this whole system work better. So the technology readiness levels that we're approaching are between 7, I'd say 7 and 8. Towards the end of this talk, I'll give you a little bit of a glimpse of our first pilot built in the field, which is our energy storage facility in Atacosca County, just about an hour south of San Antonio. But just to, you can give that flavor, that's kind of where we're headed. So this is a slide kind of summarizing a little bit about how SAGE fits into the ecosystem of enhanced geothermal systems. And also to mention just our next phase of development around that, which is going to be geothermal testing. So on the left, you see a little cartoon here. And this is on our website also in this cartoon fashion, with SAGE showing 2 wells, one going down right next to the other. And essentially right next to that, you see an enhanced geothermal system, or EGS, which is kind of the more industry standard, the forage approach, where you go down one well, you connect to another well in the subsurface via fracturing. And then on the right, you see closed loop systems, which are another approach which is being tested. I just want to stress, very few companies in the world, A, have raised the capital, B, have the people in the field to even begin to test these things. So I feel very privileged to kind of share some of the early results of that. And building off of what we have, Fervo and Tim have done a lot more, and so we're all learning together kind of how this approach is going to work or not. But it's a very exciting time. On the right-hand side, you see an image here of about a 4-foot tall supercritical CO2 turbine. And this is an area of innovation that we're progressing with the Southwest Research Institute near San Antonio to make turbines more efficient, smaller scale, things that you could put on an airplane, honestly, and fly to Nigeria if you need to, and potentially offer you the ability to have a competitor with organic ranking cycle turbines from Turboden, et cetera. That's not yet at TRL 8, I will say, so bear with us as we continue to test that. We did a pressure test, though. We did a spin test at 20,000 RPM 2 months ago, so we have our design down. I'm very excited about that. But let me back up a little bit and just give you a view about what SAGE is doing as a company. We are innovating around managing pressure in the subsurface. The founders of SAGE, Lev Ring, Lance Cook in particular, were instrumental in inventing something called managed pressure drilling and developing that at Shell and Weatherford in the early 2000s. That's something I encountered at ExxonMobil. We were drilling wells in the Gulf of Mexico, West Africa, Deepwater Guyana. It allows you to really dial in your pressure management, more than 10 to 20,000 feet subsurface within, say, 200 PSI remotely from rigs. And so that's the technology that we are essentially working on. This is a very busy slide here, and I apologize, it's the most text I have on a slide, but I want to sit here for a little while and give you a little more background. So I mentioned, and it's on the upper right, this is the little cartoon view of SAGE, two wells side by side, in this case vertically oriented. On the bottom left here, you see operations testing from 2022, 2023. We re-entered a vertical well, I mentioned about 11-inch casing. We constructed a dominantly vertically oriented fracture. Now, we connected about 3,000 feet of rock with a fracture vertically. This is something that in oil and gas terms we used to call blowing out the shoe or drilling overbalanced. And this is a technology that honestly, when I was working with BP in the Gulf of Mexico, we wanted to avoid because it would end up connecting your reservoirs where you didn't want it. But Lance had the idea to take this really and work with it in a different way, to create maybe T-shaped fractures or chevron-shaped or something with a vertical root to allow for greater connectivity to heat below, but also importantly for you to be able to basically open and close the fracture. Now, we didn't know this would work. This is something that we had modeled very extensively with physical models. I mentioned Doug Simpkins, our mathematician on the team. He had brought this up, and actually there's a paper here, I note here, Simpkins and all, 2023, if you want to read more about that. We tested this in the field. So what you're seeing here on the graph on the right is pressure through time in a black line, and essentially showing how we were able to initiate fractures at greater than fracture initiation pressure, and then dilate them, but not to go to runaway propagation fracture pressures. And so that gave us an operation window of maybe 200, 300 PSI, which we then cycled repeatedly. And so we did flow in, flow out testing. We didn't know this would be the best way to run this. Honestly, we tried perfs that were shallower, perfs that were deeper, connecting, circulating, trying to go up versus down. We ended up settling on a huff and puff style approach, which is a term some folks may have seen from heavy oil industry approaches, essentially putting the well flush with the fracture system full of water and then pulling the water back out of the same well. So this is kind of the heart of the geopressure geothermal system that I'm talking about, is that we don't rely on subsurface communication between wells. We're trying to cut costs wherever we can. We're trying to make the wells more efficient by doing this. And what we're doing with the pressure space with these, you can see the rise and fall, is essentially opening and closing these fractures. There is some precedent for this in natural hydrothermal systems, which over thousands of years encounter similar pressurization, depressurization cycling. And so far we haven't seen things like crippling fines migration. Now, we've only done 2 years of testing. This is an area of really rapidly developing interest for us. And this is also what we will be approaching in our field testing next with the U.S. Air Force. In Starr County, again, we'll be re-entering our well. We recently received funds from them to test that with the idea that we will then make geothermal power with an organic ranking cycle that we rent at the surface, and then prove that we can do this approach, as John mentioned, in areas that are not just in the Rockies or the Great Basin. That's our next approach here. So just a little bit, though, about this is that by cycling water to the surface and back, we're essentially, hopefully, driving greater efficiencies and the system as a whole, lower cost, and then also by managing pressure in this way, we're creating more of a zero voidage system where we're not losing water to the formation uncontrollably. In our tests so far, we've seen about 2% water loss, and we need to maintain that for a lot of reasons. License to operate is a big one. We need to stay away from the pressurization risk profiles associated with induced seismicity, for example, and that's something that we work very closely with the University of Texas Bureau of Economic Geology to monitor. They do a third-party independent validation of our technologies in terms of not inducing seismicity. So happy to answer more questions about this, but I just want to give that overall view of what a geopressure geothermal system is and where we're headed to test it. On our way to our approach with geothermal, and after constructing these majorly gravity-oriented vertical fractures, we found that actually we had a battery effectively for energy storage in the subsurface. We found we have about 70% round-trip efficiency for taking grid power, which could be wind, could be solar, and using that, compressing it, putting water underground in our large fractures, tens of thousands, if not hundreds of thousands of barrels, and then holding it for, let's say, more than 4 hours, which is about the economic limit of most lithium-ion batteries today. After that, they become less efficient. And then we enter the sweet spot of long-duration energy storage. Earlier today, folks talked about meeting energy demand where it is. You know, that's a really big deal. You know, there's folks who put out papers really effectively showing that geothermal subsurface pressure energy storage can help bridge the gap really for nighttime and shoulder time energy production. So the grid is intermittent, as you know. Solar and wind are intermittent. If we can approach a sweet spot of 8 to 16-hour long-duration energy storage, now we have a way to make those 24/7. So that's what we're doing. In particular now, thanks to funding from Expand Energy, we raised another capital round with them in April, formerly Chesapeake. We are now building a 3 megawatt commercial facility on the San Miguel Electrical Co-op land, which is a coal-powered, actually coal mine also, power plant near just an hour south of San Antonio. And their goal is to replace that entire plant, which is about 400 megawatt capacity, with solar power in the next 10 to 20 years. But as I mentioned, the price of batteries is a very big concern for them. And so they want to test our technology as a way to more efficiently scale to store energy for the hundreds of megawatts capacity. So I mentioned about 75% round trip efficiency, maybe 3 to 5 megawatts energy production per well. And so that's really a lightning round of what we're doing. I want to acknowledge all of the partners and collaborators. I mentioned a few. We work closely with a number of different branches of the U.S. military. We're testing at 3 different bases for feasibility studies in the United States and Texas in particular. We're kind of an interesting company funded by climate change philanthropists who want to bring zero carbon solutions to the world, Viria, but also Neighbors Drilling, who want to see less boom-bust cycling in the oil and gas industry, drilling, and make a more sustainable future for drilling and drilling employees in Texas and the world. So very excited to hear more from you guys and also hear from Tim.
All righty, well, super Mike. So, and last but not least, Tim Latimer. We've heard, Tim, that the industry is standing on your shoulders as CEO of Fervo, and also let's roll the dice here about seeing the slide opportunities. You actually have a cloud-based presentation, and so we're getting some direct help in getting that one launched, I believe, and it's a great slideshow. But yeah, again, start with how did you get into your journey into the space, and then tell us how you got to that point of being a leader in the field with Fervo.
Sure.
So you can go ahead and get started, and we will bring up here we are, look at this, lo and behold.
Yay, slides. All right. Well, first, I'm excited to be here. Thank you for the invitation, and it's great to be at the University of Houston. I live like less than a mile away from campus, so this is quite close to home to me, and we're very proud to be headquartered here in Houston, Texas, and it's great to be on this panel with Mike, a fellow entrepreneur navigating in this space, and the University of Utah, our esteemed colleagues there who we've been collaborating with for many, many years now on this. So it's wonderful to be here. I got my start in geothermal, I guess fairly consistent theme across the panel, because I was drilling wells for oil and gas first and then got excited about geothermal. In particular, my first job was a drilling engineer for BHP out of college. I was working in the Eagle Ford right when the shale boom was taking off, and the Eagle Ford is a little higher temperature than some of the other onshore basins, and so my first assignment period as an industry was to figure out our motors were failing, our MWD was failing because we thought it was temperature related. So I was sent off to research high temperature drilling solutions. I found the same exact paper actually that Joe just mentioned, the Jeff Tester report on the future of geothermal. and that came out in 2006 and through that research in high temperature drilling. And that paper basically outlined that there was an unlimited amount of geothermal out there, but only if we overcame some technical challenges to make it cost effective. And that was principally lower cost drilling and then getting higher flow rates out of low permeability formations. And I thought it was just the absolute most obvious idea ever that if horizontal drilling and hydraulic fracturing was able to accomplish that for first gas and then oil, that geothermal would be the next revolution there. And I think it is truly a revolution. And it's interesting to start this talk with IEA forecasts of what geothermal will look like in the future, because I'll say, hopefully somewhat confidently, that those are going to way underestimate how much geothermal we will build across the globe over the next couple decades. And I do think it's important to share that parallel with the oil and gas industry and the experience with shale, to do a different three-letter acronym agency and look at EIA forecasts. I remember when I started my career in oil and gas, the EIA was still forecasting that the U.S. was destined to become the largest importer of natural gas in the world. And here we are 15 years later as the largest exporter of natural gas in the world. And it was because horizontal drilling and hydraulic fracturing unlocked an energy revolution, and I think we're in the same spot here, where all the three-letter agencies are going to come up with new forecasts as they see the things that people on this panel are doing to drive costs down. So that's how I got here. Moving forward, a little bit about Fervo. So first off, something I think will resonate well in this city, in this room, our mission is to leverage geoscience to accelerate the world's transition to sustainable energy. As a drilling engineer myself, I thought that people were really overlooking all the contributions that the geosciences could make to the energy transition, and that at the end of the day is why we're in business at Fervo. We think the world needs to move to more sustainable energy, and the geosciences are going to be the backbone of making that happen. We also like to talk a lot about our core values. I won't dwell on these too long other than talk about innovation through collaboration. We are always excited to share our data in symposiums like this. And it's also, I must always highlight the Utah Forge project. This has been what I hope will continue to be successful, and we'll look at back on this as one of the most successful public-private partnerships of all time of getting a new technology to market. We couldn't do what we do at Fervo had it not been for the years of collaboration we have with the Utah Forge team. So always want to make that acknowledgement. You know, and what is it that we do? It's pretty straightforward, and for a room of industry experts like this, I don't need to get into it too much, and you've already seen a lot of it. Almost all geothermal projects drilled over the last 60 years since the first power plant came online have been vertical wells, unstimulated, and you just hope you find fractures. Fervo focused on drilling horizontal wells and doing a multi-stage hydraulic fracturing process. Easy to show on one slide, hard to implement in practice for all the technological challenges that you've already heard about today. But we turned that slide into a real project. So in 2021, we partnered with Google as part of their 24/7 carbon-free energy initiative, and they became our first ever customer for our pilot project that we did in Nevada. I'll point out, since we've already talked about fiber optics a lot today, we had fiber optics on all 4 of these wells. We did a isolated 4-stage, 10-cluster hydraulic fracturing treatment in the proof of concept well in 2020. It met most of our technical objectives in terms of breakdown pressure, fracture geometry, cluster efficiency, and it really gave us confidence to raise another round of capital, move forward with Google, and drill the next 3 wells you have there: a vertical monitoring well, again instrumented with fiber optics, and a horizontal injection well and a horizontal production well. On October 30th of 2023, so almost exactly 1 year ago today, we brought this project online, the first ever horizontal commercial enhanced geothermal systems project. This project has been producing roughly 3 megawatts of electricity and has been doing so for 12 months. And we'll be able to say a full year next Wednesday. And one thing we'll point out from a temperature standpoint, because this is one of the major research questions of enhanced geothermal systems, we have observed no thermal decline in this project at all, even though it's been producing power for 12 months, which is something that I can tell you the first independent engineer report we got after we commissioned our well test said that we would experience, the word is exactly, catastrophic thermal breakthrough in 17 days. and we're now 350 days past that with no thermal decline, which I think speaks to a little bit how radically different this approach to enhanced geothermal systems is compared to the conventional geothermal industry, where it's an entirely different paradigm of reservoir management than what a lot of people are used to. So that's our pilot project that we completed last year. And we've moved forward with Project Cape. And speaking of the public-private partnership, in all of the photos you'll see of Project Cape, you can see the Forge site and vice versa, because they are literally next door to each other. We saw the great drilling results that this Forge team produced in 2018, finding a very high temperature reservoir, what we thought was the great test bed to move forward enhanced geothermal systems. And we decided to move in and develop it as a private sector partner to try to do a commercial project to build off the research results that Utah Forge was pioneering. And so we're well on our way now. It's a 400 megawatt project. We have fully contracted that to utility customers in California, as well as to Google, who continues to be one of our largest customers. And we are moving forward with this project. We have actually drilled 15 wells there to date, and I'll show some data on that on the next slide. And we are actually broke ground just 2 months ago on the power plant. So we're building 3 36 megawatt turbines out there for phase 1 of that project, and we'll begin producing electricity that we sell to the grid there in 2026. So in terms of infrastructure project timelines, it is literally right around the corner, and it's quite exciting for me to be out there to see drilling crews, completions crews, as well as all of our civil works and plant construction going on all at once right there. It's quite a cool sight to see. And this was the big result that we produced in August of this year. So I mentioned our pilot project in Nevada is producing roughly 3 megawatts. We wanted to go deeper, hotter, bigger diameter wells, longer laterals. We actually conducted our first well test at the Project Cape site, which I'm showing videos here, in July and August of this year, and we achieved a peak electricity production equivalent of over 10 megawatts there. So just in the span of one project to the next, through longer laterals, better completions methods, doing higher temperature geology, we have tripled the productivity of from our first well system to our second well system. And we don't think we have come close to exhausting the potential upside for driving even more efficient wells. But I can tell you, we'll get into the project economics in a second, producing 10 megawatts of electricity from a single production well starts getting you to the point of making very economically attractive projects. So we're well on our way there. By the way, a note, we were doing this well testing at the same time as the Utah Forge, so it was pretty cool to be out there. You could stand on our pad, look at our steam, turn around and look at the Utah Forge steam, and just it was amazing to think about all of the exciting things for the future of the global energy system that were happening right in this valley in Utah. So really cool to be out there. So cost, this is what's held geothermal back for forever. And I'll show it on the next slide, but people believe that enhanced geothermal systems would be cost prohibitive. To get drilling costs down, you have to drill faster. So when we first started drilling our well at Project Red, our first project, it took us 75 days to drill our first deep horizontal well. It's a very high temperature reservoir. You're drilling through granite. You have to deal with all of the issues that come with that, and it's a larger hole size than most onshore oil and gas projects. And so we were excited to even get it done, because people said you wouldn't be able to drill a horizontal well in those conditions, but it was not something that was cost effective, 75 days. By the time we drilled our second well there, we dropped it to 58 days. And I can tell you we've now progressed, and our most recent well that we finished drilling at the Project Cape site was completed in just 17 days. And that's despite the fact that it is over 4,000 feet more measured depth than the well we did at Project Red. So whenever you turn it into a cost per foot basis, which is because it all comes down to the cost, we've dropped our costs from the first ever well we drilled, where we were around over $1,000 per foot of drilling, to now we are down in the $350 per foot mark. And so we have not only tripled our productivity from project to project, but we've slashed our drilling costs by over 70%. And that's led to a pretty dramatic change in cost. So this was already talked about, the commercial liftoff report and the ambitious goals that the Department of Energy has set. We've taken a chart that they put in their liftoff report and broke down costs on a $1 per kW basis for what enhanced geothermal systems could do. And the 2021 baseline that NREL had for what a deep enhanced geothermal system project should cost, they said it should cost about $27,000 per kilowatt. And I know not everybody here is probably a power plant cost engineer, so I'll just tell you, no one will ever buy power from you if that's your capital cost. And if you want to know why people weren't paying attention to geothermal, it's because the general consensus was that it would cost that much. Now, we published our data from Project Red in 2023, and the DOE updated their forecast basically to say that the cost structure was about half from those anticipated values before. And I noticed the lines are a little off, so before I do my big reveal on the next one, I'll caveat, I don't know where the little white box will show up because it seems to be off kilter. But when we look at our project costs for Project Cape, the project we're doing in Utah, and we look at the ambitious 2030 goal that the DOE said was an incredibly ambitious target, we are coming in, it's not below. It's actually right at that line. I think the formatting got messed up a little bit, but their goal for 2030 was to hit a $5,000 per kilowatt cost structure, and we are hitting that number as we speak on our project today. And if we've talked today about the theme of AI and power demand and the pressure to decarbonize and what that's doing to power markets, I can tell you there is an unlimited amount of demand for power at that price point, which is why you're seeing our business and the whole industry of geothermal really take off. And I think that ambitious 2035 target, I think we're going to end up getting it before 2035. We do this with a lot of partners. I won't go through all of these, but much like what Mike said, it's a combination of people who are deeply passionate about climate and people who are great at drilling wells and the geology and the geosciences. And again, I'll put a plug there for the Department of Energy support and the Utah Forge support. And just one last thing on where this industry is going. This theme of reliable, affordable, clean electricity and the drive for new reliability and the drive for meeting demand sources from AI and other things is creating a huge market. And we've now executed power purchase agreements that are valued over $5.7 billion in terms of binding contracted lifetime revenue from our projects, and we're just getting started. So the future of geothermal is a massive, massive industry, and I think it is going to be, the surprise of the energy transition. And I think if we're in this room together 15 years from now, we'll be talking about how deeply misunderestimated that IEA report is, just like we can talk about how everybody missed the revolution from shale oil and gas. And that's how we see the future. So thank you for that, and excited to continue this conversation with the panelists.
All righty, well, thank you very much, Tim. Let's see, somebody's missing a microphone here, and I've got the podium. So that answered my first question going in 3 days on the job. It's a revolution, and it's all about the drilling at the end of the day. So I guess the issue are similar to what was happening with the hydraulic fracturing and the shale gas revolution. What do you see as the risks here? So we see opportunity out in front of us, but where do you see the risks that you really have to maneuver in order to make this revolution happen? And Tim, I may just start with you since your mic is warm there.
Yeah, it's a great question, and it's still not a foregone conclusion that this is going to be as revolutionary as it should be. I would say first and foremost is not a technical risk, but actually a financial one. If you look collectively between the Bipartisan Infrastructure Bill and the Inflation Reduction Act that were both passed in 2022, it put tens of billions of dollars into new energy technologies. 10 billion new amounts of DOE funding for nuclear, 9 billion for carbon capture, like 8 billion for hydrogen. In total, the geothermal industry got $84 million between those bills. And so we're trying to compete in a marketplace often with projects that, there are individual nuclear projects, for example, that have gotten, for one project, more DOE funding than the entire industry of geothermal has in its existence. And so being at cost parity when there are such major disparities in public funding is a major risk. And I think that's one of the things that is happening. And I think it's related to a second point, which is we're in a unique moment in time in the power markets where the demand is here and the demand is now. And these data center companies want power to come online ASAP. And I think it's really about how can we get the exciting results that you've heard about on this panel today out into the public zeitgeist and talking about it so that we can attract the investment and put more wins on the board, because otherwise you're going to see this moment of demand move on to other sources if they don't think geothermal can be scalable enough. So I think those are the big risks is, can we attract the capital we need to move forward? Can we be competitive with other resources that get far more government funding? And can we move quick enough to keep the attention of the customers who are very, very hungry for power right now?
All righty. Anyone else want to take that particular question on the risk side?
So maybe from a technical risk, one of the things that I think is a little bit uncertain relates to conformance, okay, or the equivalent to conformance. The equivalent to conformance that we know in conventional reservoirs is that you have multiple hydraulic fractures, and if one of these fractures starts to cool off, how can you control flow into that fracture under extreme temperature conditions? I think the technologies are there. I think they can be applied, but I think that that's just something that's going to need to be addressed.
And what does that risk translate into in terms of impact?
Well, you want the worst case scenario? So as you start to inject colder fluid into fractures, if one or particular fracture starts to take fluid, then thermoelastic effects are going to happen, and the aperture of that fracture at the injector is going to increase. And progressively, that fracture is going to take more and more fluid, and it's almost catalytic. And so you ultimately may be cooling off your produced fluid.
Okay, so it's really an economic and technical risk. And so in terms of managing the induced seismicity risks, the history reports had some of the very early natural productions had some radioactivity and such. So what other types of public risks, would people worry about or basis previous discussions in this space that the public needs to be comfortable with, I guess is my question.
Well, let me address some of those questions, because they're critical questions. And I think what John mentioned, too, are opportunities at this point. Yeah, we're going to have circulation issues that we have to plug up, and it's a good opportunity to develop these tools. But as you mentioned, the biggest issue is seismic, at least in people's mind. Actually, in the West, the bigger issue is water usage. So we can address both of those. In terms of seismic, we've had some issues in some areas of the world, Pohang, Basel, Sulz, and we recognize them, and the DOE recognized them. When we started the Forge project, the first thing we did was an exploration program, and we used reflection seismic. And in fact, what we discovered was that the main basin and range faults are tilted. And based on the geometry, this was not an area that was likely to slip. So we looked at potential for induced seismicity very, very early on. And we concluded that the risk is relatively low. We think it's important to be absolutely transparent in everything that we do. So when we do something, we invite the local folks to come out. Forge has put computers in the 3 libraries and in the area, and the smallest town is 700 people. And those computers can pull up seismic data in real time. And so we make sure that the local townspeople know that we are going to do it. We are going to make some seismic events. They can come and watch, they can come and stand, or they can watch the computer in real time while we do this. And Tim has had some. We've had over 150,000 events. We have a very, very well-defined traffic light system. And if we exceed the limits on the traffic light system, we stop and we figure out what to do. And that may be to stop pumping, it may be to produce. But we have this outlined and it's available. So we recognize that we're going to have seismic events. The biggest we saw at this point was a mid-2. So not very high, certainly not sensible. And our goal is to figure out how to manage the stress field so we don't have large events. And then we constantly monitor. And it's difficult from the oil and gas industry. I don't think people really recognize that when you take these geophones and you put them down at temperature, they don't last. 150 degrees C is a good temperature for many of these, and we're trying to get them deeper. At 180, we may get 4 days out of some. So we're working on new directions, fiber optic cables with 3-component geophones, higher temperature geophones. All are critical for monitoring, so at least we know what's going on. And if we see something happening, then we can stop and take the correct approach. The second area, which in many of the Western states is even more critical, is water usage. We're taking away, and we heard this, the first thing I heard from the townsfolk was, you're taking away my water. And the water that we are using, in fact, is non-potable. It contains chemicals that are potentially hazardous, and the state has concluded that this water cannot be used for human consumption. It can't be used for grazing. It can't be used for agriculture. And so we have to make it very, very clear that we're not taking something away, and we're not adding risk to the local community. Again, it's transparency, it's monitoring, and it's working with the locals. So no surprises later on.
And so a quick question, as you move to a new site, we heard that drilling costs are one of the major drivers, but how much does it cost to go to a new area and do the risk management in terms of the amount of ground information that you have to acquire in maybe an area that you're not familiar with?
I guess we probably spent about $10 million on the exploration phase. We've been monitoring the area through Utah Geological Survey, Utah seismic stations since 1981. So we knew what the seismicity was, again, the two big issues, and what the water chemistry is. So I think relatively quickly we can get to a point where we can determine if the site is a good site or not. And also looking at the infrastructure. I think it's appropriate, I don't know if Tim was getting there, but basically the rocks we're looking at, these granites are found across the country. So they're the basement rocks everywhere in the country. And I think we're doing something that's comparable to anything we might do back east.
Very good. And Ramanan, how are we doing on time? We're still good, okay. Another question about the integration opportunities, and Mike, you had brought that up with perhaps Department of Defense and other ways. How do you get maximum value out of geothermal with its 24/7 and really get that priced into the marketplace?
It's a great question. And honestly, I point you to a study that Fervo did with Princeton on this very topic, looking at the utility of geothermal technologies to contribute to grid stability and innovate in that area as well as baseload power generation. I mentioned the storage component of what we're doing, which does not require heat. There's a benefit from using hot water, more physically buoyant, in a storage system like I described. I'd say the opportunities are massive right now, and in particular, the demand. So Tim mentioned the huge demand for just baseload power led by data centers, et cetera, et cetera. There is an equally large demand for energy storage, which is price competitive. I was in Oklahoma last month. Texas also experiences the same thing they do, which is more than 10% curtailment of wind production in many, many markets, which basically means they can't put the power that they're generating anywhere quick enough. The grid is not built up enough. So energy storage is really a critical element of their economic model. I mean, we're talking with one of the two largest wind farm companies in the United States who are keen to really get new technologies to market in this area. So like Tim said, I think we're at a really important opportunity right now for that. So with the Department of Defense, they have a separate kind of budget, if you will, which is handy. They don't have to make things as price competitive, but they are also looking for energy storage and baseload at the same time. It's all hands on deck for both.
So you can replace some of those coal plants we were learning about in the previous modeling exercise. And Any other comments in that space?
Yeah, the other thing I'd add, in addition to the valuable, dispatchability and storage attributes that geothermal can provide, the other thing that makes it unique among renewable energy resources is the heat component. And we are starting to see, we started looking early on that a lot of the sorbent technologies for direct air capture, require an activation heat that is kind of the waste heat temperature for a geothermal power plant. And so, as those technologies struggle to get to market, a big piece of it is how do you get the enormous energy requirements needed, and a lot of it's in the form of thermal energy and low-grade heat. And so we got a grant going back 2 years ago from the Chan Zuckerberg Institute to explore integration of direct air capture with geothermal, and that's expanded into, we were one of the award recipients on a teaming partner for what we call the Red Rocks DAC Hub, which is around our site in Southwest Utah, looking at carbon sequestration potential. So that's a big area. And then there's other things as we looked into this market more where there's huge demands for low-grade heat in a whole host of different industries, food and agriculture, paper and pulp, you name it. And those companies often have just as ambitious climate targets as the big tech companies have, but getting cost-effective low-grade heat that's carbon-free has been an almost insurmountable challenge for them. And so, it's possible that the market for geothermal heat in the medium to long term might be even bigger than the market for geothermal power.
Well, very good. And I realize that I'm in a room full of geoscientists here. And so, Christine, let's kick off the questions from the audience. Okay.
I understood that you were describing two horizontals with multiple parallel fractures, and you've got 12 months of successful constant heat supplied to the surface. We heard about geophones, but I thought I heard you say you have fiber optics. So do you have confirmation that you're getting uniform flow through these parallel fractures?
So, it's a great question, and the answer is we have some confirmation, not as much as we would like. Our experience with fiber optics was mixed. We've done fiber optics on 4 wells now. 2 of them are still recording and successful, and 2 of them recorded useful information during the well stimulation phase, but then we had both fibers in our horizontal wells severed at different stages of the operation. So we got about half lateral coverage in one well, and then only through the heel of the other well. So we don't have the direct production data that we would like to see there. But what we looked at from a cluster efficiency standpoint with the fiber optics that we were able to collect during that test was very encouraging. We had a very high cluster efficiency. And then the logging tools don't exist to log the production well, but because the injection well, you're pumping down it, you can cool it off enough, you can log the injection well. So we've done multiple injection flow production logs in the injection well, where we've seen a high degree of conformance across the different stages, including large contributions all the way down to the toe of the well, which is what you want to see. We've actually published that data in a couple of different white papers that you can find that our CTO, Jack Norbeck, has authored. And so directionally, I think our philosophy on this is that you're not going to get uniform distribution across the fractures. Some fractures are going to connect, some aren't. And so for the time being, the way we solve that problem is dramatically over-designing the system. We assume a percentage of the fractures connect and a large percentage do not connect. And one of the things that we think the cost and performance improvement over time is going to come from is getting a lot better at understanding what drives that. But what we've seen, and I think 12 months of production, it's not definitive. Everyone now that we have 12 months of production, everybody wants to know what 20 years of production looks like, but we're 19 years away from that. But what we've seen so far has been highly encouraging, that the conformance we see, the cluster efficiency we see, and the percentage of fractures that do form a connection are sufficient for commercial viability today. And so I think that's really the metric that matters most to us, because can you be profitable so you can do more projects, you can get on the learning curve so you can come down more in cost. But the short answer to your question is we have some data, not as much as we'd like, but the data we do have is very, very encouraging. No, because a short circuit would show up in the temperature profile, and we keep refining our history match over time. I can tell you, because the spacing on our pilot project is really tight spacing, because we were worried about not getting the right connection. So we knew that the thermal decline was going to be much more elevated than sort of a go forward project where we have much larger spacing. Our initial production forecast saw thermal decline starting 4 to 6 months into the project and then kind of entering a long gradual decline phase. Every month that goes by, we try to get a better history match because we still don't see the decline. So we do expect it to start declining at some point in the next 12 months, but 12 months ago, I thought it was also going to start declining in the next 12 months. So, each day that goes by, the data just becomes much more valuable for our history matching.
Yeah, great presentations, and thank you for coming. I'm just wondering how long is the permitting takes for these things? And secondly, Tim, you may know from Eagle Ford experience cases of frac hits. Seen frac hits there for 3-4 miles. I know these are early days here, but what do you see if you have multiple operations of geothermal wells? In some ways, it's probably good, but do you see a negative effect of that too in these, or not really?
So multiple questions. First, permitting, and then
permitting. It takes a long time, but it's getting better. There's actually true bipartisan consensus in DC on permitting reform, and actually, I think Mike would be interested to hear y'all's experience on private land, because it's really a tale of two stories. Unfortunately, the geothermal world's put in a spot where you either have to go to where the best geology is and deal with the federal permitting timelines, or go to less good geology but deal with more reasonable permit timelines. So, our project. We just announced last week that we got our final NEPA approval to begin not just the drilling but the power plant construction phase of the site in Utah. And from the moment we filed for our first lease application there till we got our final NEPA approval for the Project Cape in Utah, it was about 5 years. And we are getting accolades for that being one of the smoothest and fastest NEPA federal permitting processes that have ever happened. So that's been our experience. You can permit them. It takes a lot of hard work. It takes a lot of time. What's exciting, in addition to announcing our project last month, or our project approval last week, they also announced a new suite of categorical exclusions that are going under administrative review right now to really bring geothermal permitting on federal land to more parity with oil and gas permitting on federal land, which is a much more streamlined process. And we think that's going to be very, very helpful. But that's been our experience on federal land. It's challenging but doable, and we're actually quite optimistic that there's strong bipartisan support that's going to make it better in the near term.
If I could chime in too, everything he said it's spot on. And the challenge, you step back, you think a company even like Ormat, which is the world's largest private, publicly traded company working in geothermal, they're looking at timelines easily were 7 to 10 years, even 5 years ago. So folks like Tim have gone to the Hill, brought forward this issue, made some progress. Honestly, that's remarkable. We at Sage dealt with this mainly by doing most of our testing in Texas. Let's just be honest. That's the fastest way to get to market, really, for us. I mean, we've looked at partnerships and have active partnerships in Europe. You can read about those in the permitting time, but it's beyond what we ever encounter, even in states like California, in terms of hesitancy to permit. We got a categorical exception exclusion at Ellington based on similarities from our work to other approved Air Force sites, in particular in Idaho. But that was the only way we were able to move forward and avoid the very arduous NEPA process that Tim mentioned. So we are very excited also about this progress on BLM land. Our private partnerships have offered us, though, in Texas, a really great way to move forward. And like Tim said, we kind of have to deal with the rocks that we get in those locations. But we've been working with McAllen Ranch, also Fela Martinez Ranch, South Texas operators who are interested in bringing forward a new generation of energy on their properties. And so they are able to work with us and use, thanks to lobbying efforts from Geothermal Rising and the Texas Geothermal Energy Alliance, new rules in Texas that have clarified over the last 2 years where we stand with geothermal power production. Service ownership is really the definition of the heat ownership here for the last year, thanks to those efforts. So we've gotten a lot of clarity in Texas. We have a long way to go across the country, but we have a lot of hope that it's moving in the right direction.
Yeah, just in general, we always kind of relate this to oil and gas, and we working with Pinnacle, we followed Mitchell with the Barnett to where we are, where stages were going, $6,000-$7,000 a stage down to whatever they are, $2,000, $2,500 a stage now. But I guess for the Fervo guys and the Sage guys, and for Joe and John, it seems like these guys got to go to the plate and hit a home run every time. And I guess it's, is that the way you feel with your project? Because there's, from the transition from what George Mitchell did in the Barnett to where we are, pretty much all the shale projects, there were a buku of wells drilled. And there's so many permutations from our limited experience. Maybe you want a perfectly working tractor to get down there, but I guess just in general, do you guys feel like you got to hit a home run every time you punch out a system, and are there lobbying efforts to provide that understanding that this is going to take time to develop? These systems are going to be optimized. I sincerely believe in what we're doing, and I think it will pay off. But one black eye can go a long way to set us back. So.
Yeah, it's a great question, and I think one of the things I'd point out there is it's interesting when you think about the trade-offs in designing of new experiments, because in some ways you want to test a wider variety of more radical approaches so that you can learn faster. And in other ways, you want to increase the likelihood that your next test is going to be successful. And I can tell you right now, we're funding our projects with about 99% of the capital that is going to go into, we have a couple Department of Energy grants that we're very excited about, but about 99% of the capital that goes into our project CAPE will come from private sources and investors that expect a return on that project. And so this is one of the areas where I think federal funding could help a lot, because we only want to test incremental things as a result. Because we know 300-foot spacing works, so let's try 400 and then 500, and then as long as it keeps working, we'll go there. Now, if your goal was to learn faster, you would say, okay, if 300 works, let's try 100 and let's try 1,200, and we can collect a more disparate data set. But we have so much pressure, we can't afford to have a failed well right now, that it's forcing us to be a little bit more incremental in our R&D program than we would like to be. And so I think that's where more funding for DOE funding that goes into projects like ours, or increased funding for efforts like Utah Forge, would just make it a massively more successful learning curve. So far we're 2 for 2. We've done 2 production well tests, and they've both been very successful and very much in line with our modeling results. And I would say, in the comparison to shale, it's a lot like shale. We couldn't have been 2 for 2 had it not been for the hundreds of thousands of wells drilled for shale. Sometimes I tell people that it's a little bit funny. We're doing the shale revolution, but in geothermal, but it's like we got given the textbook that had the answer key in the back, because it's like all the hard lessons learned over 25 years since the first Mitchell Energy well, we know those now. And yes, geothermal is different. It's a different geology. It's a different production system. But things like, screen outs, like the mitigation measures used on screen outs, those are the same in our wells as they are elsewhere. And so we get to kind of run through the innovation cycle of shale, longer laterals, more productive wells, more intense proppant loading, more productive stimulation treatments on speed mode, because we have the answer key, and we're not trying to reinvent the physics. We're just trying to apply it in a new domain.
If I could quote my friend Joshua from University of Chicago here, he pointed out we need 18 forges. honestly. That would be the great answer to your question. If we had 18 forges, we could test all of these ideas, like Tim's saying, and work faster. Also, just if we take a step back, 5 years ago, there were only a few hints of the types of wells that Fervo is now drilling month after month. So the data is now coming in for the first time from what we're doing, and we're kind of learning how we can set expectations. For us at Sage, we also think beyond just, I would say, federal funding. Tim mentioned that less than $200 million amount, $80 million amount, which is so tiny compared to what, say, carbon capture or hydrogen have received. We've had to go to other entities, and we've been working with private industry, much more so in response to that. I would note, though, the hunger for innovation on this is global. We partner with ADNOC, which is the Abu Dhabi National Oil Company. They're looking for the future in Abu Dhabi for not only energy storage, but even geothermal. There's other groups out there. We're partnering with Romanian partners to look at direct heat use. Tim mentioned the ability to provide thermal capacity, not just power. So there's other partners out there. Of course, public spending would be ideal. I think we have to go in this thinking about educating. We're all ambassadors for the technology now, and we can speak to how it can succeed.
De-risking is one of the key goals of the Forge project, and we do need more forges. There's no question about that. But let me give you some examples. As owners of the well, some of the things that we've done. We've tested plugs, we've tested packers. Initially we had about 100% failure, but we've tried different ones. And eventually we did figure out how they work. We've tested particle drilling, and we've tested mud hammers in our wells with no liability to the companies who owns them. And I don't know how many oil and gas companies or geothermal companies would take a perfectly good well and say, well, why don't you go in there and see if you can drill with a mud hammer, and if we lose the hammer or we do irreparable damage to the well, there's no liability to you. So we are taking very, very significant risks in what we're doing, and that's, I think, critical. And we need that continued DOE support to do that.
All righty, with that, I think we're going to have to wrap up, and let's have a round of applause for a really great panel discussion. And like the lunch group, I'd like to get a photo, and you'll get your gift cards immediately, as you will have access to snacks and refreshments immediately after the event here. But thank you so much for a very good presentation. And the one thing we learned today is that geothermal is who can complete the sentence? It's a revolution. Okay, that's what we've heard. And so we'll take that. So thank you very much. And you all are such a great audience that we're going to offer snacks and refreshments to you as well here as we're done now. So,
Joe, thank you so much for organizing this panel. There is a poster session outside. There are about many of our students from University of Houston and Utah have put together posters. Please do attend those, and there'll be snacks. And so thank you all for attending. We greatly appreciate it. There is a session tomorrow at the Technology Bridge. It's much more of a workshop-style effort where we're going to be talking about potential collaborations. If you're interested, please let us know. We'd love to have you come and engage. It's in the Technology Bridge in Building 9. It starts at 8:30. Please come and join us then.